but forcible consequences of the externality of efficient causation. Needless to say, every one of the foregoing consequences of the doctrine of causality is refuted in the theoretical processing of experience, one that is, in science, since, save by abstraction, we never meet anything devoid of qualities and standing apart from change, nor do we find, except by abstraction, qualities outside objects endowed with them, whence the expression. Emergence of qualities should be understood as just a convenient metaphor for appearance of new qualities in an object. The above-mentioned conceptual possibilities following from causalism amount to regarding the substance-attribute connection as a contingent relation, that is, as one that does not stem from the nature of either. That is, causalism leads to the conception of the attributes of things as accidental determinations, the scholastic accidentia, as contingent either relatively to the very essence of things, or relatively to each other, or both. This phenomenalist view of qualities and of qualitative change is of course possible solely on the assumption that things lack a self-movement enabling them to assert their peculiar being, their personality, to indulge in an anthropomorphic term. 8I.2 Contingency of attributes in Hegelianism and positivism. The thesis of the contingency of attributes is not, however, exclusive of causal ontologies. It can also be found, in a more or less explicit form, in two influential systems of metaphysics which, at first sight, share nothing but their dislike for causalism, namely, Hegelianism and empiricism. Like Leibniz before him, Hegel held that conceptual entities are necessary while natural ones are contingent, that is, they might have been different, and they are contingent because they are external to their own concept, constituting accidental, unbound aggregates of externally related properties. 2. The properties of the concrete object, das unmittelbar Konkrete, are logically external to one another, are not deducible from one another, whence their existence in a given object is not necessary but more or less indifferent. 3. That is, according to Hegel, properties neither follow analytically from one another, which is right, nor constitute systems, which is wrong, they are mere heaps or aggregates of accidental marks. As a consequence, the play of forms has in nature the character of the unbound, unrestrained chance, ungebundene Zufälligkeit zufällig. Kate. Point 4. Natur is, in short, the kingdom of contingency and randomness. This belief, revived later on by Baudrou, the philosopher, 5 was one of the reasons why Hegel held nature in contempt, the other reason being presumably nature's obstinate refusal to conform herself to his schemes. The problem of the substance-attribute relation hardly arises in empiricism, which regards substance as a figment of the imagination, not, however, on the ontological ground that there is no matter without motion of some sort, but on the epistemological ground that such a constant and simple support of qualities is transpiritual. On the other hand, empiricism has usually held that things are unorganized aggregates of sense data, lacking both an independent carrier and an inner necessary bond, that events just are, in experience, without there being any genetic connection among them, or among the qualities of every complex or aggregate of sensations unless such a bond is superimposed on them by God, as Berkeley, the most consistent empiricist, thought. From this doctrine of qualities and change it follows, of course, that everything we see could also be otherwise. 6. And that the laws of nature and of society are nothing but summaries of experience, empirical rules, or directions, Vorschriften. 7. That might have been different. According to empiricism, laws are, in short, contingent relatively to the nature of things, and this for the simple reason that there are not things placed in an independently existing external world, but only lumps of sensations, and that which experience establishes further experience may demolish. Thus 2 varieties of immaterialism, namely, objective idealism and radical empiricism, attain, with regard to the problem of qualities and their changes, conclusions similar to the scholastic theses. In point of fact, they all ultimately end up in some sort of fortuitism in the domain of nature, while retaining strict necessity in the domain of discourse. In all three cases, scholasticism, Hegelianism, and empiricism, the ontological thesis of the contingency of nature is a consequence of idealism. In the case of most scholastic philosophies of nature, a further source is paradoxical as it may seem at first sight: causal determinism. 8.3. Beyond causalism and accidentalism, when carried consistently to its extreme consequences, the doctrine of efficient causality may lead to indeterminism. It could not be otherwise, since the scholastic concept of quality and alteration as accidentia that are alien to the essence of things, and that are stamped on them from the outside like removable tags, is complementary to the belief that nothing, save God, can be self-caused, but everything must be determined ab extrinseco by something else. A way of avoiding indeterminism while sticking to the belief in the externality of causation is to adopt Malebranche's doctrine of occasional causes, which, in the domain of ethics, leads of course to a serfdom no less complete than the hopeless helplessness to which indeterminism leads. If matter were nothing but extension capable of being pushed and pulled hither and thither, and if mind were nothing but a tabula rasa capable of receiving external stimuli, as Father Malebranche thought, then he would have been right in regarding change as brought about by the sole efficiency of God. But Malebranche's occasionalism, grounded on the identification of matter with passive extension, and on the tenet of the essential passivity of finite spirits, is altogether inconsistent with modern science, which exhibits the dynamic character of the real world and the large extent of spontaneity in the behavior of every bit of both sensing and inanimate matter. Moreover, this sort of causal determinism is self-defeating, since it withdraws causation from causally zero and novel zero, the world, turning it into the exclusive privilege of God, the sole active and efficient substance. The extension of causality to include self-determination led Spinoza and Leibniz to modify the traditional definition of substance, which etymologically means that which does not change. 8. They asserted that the very substance of things consists in their activity, and they more or less clearly recognized that efficient causes are not sufficient producers of change, as their efficiency depends on how deeply they disturb inner processes. Leibniz went so far as to declare that the natural changes of monads come from an internal principle, since an external cause could not influence their interior. 9. The scientific discoveries of Leibniz's own time, modern dynamics, corpuscular philosophy, embryology, and so forth, certainly supported the doctrine of self-movement. Still, they did not warrant his exaggeration of it, an exaggeration to which he was led partly by the Hermetic writings, which had always emphasized the inner principles of things and of man. The adequate course is, I believe, the synthesis of extrinsic and intrinsic determination, suggested in the previous chapter, and such a synthesis stops the whole babble about the accidentia, rendering both quality and qualitative change intelligible. 8.2. Causality renders genuine novelty impossible. 8.2. The principle causae quod effectum: if the joint action of several causes is always an external juxtaposition, a superposition, and in no case a synthesis having traits of its own, see sector 6.2, and if the hypothetical patients on which the causal agents act are passive things incapable of spontaneity or self-activity, incapable, in short, of adding something of their own to the causal bond, see sector 7.r, then it follows that, in a sense, effects pre-exist in their causes. According to this extreme but consistent doctrine on the what causal determinism does assert nature of causation, only old things can come out of change. Processes can give rise to objects new in number or new in some quantitative respects, not however new in kind, or, again, no new qualities can emerge. A world running on a strictly causal pattern is such as yogis, Thomists, and 18th-century Newtonians imagined it, namely, a universe without a history, aching no step forward and running, as Hegel said of nature, around a perpetual circle after the model of the apparent motion of the heavens, before the corruptible, that is, changeable nature of celestial bodies was discovered by Tycho Brahe and Galileo. The formula summing up this extreme version of causalism is, there is nothing in the effect that has not been in the cause. Now this thesis admits two variants, both of which exclude novelty, at least as a natural event. According to one of them, the effect includes the same as the cause, symbolically, C equals E, whereas in the second version the effect contains less than the cause, symbolically, CE. In the former case we have the old formula, causa quod effectum, which by no means should be admitted by consistent believers, since it entails the divine nature of the Creator's works, pantheistic heresy. This is why Thomism asserts that like begets like, that cause and effect resemble each other or at least cannot be too dissimilar, as every agent intends to induce its own likeness in the effect, so far as the effect can receive it, with the important proviso that the effect never receives the whole content of the cause. Before analyzing this important and widespread theory of change, it will be convenient to place it in its historical context. 8.v. Archaic origins of belief in immutability. One of the oldest written statements of the above-mentioned view of change is found in the Upanishads, 1000 to 500 BC, in which it is metaphorically said that whatever there is belonging to the Son belongs to the Father, whatever there is belonging to the Father belongs to the Son. L1 This assertion of the identity of antecedent and consequent was also the kernel of Solomon's celebrated wisdom: the thing that hath been, it is that which shall be, and that which is done is that which shall be done, and there is no new thing under the sun. Is there anything whereof it may be said, See, this is new? It hath been already of old time, which was before us. 12 A sociologist of knowledge would perhaps say that these pieces of scriptural wisdom reflect the boredom of pastoral and agricultural life, with its recurrent cycles, and that they were probably supported by the wish to preserve the corresponding social structure. The oldest theoretical elaboration of the view that the effect is similar to the cause and is even contained in it, so that no newness can ensue from causation, is perhaps the Causality religious philosophical doctrine 13, which emerged around the 7th century BC and was one of the most influential of all. It is the philosophical partner of the yoga system. The tenet of the qualitative immutability held such an important place in the Causality system that its followers called themselves Satkirya-Ayadina, which derives from Satkirya-Aitsa, pre-existence of the effect in the cause. In contrast to the Nyayavise #Ka school, which held an emergentals view, the Causality asserted that it is not licit to speak of the birth of something but only of its manifestation, since nothing is qualitatively created or lost. 14. Whatever seems to arise had been latent and is freed from the state of cause by an agent acting from the outside. This view, which is sometimes regarded as a typical illustration of Eastern conservatism, has been the most conspicuous theory of change in the West since the end of the Greek classical period. 8.2.3 Conservative evolution. From Thomism to mechanism, a similar theory of change as the unfolding, growth, and manifestation of pre-existing potentialities under the influence of external causes, was held by Aristotle and worked out in detail by Muslim and Christian schoolmen. According to the peripatetic schools, change is nothing but the actualization of that which had always been there, though only in potency, that is, in a hidden, non-manifest way. 15 Hence whatever is in the effect must previously have been in some way in the cause. Quid quid est infectia debet esse prius aliquo modo in causa, the maxim so brilliantly ridiculed by James. 16 This scholastic aphorism, entailing as it does the assertion that change is nothing but the unrolling or unfolding of pre-existing potentialities, excludes flatly the emergence of authentic novelty. While asserting conservative evolution, it denies epigenesis, what Bergson called creative evolution. In particular, that theory of change excludes higher novelty, and consequently progress. Progress is indeed explicitly denied by another scholastic maxim, namely, the cause is higher than its effect. 17 Contemporary irrationalists, in their defense of the mysteriousness of emergence, often claim that the negation of the possibility of radical change is typical of modern science. Thus Bergson 18 held that science and, in general, intelligence, in contrast to intuition, does not grasp newness but regards everything as given, being solely interested in repetition. As we have seen, however, the doctrine that change is the mere unfolding of pre-existing capacities has remote origins, being in point of fact at least as old as the Bergsonian, and holistic, thesis that the emergence of novelty is basically unintelligible. A similar inability to account for novelty has been attributed this time rightly to mechanism. True, mechanistic philosophy does not grant the emergence of novelty but aims at leveling everything to the plane of mechanical actions and reactions. Remember Diderot's definition of that most intriguing type of matter: life is a succession of actions and reactions. To be born, to live, and to pass away, is to change forms. 19 But mechanist philosophers did not invent the theory of change without novelty. Mechanism just adopted, reinforced, and rationalized the picture of change as a circulation of a limited stock of forms, which is quite understandable, since the doctrine of conservative evolution satisfies both the scientific demand that providential arbitrary interventions be dispensed with from the moment the world machine has been created, and the dogma of creation without antecedents. Unlike Skolman, mechanist thinkers during the 17th and 18th centuries usually did not grant the deity the ability to create novelties after the sum total of qualities, which were but a few primary ones, had been built into matter. God, when acknowledged at all, was either an absentee landlord, as with most deists, or a mechanic repairing the cosmic machine from time to time, though only in a quantitative sense. For instance, by restoring the quantity of motion lost during non-elastic collisions, as Newton thought. Just as most schoolmen had asserted that the cause is higher than the effect, Descartes 20 maintained that the cause is higher than or equal to the effect, symbolically. C, E, and all the remaining mechanistic philosophers accepted, at least concerning natural affairs, the thesis of the exact equivalence between the cause and the effect. In fact, explicitly or not, mechanists rejected the progressive degradation required by most systems of theodicy and held the principle causae quod e dot fectum. This conservative principle once played a progressive role, now almost forgotten, because, among other reasons, it entailed the rejection of miracles. Its further positive features will be mentioned in Sector 8.2.6. But the price paid for such a rationalization of the world was, again, otherworldliness talk, certainly a very intellectual one. In fact, if the material universe was a self-running mechanical contrivance in which nothing new could emerge, the first origins of things necessitated a first, and almost always last, miracle. This was clearly realized by Newton. Blind metaphysical necessity, which is certainly the same always and everywhere, could produce no variety of things. All that diversity of natural things which we find suited to different times and places could arise from nothing but the ideas and will of a being necessarily existing. 21 Since the strict doctrine of causality rendered radical novelty impossible, the emergence of newness had to be either denied or assigned to that which, by definition, was absolutely autonomous, free, spontaneous, namely, spirit, with or without a capital. Some contemporary occultists, like Ouspensky, hold that the sole possible source of novelty is psychical free will, the foundation of magic. Orthodox holism, too, regards emergence as a sort of magical mystery beyond the scope of science. As to progress, which by definition involves the emergence of higher novelty out of previously existing levels of being, it was of course unaccountable in mechanical terms, since mechanism is essentially reductionistic. For mechanism, higher can only mean more complex, never qualitatively richer. 8.2.4 Qualitative immutability and causation in Kantianism. Essentially the same qualitatively unchangeable picture of the universe Kantian has explained. According to the critical philosophy, despite all phenomenal changes the world remains essentially the same. The cause is just the form taken previously by the effect, and the effect is the form that the cause takes. The true meaning of the causal law is, then, that there is nothing new in the world, and so far, essential acquisitions of modern physics, in the first place the principle of conservation of energy, and the law of conservation of electric charge, must be regarded as expressions of the causal law. 23 The Kantian view that causation brings forth no novelty seems to have been introduced in Britain by William Hamilton, according to whom the whole meaning of the intellectual phenomenon of causality is that all that now is seen to arise under a new appearance, had previously an existence under a prior form. There is thus conceived an absolute tautology between the effect and its cause. \ve think the causes to contain all that is contained in the effect to contain nothing which was not contained in the causes. Point 24. According to this conception, then, change is ultimately reduced to permanence, and variety to identity. A causal picture of the universe is asserted, which need not be wholly static but which is at most periodic, since it allows only for repetitions. Change is granted only to show how similar the present is to the past. As the French saying goes, plus va change plus si est la même chose. The more it changes, the more it is the same thing. 25. Such is the poor result of the elaborate Kantian play with categories, antinomies, and analogies from experience, a wrong archaic solution of the central problem of ontology, namely, the rational and verifiable explanation of the possibility of newness. 8.2.5. General lawfulness accounts for the novelty excluded by causalism. The poor picture of becoming held in various ways by the Psieudekia, by scholasticism and by mechanism, and adopted by Kant, began to change towards the end of the 18th century under the pressure of two movements that were otherwise largely antagonistic, namely, Romantic philosophy and science. Natural science discovered non-mechanical patterns of change, notably biological evolution, and some of the Romantic philosophers, particularly Hegel, elaborated certainly in a fantastic and mostly unintelligible way the dialectical theory of change, the nucleus of which is the hypothesis according to which radical change is brought about by the tension and final synthesis of opposite trends. From that time on, it is less and less disputed among scientists that there is no such thing as an equality sign between every cause and its corresponding effect, that sometimes there may be less, as Aquinas thought, but at crucial points there may be more in the effect than in the cause. Genuine novelty, unexplainable on strict causalism, is understandable at least in principle with the help of the totality of categories of determination, not excluding causation. The scientific description, explanation, and prediction of change, whether quantitative or qualitative, is performed with the help of law statements, see chapters 10 to I2. Among laws there are those with a strong causal component, like Newton's law of motion, and laws of emergence, like those of the formation of molecules out of atoms. Now, if the emergence of an isolated new property, new, of course, in a given context, need not entail the correlative emergence of new laws, what about the emergence of entire systems of new qualities? It seems that such a basic change does bring with it a change in the laws or, if preferred, the addition of new laws, as is the case with the laws of social behavior with regard to those of life. Such a newness in the laws, of nature or of society, which seems to accompany the emergence of a new integrative level is, of course, relative to the given context. The emergent laws need not be entirely and absolutely new, that is, new regardless of contexts, they merely have to be new with regard to the laws followed by the object concerned, which evolves to the point where the new modes of behavior appear. A few such emergence of new systems of qualities, presumably accompanied by the emergence of new laws, may have occurred and may occur in the future for the first time in the history of the universe as presumably the levels of life, thought, and social organization occurred. In any case, whether original or just relative novelty is at stake, the appearance of entities characterized by entire sets of new properties, that is, the emergence of a new level of being, seems to involve changes in the laws of the mode of being and becoming of such entities since, after all, laws are patterns of being and becoming, and such as relate qualities. Consider the laws of chemical binding, we know that they do not find any application outside a certain temperature range. Thus, before any experiment performed on the spot, we are pretty sure that no chemical reaction takes place in the inside of the known stars, on account of their high temperature. But as soon as a bit of matter in the stellar atmosphere cools down to the point where chemical reactions become possible, at such a critical point a radical change in the system of qualities characterizing the bit of matter in question may occur. The very laws of nature may change in it, at least in the sense that new laws, new relative to the ones that had been working in that bit of matter till the change concerned, may emerge from the old laws, or if a mechanistic way of speaking is preferred, new laws will be added to the former laws. To be more specific, in a mass of matter nothing but mechanical, thermodynamic, and electrodynamic changes will occur within a certain temperature range. But beyond a critical temperature the laws of thermonuclear phenomena may begin to operate, and below another critical temperature chemical laws may begin to work. This has an important consequence for the theory of causation, namely, that causal connections should not be isolated from the set of associated laws, or, if preferred, a causal law will obtain provided the remaining relevant laws do not change. For, if the background laws do change, then the same cause C may no longer produce the same effect E, that is, under changed conditions the connection between C and E may be altered. Thus, an electric discharge will produce a set of physical phenomena E within a certain temperature range, but if the temperature is conveniently raised or lowered, the same discharge may elicit a chemical result E, emergence of molecules out of atoms. Even mere changes in the reference system may produce qualitative changes. Think of the classical magnetic field of a charged body in motion. It simply does not exist in the charge's own reference system, although it does exist in systems in motion relative to the charge concerned. Such a qualitative change does not require any change in the laws of the variable phenomena. Moreover, the laws are assumed to be independent of the reference system, principle of covariance of the laws of causality and novelty nature, but the solutions of the corresponding equations do depend on the reference system, and it is precisely the solutions that are correlated to the phenomena. In other words, the uniformity of nature does not apply to the phenomena, which are relative, but to the laws of phenomena, which are absolute, or, if preferred, while it is usually assumed that place and time are irrelevant to the laws of nature, it is known that events are relative to their space-time context. There might be a further way in which phenomena could vary while keeping the laws unchanged, namely, if some of the so-called fundamental constants of nature, the gravitational constant, the velocity of light in vacuum, Planck's constant, and others, were to change in time. If this were the case and there is no a priori ground for rejecting this possibility, physical laws would remain constant, but phenomena would change in time. Consequently we would no longer be entitled to assert that if C happens then E will alocus be produced by it / but we would have to add a qualification concerning the time range within which such a regularity is approximately found to obtain. 26. We may, in Briot, account for novelty without adopting James's perceptual view of causation. The rejection of causality, or, rather, the realization of its limited scope, need not lead us to admit the emergence of novelty out of nothing and to bow before it with natural piety, as the upholders of emergent evolution advise us to do. 27. Science is engaged in disclosing the specific ways of emergence of newness in the various sections of reality, as well as in investigating the appearance of whole new sections of reality, levels. And the central problem of a scientifically grounded ontology may be regarded as that of inferring from science the most general ways of qualitative change, a task that may eventually lead to suggesting the search for further forms of emergence. 8.2.6 Positive features of the invariancy asserted by causality. The positive features of the principle causa quod ejectum should, however, not be missed. One of them concerns quantitative invariance, another immutability, and a third identity of structure. The former restriction on change is true, hence positive, insofar as it states that there are constant quantities and relations amidst the ceaseless flux of phenomena. The insistence on qualitative invariance is positive to the extent to which it warns us not to expect novelties of a radical kind at every step, newness being the exception rather than the rule. Finally, the contention that the cause and the effect are structurally identical may be regarded as one of the principles of scientific inference, or, rather, as one of the ontological principles underlying scientific inference. Let us deal separately with the three interpretations of causa quod effidem. The equality of causes and effects has been interpreted, from Aristotle down to our own time, as synonymous with lawfulness. Thus, when the philosopher defined the force as the cause of motion, he established a constant relation between a cause, force, and its effect, velocity. In modern terms, Aristotle's law of motion reads F equals RV, where F symbolizes the force, R the resistance to motion, and V the velocity. See Sector 4.4.3. 2 millennia afterwards, Leibniz 28 made an explicit use of the principle of the equality of the cause and the effect, in order to demonstrate what we now call the theorem of conservation of mechanical energy. By adding to that philosophical principle the definitions cause equals force, and force equals living force, twice the kinetic energy, he is able to demonstrate his laws of motion and, what is more important, feels himself entitled to set forth his hypothesis of conservation of force, energy. 1.5 centuries later, Julius Robert Meyer reasoned in a similar way when trying to demonstrate a priori the principle of conservation of energy, which he called force, as was then usual. The kernel of his, partially wrong, reasoning, or, rather, of his own ulterior reconstruction, was the following. Forces are causes, accordingly, we may in relation to them make full application of the principle causality quod E. Fectum. If the cause C has the effect E, then C equals E. If, in its turn, E is the cause of a second effect J, we have E equals J, and so on. C equals E equals F equals C. In a chain of causes and effects, a term or a part of a term can never, as plainly appears from the nature of an equation, become equal to nothing. This first property of all causes we call their indestructibility. 29. In other words, the main property of causes is their conservation. Now, forces are causes, which is true as long as the term force does not designate energy, hence forces are conserved, which is true provided the term force does designate energy. Very likely this was not Mayer's original train of thought, but when writing it down he found it convenient to rely on the supposed authority of the causal principle, in the narrowest of its formulations. Moreover, Meyer went so far as to claim that his own discovery was but a consequence of the causal principle 3D, as if qualities could be causally connected with one another. In short, whether understood as asserting quantitative constancy, or numerical equivalence, or proportionality, the principle causality quod E. Fectum has often played a constructive role, or at least it has helped in disguising scientific novelty under a respectable appearance. The reason for that is simple. The maxim can be interpreted as affording a precise quantitative expression of the causal nexus. A more neutral and powerful principle, that of lawfulness, has nowadays taken the place of the hypothesis of the quantitative invariance of causes and effects. Invariant relations have replaced unchanging events. As to the qualitative invariability entailed by the principle causality quod E. Fectum, an invariance which Meyer rightly rejected, 31. Its positive content is the following. In the first place, although causalism may produce in us a bias against novelty, it warns us not to be deluded by apparent novelty, and this is in most cases a sound rule, for genuine novelty is infrequent. As Milne Edwards said, nature is prodigal in variety but niggard in innovation. 32. Secondly, to say causality quod E. Fectum amounts to saying, for instance, that flies, not dogs or TV sets, nor even new species of insects, will come out of flies. It definitely rules out the possibility of transformation of this animal genus, which is also correct to a first approximation, since such things do not happen daily. The qualitative immutability asserted by causalism means that one cannot expect to obtain, from a given set of causes, whatever effect one's fancy invents, but only those effects that the given conditions can possibly bring out. So far, this is included in the general principle according to which nothing is produced ex nihilo and in arbitrary ways, which we regarded as the essence of general determinism, see Sector 1.5. Not only pantheism but also miracles are thereby ruled out. A third meaning which the maxim causality quod E. Fectum may be assigned is that of structural invariance. This is, indeed, one of the many ways in which Russell has understood the causal link. Let us hear him. Take, say, broadcasting, a man speaks, and his speech is a certain structure of sounds, the sounds are followed by events in the microphone which are presumably not sounds. These, in turn, are followed by electromagnetic waves, and these, in their turn, are transformed back into sounds, which, by a masterpiece of ingenuity, are closely similar to those emitted by the speaker. The intermediate links in this causal chain, however, do not, so far as we know, resemble the sounds emitted by the speaker except in structure. It appears generally that, if A and B are two complex structures and A can cause B, then there must be some degree of identity of structure between A and B. 33. If bionic correspondence is regarded as a defining mark of the causal connection, see Sector 2.4. Then the last statement is tautologous, because structural similarity is nothing but bionic correspondence, that is, coordination of sets of elements of arbitrary kinds. Even so, Russell's is a useful statement, so far as it emphasizes that the causal principle does not involve quantitative or qualitative invariance, but just the identity of structure between the effect and its cause. It is only causalism that leaves no room for novelty. 8.3. Summary and conclusions. In summary, strict causalism may account for novelty in number and in quantity alone, by declaring that actuals are either the mere manifestation or the quantitative development of possibles. Causalism definitely excludes qualitative novelty. We are thus faced with the strange fact that the doctrine of causality, which is supposed to account for change, ends up by denying radical change, that is, that variety of change involving the emergence of new qualities. This paradox led Meyerson, who granted the possibility of novelty but saw no other form of determinism than its causal variety, to the conclusion that science leaves always an irrational remainder. 34. The same paradox has led others to fancy that novelty either is impossible or shows the failure of determinism, which would be right if causalism exhausted determinism. Novelty is not the insoluble caput mortuum imagined by irrationalism, it is explainable, but with the help of all the categories of determination. Moreover, the causal principle can be helpful in the detection of the very novelty causalism denies. In fact, whenever the principle same causes same effects does not seem to be fulfilled, we tend to assume that the cause has not been the same in all cases, that is, that something new crept in unnoticed. As Bernard said, given a natural phenomenon, whatever it may be, an experimenter should never admit that there is a variation in the expression of that phenomenon, without at the same time new conditions appearing in its manifestation. 35. That is, just because causalism is insufficient to explain novelty, it affords a criterion for disclosing the emergence of newness, namely, the failure of causal laws. The same holds for every conservation law. Whenever such a law seems to fail, we are led to assume either that the concrete object in question is not as isolated as it was supposed to be, or that something new has emerged. This is the type of inference we perform when we find something missing at home, or when we assume the emission of a neutrino. In either case a new entity, burglar, neutrino, is assumed to exist, which restores conservation of something, property, energy. But if the doctrine of causality is too narrow to account for every sort of change, on the other hand the causal principle is consistent with radical change, and causation itself seems to take part in the emergence of every novelty. Ideal schemes of change may be purely causal, purely random, purely self-determined, and so on. Real changes, on the other hand, are always a mixture or, better, a combination of several types of becoming. Their description should consequently include various categories of determination, if only because real changes happen to many-sided objects that bear a number of connections with other objects. Causal bonds may not constitute the main connections in all cases, they may even be irrelevant to a given transformation, but it seems safe to assume that they somehow have a share in actual change. In short, causation participates in the production of novelty although it does not exhaust it, and, although causalism is a conservative doctrine, the principle of causation is consistent with the emergence of newness. This is why the causal principle has a place in science, though not to the exclusion of other principles of determination. To find that place will be the concern of the remaining investigatiosophical principle in scientific research. Should it turn out that the principle does play a role, our conclusion would support the general thesis that philosophy neither towers above science nor stands at its basis, but is instead part of the very stuff of scientific research. Before such analysis is begun, it will be convenient to make it clear what is here meant by scientific knowledge, or science, which is in turn a province of rational knowledge. In German-speaking countries, every serious, but not necessarily meaningful, coherent, and verifiable, discourse is entitled to be labeled scientific. Thus, for instance, Husserl described phenomenology as strenge Wissenschaft, rigorous science. In other languages of the European continent, on the other hand, every discipline making verifiable statements or at least striving to make them, whether requiring empirical confirmation, like those of biology, or not, like those of mathematics, is usually called a science. Finally, in English we find the paradox that mathematics and logic, though both admittedly scientific in the highest degree, are not usually included in science. Indeed, in that language the word science ordinarily covers the study of nature, spiritual activity, and society, to the exclusion of the disciplines dealing with the forms of thought. Sometimes the term empirical science is employed to denote all sciences in which observation or experiment or both play a decisive part. 223. 224. But this 10 is not convenient because factual sciences are not more empirical than rational, and because it seems to entail a commitment to empiricist philosophy. Although the English nomenclature is not entirely satisfactory, it will be adopted in what follows, that is, we shall include under science any discourse that is both rational, meaningful and coherent, and at least partly empirically confirmable though not necessarily demonstrated, that is, not necessarily true with a high probability. 9.1. Is causality characteristic of modern science? According to a rather popular belief, causality typifies modern science from its beginning till the birth of quantum mechanics, that is, roughly from the middle of the 16th century to our day. But most philosophers, and some scientists, know that the causal principle has survived the birth of the quantum theory, see Sector 1.2.5, and that causal thought is much older than modern science. Explanation by causes is, indeed, as old as the phenomenological description of sheer time sequences. Moreover, the reduction of determination to causation is found in rather backward stages of knowledge, though probably not in the most primitive of all. Thus, the Trobriand islanders are said to lack words to denote causation. It seems, in fact, characteristic of primitive mentality, one at least at a certain stage of its evolution, to assign a cause to everything that is, begins to be, or passes away, and, particularly, to invent myths for explaining causally the origin of what we now regard as self-existent, unengendered, uncaused, namely, the universe as a whole. Thus many cosmogonies, whether religious or not, besides fulfilling a social function, satisfy the urge for causal explanations. A second typical characteristic of primitive mentality is the ignorance of chance, the refusal to believe in mere conjunctions and fortuitous coincidences, and the complementary belief that all events are causally connected, whether in an overt or in a hidden, magical, way. This belief in the universal causal interconnection, a belief probably born in prehistoric times, was adopted in antiquity by Stoicism and is nowadays held by the continuers of prehistoric thought. Too admittedly, it is a far cry from the primitive to the modern stage of causal thought. Neither primitive nor archaic, pre-classic, thought had our view of an impersonal, lawful, and in principle controllable causation. 3. Causal thought, chimerical in most cases but often correct when it was a question of survival, had been one of the first ways of explaining becoming and even being. By requiring a ground for every existent, causal thought has prompted the search for objective connections. On the other hand, by being unable to conceive that something may exist per se, on its own account, without having been created, and by exaggerating the connectedness of the world, causal thought has also stimulated the elaboration of mythical and religious worldviews, quite apart from their well-known social roots. Causal thought was codified by Aristotle, see Sector 2.1. But, unlike primitives and children, who ignore chance, the Stagirite admitted it both at the ontic and at the epistemological levels, that is, both as objective contingency and as a name for our ignorance of the real causes. Only, he refused to admit chance as an object of scientific knowledge, since by definition we cannot know the truth apart from the cause. For every object, with the sole exception of the unmoved mover, exists and eventually changes in virtue of causes of several kinds, nothing but the first cause is self-caused. The causal teaching of Aristotle was revived and worked out by the best of scholastics, one of whose watchwords was "Sire per causes to know by causes." The scholastic period was the golden age of causality, everything was then assigned a cause, and even chimeras were explained in causal terms in every detail. Conoscere causes rerum, to know the causes of things, notwithstanding that it is the motto of modern institutions of learning, is not a mark of modernity but rather a mark of a peripatetic outlook and, indeed, a mark of Christian philosophy in both its Aristotelian and its Platonic trends. What is characteristic of modern science, in connection with causality, is rather, a. the restriction of causation to natural causation, naturalism, b. the further restriction of all varieties of natural causation to efficient causation, c. the endeavor to reduce efficient causes to physical ones, mechanism, d. the requirement of testing causal hypotheses by means of repeated observations and, whenever possible, through reproduction in controllable experiments, e. an extreme cautiousness in the assignment of causes and a ceaseless striving toward the minimization of the number of allegedly ultimate natural causes, parsimony, f. the focusing on the search for laws, whether causal or not, g. the mathematical translation of causal connections. Even so, the first characteristic, that is, the restriction of causes to natural factors, although practiced by many scientists in antiquity, was not firmly established until the 18th century. Before that, supernatural causes, as well as reasons, were admitted among causal determinants. 9.2. Cause and reason. The principle "there is a reason for everything" has usually been regarded as the epistemological partner of the ontological principle according to which everything has a cause. Moreover, the two have been welded for thousands of years. The identity of explanation with the disclosing of causes is even rooted in the Greek language, in which ation and logos are almost interchangeable, since both mean cause and reason. The confusion of cause with reason, and that of effect with consequent, are, moreover, common in our own everyday speech. The identity of reason and cause was consecrated by Aristotle, to whom we owe the distinction between demonstrative, or empirical, and explanatory, or theoretical, disciplines. The former he held in lower esteem than the latter, which he regarded as pointing out the causes of things. Those who know by experience know only the how of things, the scholasticia, whereas those who possess the art attain the understanding of the why, the proterquid of the schools. And men do not think that they know a thing till they have grasped the why of it, which is to grasp its primary cause. 6. In the case of the Stagirite, this identification of cause and reason was not a mere confusion, although it may have been influenced by language. It was, I believe, an instance of his deliberate identification of logic and ontology, an identity that is still blocking the understanding of both. A similar identification of reason and cause, and consequently of explanation with causal explanation, was taken for granted by most peripatetic schoolmen. Albertus Magnus was among the very few who distinguished the physical causa from the logical ratio. This shows, once again, that the identity of explanation and causal explanation is far from being peculiar to modern science, the moral being that we need not fear being called unscientific whenever we resort to non-causal explanations. The 17th century rationalists adopted the traditional identity of cause and reason, but they inverted the terms. Causes were now reasons and, most often, reasons were of a mathematical kind. A mathematical proposition, not a physical agent, was regarded as the sufficient or determinant reason, not only of another idea but of material facts as well, as if things and ideas were on the same level or as if the former hung from the latter. This reduction of causal explanation to rational explanation was typical of Kepler, at any rate of the young Kepler, who took no empirical fact for granted but, in a characteristically rationalist and Renaissance mood, tried to explain why the then known planets were just 6. He did it, as is well known, in terms of the 5 regular polyhedrons and the spheres containing them. To young Kepler, the ultimate cause of things is some mathematical harmony. As Bert explains, Kepler thinks that he has reached a new conception of causality, that is, he thinks the underlying mathematical harmony discoverable in the observed facts as the cause, the latter, the reason, as he usually puts it, why they are as they are. 7. That rational explanations of this sort are in a sense the very opposite of causal explanations in terms of physical agents could not, of course, be realized by any rationalist who believed that nature is mathematically built, whence the use of mathematics, more than a mere practical convenience, as pragmatism holds, and much more than the sole adequate language of natural science, conveys the very essence of things. 4. As Galileo put it in well-known words, the book of nature is written in the language of mathematics. 8. The conviction that a mathematical object not only may be helpful in the description and explanation of nature but is in a sense the cause of it, or even that the fact consists in a given mathematical structure, is not a relic of past. It can be found, for example, among those physicists who assert that the quantum properties of matter consist in, or follow from, the non-commutative multiplication of certain operators. 9.3. Causation and the principle of sufficient reason. No wonder, therefore, that to orthodox rationalism, whether medieval, Renaissance, or contemporary, the principle of causality is analytic and, moreover, has to be stated in the phone of the principle of sufficient reason. According to the latter, which was Leibniz's pride and joy, nothing happens without a sufficient reason. 9. This proposition has actually been regarded as a ground of being, as a principium essendi, and not only as a principle of becoming or principium findi. In point of fact, a strict rationalist should require that a reason be given not only for that which begins to be or ceases to be, but also for every existent, including the sum total of existence, for there can be found no fact that is true or existent, or any true proposition, without there being a sufficient reason for its being so and not otherwise, although we cannot know these reasons in most cases. Point 10. But the confusion of the causal principle, which has an ontological status, with the principle of sufficient reason, which is an epistemological rule of procedure, although it has often been counted among the principles of logic, is not the monopoly of rationalists. This confusion of cause and reason is not peculiar to Kepler, Spinoza, or Leibniz. It has also been indulged in by some empiricists too, which should not be too surprising in the context of a doctrine holding that causation belongs to the sphere of the experiencing and knowing subject. Ot, as the case may be, deliberate identification parallels the confusion of material reality with its reconstruction in thought. It has suggested the doctrine of pre-established harmony between reason and reality, and it has fostered the notion that the result is contained in the cause in the same way as the consequence of a ratiocination is logically entailed by its premises, whence nothing new can emerge in the world unless novelty is injected from outside the world itself. The confusion of cause and reason in favor of the latter was useful for science as long as it rested on an unbounded faith in the rationalizable, intelligible structure of reality, and on confidence in the power of reason to disclose it. Moreover, in the beginnings of modern science this confusion carried with it a great enlargement of the scope of scientific research. Indeed, since looking for the causes of things was interpreted as advancing reasons and, whenever possible, reasons of a mathematical kind, instead of looking for one-sided cause-effect bonds among separate events, instead of searching for the ultimate, hidden causes of phenomena, and of formulating integral laws with the schematism required by the narrow frame of causality, and, above all, instead of inventing fictitious causes in order to comply with causalism, modern science began to frame all sorts of reasons, establishing all kinds of connections, whether among coexistents or successive qualities of the same object, or among aspects of different objects. It was fortunate for science that Kepler and Descartes should regard rational, and, particularly, mathematical, explanation as ultimate, and that Galileo regarded it as indispensable. But rational explanation in terms of mathematical propositions could not satisfy physicists forever. It did not satisfy Galileo, who, besides mathematical reasons, sought, without finding them, the hidden physical causes, which he identified with mechanical forces. It did not satisfy Hobbes either, who tried without success to combine ancient atomism with Galileo's mechanics. And it did not satisfy Newton. Moreover, Newton was the first who succeeded in setting forth a logical, as contrasted to a rational, explanation of the motion of bodies, and in framing it in the language of mathematics. The rationalist. Causality and rational knowledge program advanced by Descartes and consisting in the derivation of all physical phenomena from self-evident mathematical principles 12 was, in fact, definitely turned upside down by Newton, who, in opposition to the Cartesians, though without mentioning them explicitly, asserted that whatever is not deduced from the phenomena is to be called an hypothesis, and hypotheses, whether metaphysical or physical, whether of occult qualities or mechanical, have no place in experimental philosophy. In this philosophy particular propositions are inferred from the phenomena, and afterwards rendered general by induction. 13 From that time on science has been explaining the world around and inside us with increasing success, especially to the extent to which determinism has unawares been enriched with the addition of new, non-causal types of scientific law. Modern science has, at least in this respect, complied with Bacon's requirement 14 of disclosing not so much the causes of things as their laws, something that cannot be understood if the identity of cause and reason is retained. The principle of sufficient reason is extensively used in all fields of knowledge, though only exceptionally as synonymous with the causal principle. Giving reasons is no longer regarded as assigning causes. In science, it means to combine particular propositions about facts with hypotheses, laws, axioms, and definitions, some of which may but need not involve the cause concept. In general, there is no correspondence between sufficient reason and causation. It suffices to recall that mathematics, which does employ the principle of sufficient reason, remains outside the scope of the causal principle, which has an ontological status. Consequently, the principle of sufficient reason cannot be regarded, as it usually is, as the mental aspect of causality. 15 And, generally, scientific knowledge does not consist in a mere reflection of material reality, but in a real reconstruction employing materials, images, concepts, ideas, ratiocinations, of its own, obeying laws of their own, those of formal and inductive logic, and often lacking a factual, empirical or material, correlate. 9.4 Limits of the principle of sufficient reason in connection with theoretical systems 9+I. Should everything be rationalized? One of the most amusing shows provided by rationalism was Christian Wolff's attempt to demonstrate the principle of sufficient reason, which attempt was, of course, grounded on the assumption of the validity of the very principle he tried to demonstrate. The principle in question has a wide field of application, but its range of validity is not the whole universe of scientific and philosophic discourse. First of all, it obviously cannot be applied to itself, but only as philosophical semantics teaches us to propositions belonging to a lower level of language. That not everything should or could be defined, explained, or demonstrated, in short, rationalized, in a given context or level, that some starting point is always required, was dimly perceived in antiquity by many philosophers and scientists, as is shown by the fact that they often developed their discourse starting from first principles that were either taken for granted as obvious or regarded as results of induction. Thus, for example, Leucippus and Democritus explained everything in terms of moving atoms, not simply atoms, nor solely motion, but ceaselessly moving ultimate particles of matter. Atoms were regarded by them as self-sufficient, ultimate, uncaused entities, which had been in motion from all time. 16. Some ancient atomists may have suspected that such atoms need not be explained, since they are the roots, rhizomata, or principles of things. Moreover, it is likely that some of them had even realized that atoms must not be explained, although they can of course be described, if they are to function as ultimate explainers of everything that is and that comes into being and goes out of being. Aristotle was not satisfied with this procedure, which he regarded as lazy. He asked about the cause of the atom's motion. 17, which he did not regard as self-evident. Only self-evident truths could be accepted as starting points according to Aristotle, which was obviously not the case with the propositions of the atomists. As a consequence, he did not grant atomic motion the status of a first principle, archaeotene or unengendered root. Neither Aristotle or his followers seem to have been aware of the logical necessity of admitting, in every context, a set of unexplained or primitive concepts and ideas in order to avoid reasoning in a circle. They did not regard first principles as hypotheses to be eventually justified a posteriori, and to be 234. Assumed because something must be granted in every discourse at the start, they regarded them as self-evident and undemonstrable verities that had to be received without dispute just because they were obviously true. 19. The methodological prescription of modern science, according to which every discourse shall start with a handful of notions among which some are either undefined, but become actually defined, explained, or at least made intelligible a posteriori, by the function they perform, or are defined in a different context. This prescription, I say, seems to have risen to consciousness not before the 17th century, and this in connection with mathematics exclusively and moreover in a few cases. I am thinking of Pascal, who was perhaps the first to realize that the penalty for not granting some undefined notions at the start is circular reasoning. 2. Even Leibniz, the most powerful logician of his time, wished to prove the axioms of Euclid's geometry. 21. It is no longer seriously disputed, I believe, that logical consistency requires the admission, in each theoretical context, of a set of notions that are primitive in it. Their meaning is clarified by the very function they perform in the given context, and their adequacy and fruitfulness can be judged from the consequences that are deduced from them. Finally, definitions, whether explicit or implicit, of terms, and demonstrations of primitive or undefined propositions, are sometimes afforded in other contexts. Reason, namely, the so-called principle of indifference, or principle of insufficient reason. According to Jacob Bernoulli, who formulated this celebrated rule, chance events can be said to be equally probable, for instance, pi equals p2 equals t, as in coin throwing, if we know of no reason why one of them should be expected in preference to the alternative events. Thus, in the case of a perfectly balanced coin, we may assume that the mutually exclusive alternatives head and tail are equally likely, because we have no ground or reason to expect the appearance of one of them rather than of the other. The principle of indifference, as it is also called, has often been regarded as an equitable distribution of ignorance among mutually exclusive alternatives. Besides, it is often thought to be a purely logical criterion for ascertaining a priori when events may be regarded as equally probable, and even as a logical definition of equal probability, enabling us to circumvent the circularity involved in Laplace's definition of probability in terms of equally probable events. Now, strictly speaking, the principle of indifference is not a principle of the calculus of probability but an assumption that is often made in its applications to specific situations, and that, far from being purely logical, formal, is usually supported by explicit or tacit symmetry considerations. That is to say, the hypothesis of equiprobability can often be grounded on, or explained in terms of, geometrical or physical symmetry properties. Consequently, it is not an ultimate explainer, an Urgrund. The principle of indifference is just a hypothesis to be confirmed or invalidated by its testable consequences. Thus, we cannot assess a priori the probability of casting an ace when throwing a real die by merely applying the principle of indifference. The estimate p equals I is valid for the ideal die, it is approximately true for a true, unbiased real die, but definitely wrong for a loaded die. Moreover, Such an estimate does not rely on a complete ignorance but on a definite knowledge of the symmetry properties of the cube, not to speak of our previous experience with dice throwing. Besides, the principle of indifference does not shrink the domain of validity of the principle of sufficient reason, although it may occasionally shift the range of its applicability. In point of fact, even admitting that the lack of any sufficient reason may lead us to conjecture equiprobability in some cases, this will not prevent us from asking, in a different theoretical context, why the alternatives concerned are equally probable, in case the hypothesis of equiprobability is actually confirmed. To say it in a paradoxical way, we can always ask for the sufficient reason why we have no sufficient reason to expect that a certain chance event will happen rather than another, equally probable, event. The answer to this question, asked on the ground of the principle of sufficient reason, belongs neither to logic nor to the mathematical theory of probability, but to the special science concerned with the class of events under consideration. Thus in statistical mechanics the ergodic theory is supposed to answer the question, why are microscopic configurations equally probable in the equilibrium state? Analogously, the method of arbitrary functions applied to an ideal model of roulette enables us to deduce the equiprobability of blacks and reds. 22. In other words, what is taken as a primitive in a given context, for example, equiprobability in the applications of the probability calculus, may turn out to be derived in a further context. In short, the principle of sufficient reason is limited in every theoretical domain by the need of avoiding circularity, but most such limitations disappear if the entire field of relevant rational knowledge is taken into account. But what about matters of fact? Are we to stop here, too, at a certain critical point, are asking questions about sufficient or determinate reasons? 9.5. Limits of the principle of sufficient reason in connection with matters of fact in modern physics. The following question has been asked: why are the values of empirical constants what they are? And, in particular, what is the reason for the values of the so-called fundamental constants, like the gravitational constant 22 C. Poincare, 1912, CLL/QE de probabilis, 2nd ed., pages 148 it. Causality and rational knowledge 237 and the velocity of light in a vacuum. Bridgman, in a curious rationalistic slip, entertained the hope that someday we may be able to give some sort of account of the numerical magnitude of these constants. 23 Other outstanding physicists have wondered about the particular numerical value of the so-called fine structure constant, a dimensionless number, A equals 27 TE2JHC, relating Planck's constant h with the basic electromagnetic constants c, the speed of light, and e, the electronic charge. Some have gone so far in their Pythagorean faith as to believe that the explanation, theoretical determination, of this number might be the key for solving the riddles of the quantum theory, being consequently the most important of the unsolved problems of modern physics. 24 The search for an explanation of the fine structure constant has resulted in a large number of papers out of which nothing seems to have come as could not be otherwise, since there does not seem to exist a clear idea of what is meant by explaining the so-called fundamental constants or their various dimensionless combinations. It might be that the failure is just due to the failure to point out what sort of reason would be regarded as sufficient in this case. But it might also be that this happens to be a pseudo-problem, there being nothing to be further explained or understood about fundamental constants apart from an eventual derivation of such constants from other constants, to which fundamentalness has been shifted. Besides, it is not altogether true that empirical constants, such as the mass and charge of the electron, mean nothing to us because we have to read them from experiment, as is sometimes stated. That would be so if the values of the mass and charge of the electron were entirely 238 isolated pieces of information, but they mean something to us just because they fit into the whole framework of experimental and theoretical electron physics, and they fit so tightly that their values can be obtained in a number of seemingly disconnected ways. To turn to more general factual questions, it should be pointed out that there are certain basic principles concerning material reality whose admission qua starting points not only does not entail any irrationality but enables us to avoid a lot of nonsense. Thus the principle that matter in motion, and the universe as a whole, are self-existent, uncaused, or causes of themselves rules out in a radical manner the validity of inquiries into the sufficient reason for the existence of moving matter, which inquiries usually transcend the boundaries of rational knowledge. Moreover, if the principle is granted that the universe is uncaused, and that matter is self-existent, then the existence of the material world, rather than having to be justified by human reason, becomes the very possibility for affording the sufficient reason, or, rather, the determining ground, of other things, among them, of reason itself. The admission of this axiom dispenses us from performing the impossible task of explaining the existence of the sum total of existence, a task that is thereby rendered an apparent question. It does not dispense us, however, from the duty of explaining the changes in the world or the existence of the various parts of it which can be explained, at least in principle, as the outcome of processes. Thereby the old and odd question, why is there something rather than nothing, which has haunted so many thinkers 25 and existentialists 26, becomes deprived of every sufficient reason. Causality and rational knowledge 239. In brief, the unrestricted application of the principle of sufficient reason, both in theoretical and in factual questions, may lead to the very destruction of reason. 9.6. On the formalization of causal statements. 9.6. Illogical equivalence, or logical correlates of the causal connection. If there is some truth in what has been said in the preceding sections, textbooks on logic are not the proper place to deal with the Caus.al problem nor with any other ontological question. The reason for this is that the causal connection is not a logical relation, that is, it is not an abstract relation of the type X-ray among abstract objects. The causal problem is an ontological, not a logical, question, for it is supposed to refer to a trait of reality, and consequently cannot be settled a priori by purely logical means. It can be analyzed with the help of logic, but cannot be reduced to logical terms. 27. An elementary proof that the causal problem does not belong to logic is that laws of nature, whether causal or not, are by no means logically necessary. They are not the sole conceivable ones, and they are not necessitated by the laws of logic. In other words, the law statements are contingent truths, in Leibniz's sense of the term, because they lack the certainty that is supposed to characterize analytic statements, necessary truths. This does not mean, of course, that the laws themselves, the objective patterns of being and becoming, are contingent. The assignment of contingency to the laws of nature is often nothing but a consequence of their mistaken interpretation as factual singular truths. Nor does it mean that the establishment of law statements is a purely empirical matter. Some laws of nature have indeed been deduced theoretically, but always on the ground of empirical knowledge, however scanty it might be. Moreover, the objective validity of such theoretical results cannot be ascertained by purely logical means. Only experiment can help to decide, though never irrevocably, about their condition as natural laws. Conversely, what is logically possible need not be causally possible. Thus, it is logically possible for something to emerge out of nothing, in particular, to be non-caused. In other words, no rule of logic prevents us from conceiving of such a possibility, even though it contradicts the known laws of nature. Thus, nothing is easier than framing non-conservation, that is, creation, hypotheses, like 0 ox #0, contradicting the principle of productivity. It is only theoretical reflection upon experimental data, and not pure reason, that suggests putting OTIV/ox equals 0 instead of the previous inequality. Again, it is logically possible for the whole world to cease existing, thereby frustrating all causes, but this conceptual possibility not only contradicts the known laws of nature but is unverifiable, that is, it is not a scientific hypothesis. The fact that the causal problem is of an ontological nature is not inconsistent with its having both a logical and an epistemological aspect, as every other philosophical problem does. The causal problem is an ontological question because it refers to a pervasive trait of reality that, rightly or wrongly, is often supposed to appear on all levels of the material and the cultural world, with the exception of the level of abstract objects, that is, the question itself is an ontological one, because its referent belongs to the ontal sphere. But, like every other philosophic and scientific question, the causal problem raises epistemological problems, exemplified by the question of the verification of the causal principle, and logical problems. The logical side of the causal problem essentially consists in the logical structure of the propositions by means of which causal statements are formulated. Thus the logician is interested in studying the sentence if C then E always, by abstracting from the nature of the entities designated by C and E, as well as from the specific character of the connection between C and E. He will probably say that, from the point of view of logic, the sentence can be regarded in any of the following alternative ways: a. As a relation of material implication PCPE among propositions, b. As an inclusion relation CCE among classes, c. As a dyadic relation X-re among members X and Y of the classes C and E. In either case, the logician will divest the statement of its eventual ontological meaning, transforming it into a logical form, a form shared by an unlimited number of statements. And this is just what formal logicians are supposed to do, namely, disclose the most general forms, by dispensing with the contents. Something similar will happen, a fortiori, with the eventual formalization of the more complex sentence if C happens, then E is always produced by it, which we have regarded as an adequate formulation of the causal principle, CC's 2.5 ff. Any process of formalization would turn this synthetic statement into a non-causal statement, which, however, would be a logical correlate or transcription of it. It should not be expected, therefore, that the formalization of the propositions expressing ontological statements, such as the law of causation, will ever exhaust their content or meaning. It is not the business of formal logic to lift the veils hiding the face of the world, but rather to sharpen the rational tools with whose help such a task is performed by the sciences. On the other hand, it is, of course, perfectly legitimate and interesting to inquire about the adequate logical correlates of the various verbal statements of the causal principle, as well as of the combinations of causal statements. I speak of logical correlates rather than of logical equivalents, implying that causation is a form of generation or production, and that statements, contrary to their physical marks, such as spoken sentences, cannot produce anything, so that they cannot stand in a causal relation to one another. This problem of the formalization of causal statements has, of course, been approached, but, so far as I know, with no particular success. Let us take a glance at the difficulties besetting this task, too often hindered by the confusion of logical relation with factual connection, as well as by the Humean tenet that there are no factual connections. 9.6.2 Causation and implication, material, strict, and causal. The relational approach consider the conditional if P, then Q, which is often, and erroneously, regarded as the essential scheme of the correct formalization of the causal principle. In the calculus of propositions, the material implication P:(Q), sometimes also symbolized in the form P' plus Q, is usually regarded as the adequate formalization of the sentence if, then Q, P, and Q being propositions. But the logical connective : is far from representing the causal connection at the level of logic. In fact, there is general consensus that the logical correlate of the causal connection is logical entailment, or the relation of premise to conclusion, that is, the projection of causation on the logical plane is deduction, which does not mean that causation is a logical category, or that deducibility is an ontological category. Now, contrary to logical entailment or deducibility, Carnap's L implication, the sense of P:(Q) is not that, given P, Q will unambiguously jacalo from it. 28 In fact, in the first place, a true proposition Q is implied by any proposition P, whether true or false. Particularly, anything follows from a false proposition, ex falso sequitur quod labet, P:(Q). If the antecedent P were interpreted as the cause and the consequent Q as the effect, this theorem would roughly read: a cause, if absent, entails any effect. Secondly, every proposition implies itself, P:. P. Interpreted in causal terms, this could be taken as meaning anything is self-caused. On the other hand, the causal connection is essentially non-reflexive, nothing being self-caused according to causalism. Thirdly, the relation of implication need not be irreversible or asymmetrical. On the other hand, the cause-effect link is essentially asymmetrical. The lack of uniqueness, irreflexivity, and asymmetry characterizing material implication renders this logical connective a very inadequate logical transcription or correlate of the cause-effect link. In ordinary language, one says that Q follows from P and Q is deducible from P in an unambiguous, unique way. We also say that P entails Q, or that P implies Q, though not in the above-mentioned technical acceptation of the word implication. As far back as 1912, c. 1. Lewis suggested restoring the correspondence between the ordinary and the technical meanings of implication. To this end, he introduced a new notion of logical implication, to wit, true or strict implication, P:. 5tq, which is read: it is not possible that both P and Q be true. 29. That is, strict implication among propositions holds whenever Q is uniquely deducible from P. However, strict implication has not solved the paradoxes of material implication. 30. And has moreover paradoxes of its own. It does not entirely overlap with deducibility, whence it cannot be regarded as the adequate logical correlate of the causal bond. A third kind of implication has been put forward in an attempt to build a closer logical correlate of causation, namely, the causal implication 31 of propositions, symbolized by PCQ, or, in an analyzed form, X, XCDX. This pioneer work is valuable, if only because it is not an exclusively extensional approach. However, it is written by paradoxes and it is open to technical criticism. 32. Besides, the following objections can be raised against it. A. It seems to establish, by convention, the rationalistic tenet that every logically necessary statement is causally necessary. B. Causal implication seems to refer to all types of bionic connections, whether involving a genetic relation or not, hence it does not account for what is peculiarly causal. No satisfactory logical correlate of the causal nexus seems so far to have been proposed, but work is being continued in this field. 33. In my opinion, an adequate verbal formulation of the causal connection, on which there is no consensus, should precede every attempt to formalize causal statements. Besides, it should be clearly pointed out from the outset that what is required is not an extension of formal, extensional, relations, but the determination of a type of semantic connection among terms that are relevant to each other. The logical aspect of the causal problem is semantical rather than syntactical. Finally, there is no reason why logical analyses of the causal bond should continue to be restricted to the context of the theory of propositions, or even to the calculus of one-place functions. A relational approach might be more rewarding. In fact, it allows us to disclose the following formal properties of simple causation. A. It is a dyadic relation X holding among elements interpretable as events. B. It is irreflexive, that is, X, XRX, which can be read nihil est causa sui. C. It is transitive, chain-like, that is, X, Y, Z, X and YRZ XRZ. D. It is asymmetrical, that is, X, Y, X YRX. Notice, however, that this set of properties does not specify the causal relation. They are common to all ordered sequences, such as the succession of days and nights. They specify the topology of the series, not the nature of its terms. No formalization should be expected to solve the causal problem, although it may contribute to its clarification, especially to the extent to which the causal problem is thereby shown not to be of a logical, and, particularly, extensional, nature. Moreover, an exaggerated insistence on the logical aspect of the causal problem at the expense of its ontological content might lead us back to pre-Humean times, when the term cause was so often identified with reason, and when so many philosophers thought that the validity of any particular causal statement, and of the causal principle in general, could be settled a priori as if it were a logical question. It was a merit of Hume to insist that causation should be stripped of the rationalist element of logical necessity. It was, I believe, a mistake of his, as well as of his followers, to deny that the causal problem is an ontological one, and to claim instead that the concept of causation can be exhausted with purely logical means. 34. To sum up, the causal problem cannot be solved in the domain of pure logic, because it is about the non-logical, or non-linguistic, world. Like every other ontological problem, the causal question should be approached on the basis of the so-called empirical sciences, for they are concerned, among other tasks, with the study of particular causal connections. As to the formalization of causal sentences, the fact that no satisfactory solution seems to have been attained may partly be due to the very starting point of most logicians, which is some conventional highly controvertible formulation of the causal law. The formalization of causal propositions is, in conclusion, an interesting open problem, the importance of which should, however, not be exaggerated, especially since the whole content or meaning of the causation category cannot be displayed with a few symbols. Finally, it must be borne in mind that, to the extent to which the logical side of the causal problem is solved, it ceases being causal. 9.7. Recapitulation and conclusions. Even by the end of the Age of Enlightenment, Lazare Carnot found it necessary to explain, almost apologetically, why he had not deduced or explained the principles of his famous essay Sur les machines en général. A detailed explanation of these principles was not in the plan of the present work, and might result only in confusing things. In fact, the sciences are like a beautiful river, the course of which is easy to follow after it has acquired a certain regularity, but if one wishes to trace it to its source, one does not find the source anywhere, because it is nowhere. The source is in a way scattered over the whole surface of the earth. Likewise, if one wishes to go back to the origin of the sciences, one finds nothing but obscurity, vague ideas, vicious circles, and one gets lost in primitive ideas. 35. Like almost everybody, Carnot was confusing the historical development of a science with its logical structure at a given time. The admission of a few ultimates in every scientific discourse, as contrasted with the positing of material ultimates, that is, of unanalyzable material entities, entails no limit upon the intelligibility of the world. In fact, the meaning of such ultimate explainers is always clarified a posteriori, by the function they perform in the given context, that is, they are explained along the way. Contextual definition. However, it should be recalled that in science rational ultimates, such as axioms, are not to be regarded as dogmas, or as indisputable self-evident verities, but simply as hypotheses to be justified both by the consequences to which they lead and by their consistency with other hypotheses regarded as established. Moreover, the possibility of a further explanation or demonstration of rational ultimates in a different context should not be ruled out a priori, especially in the case of the so-called empirical sciences. 36. In summary, the principle of sufficient reason may be applied to everything save to itself and to such elements of discourse as function as explainers in a given context. Such a limitation of the range of the principle of sufficient reason, far from curtailing the program of attaining a rational understanding of the world, is rather a condition for its consistent fulfillment, for it avoids both vicious circles and the assignment of a fictitious final reason of things. What is true of reason in general is, of course, true of causal reasons, that is, of the reasons whose referents are causes, and which are invoked to explain facts of the concrete world outside and inside ourselves. If not everything that exists has to be explained, then not everything need be assigned a cause. On the other hand, the requirement that everything in the world be explained by causes necessitates the assumption that every causal chain has its ultimate source in an otherworldly final cause. 37 This helps to explain why the identification of science with the knowledge of causes has not always been beneficial for rational knowledge. While it is true that the description of the task of science as the disclosure of causes has led to the discovery of a number of specific connections and types of connection, it has also had the following negative sides. First, it has contributed to blocking the understanding that matter in motion exists per se and that the physical universe is uncaused, the material world being the ground of reason, rather than needing our rational justification for its existence. Secondly, the belief that science is coextensive with causality has fostered the invention of countless fictitious causal agents, among which the scholastic substantial forms have been prominent, and has stimulated a confusing multiplication of the varieties of causes. The schoolmen of the 17th century went so far as to list about 30 kinds of cause. Thirdly, the belief in question has made it easier for the enemies of rational knowledge to hail every instance of non-causal connection as a victory of indeterminism and irrationalism, a triumph determined, be it noted, by rational knowledge itself. Such are some of the reasons why it is important that causation does not exhaust determination, when science cannot be restricted to the knowledge of causes. The chief aims of the present chapter are to clarify the meaning of the term scientific law and to show that the concept of causation need not be replaced by that of law, but on the contrary often actually enters into it. A cursory examination will presently be made of both causal and non-causal types of scientific law. It will show that causal laws are only a species of the genus scientific law. This analysis should enable us to avoid excluding from science all those disciplines in which a certain type of law, for example, causal law, does not play a prominent role. 10.1. Law and law statement. Most scientists are prepared to grant that the chief theoretical, that is, non-pragmatic, aim of scientific research is to answer, in an intelligible, exact, and testable way, 5 kinds of question, namely, those beginning with what, or how, where, when, whence, and why. For the sake of brevity, let us call them the 5 W's of science. Only radical empiricists deny that science has an explanatory function, and restrict the task of scientific research to the description and prediction of observable phenomena. Also, most scientists would agree that all 5 W's are gradually, and painfully, being answered through the establishment of scientific laws, that is, general hypotheses about patterns of being and becoming. Scientific laws enable us to answer the what, the where, the when, the whence, and the why of facts, events and processes, since with their help we can perform the most faithful description, the most accurate pre-24. 8. Diction, both forward and backward, and the most truthful explanation of natural and social facts that are possible at any given moment. It will be necessary to distinguish between laws, whether of nature, thought, or society, and law statements. The former will be defined as the immanent patterns of being and becoming, the latter as the conceptual reconstructions thereof. Whenever a law statement is a general and testable, not necessarily tested, hypothesis, and whenever it has been forwarded in accordance with the fluid standards of scientific method, we may call it a scientific law. For the sake of brevity we shall often refer to laws low, objective patterns, or laws at the ontic level, and laws too, scientific laws, or laws at the epistemic level. Later on we shall have to distinguish a third level of meaning of law, namely, that of predictive nomological statement, see sector 12.I.2. This distinction between objective laws, laws I, and their tentative and improvable reconstruction in the human mind, laws II, is not usually made, although it should be obvious to all non-mentalists if only for the fact that the difference in question is involved in the very notion of perfectibility of the scientific account of facts, as contrasted with the assumed constancy of the patterns of facts. In fact, with but few exceptions among them ampere philosophers of science mean by law what I am calling scientific law, law II. Thus Mach asserted that a law of nature is nothing but a rule for displaying all single predictions. 2. Ostwald III defined laws as predictive patterns of the form if A is experienced, then we expect B. Carnap saw in laws of nature just assertions with a general content. 4. Braithwaite, in his important treatise on scientific explanation, gave the following description: what we call the laws of nature are conceptual devices by which we organize our empirical knowledge and predict the future. 5 And Hutton, in his valuable work on the semantic aspect of metascience, states that a law is merely a statement, or theorem, within a scientific theory. 6. These views are all, of course, in line with the purist empiricist and Kantian Seven tradition, and they are so widespread among philosophers that even Meyerson, despite his conviction that scientific statements have objective reference, could not help writing that a law of nature that we ignore does not exist in the most rigorous sense of this term. 8. On the other hand, what is here meant by a law of physical or social reality is not supposed to depend on our knowledge of it. We assume that laws work objectively, that they are immanent in things, that they are the modes of being and changing of things. As a consequence, laws are discoverable and not inventable, although they are certainly discovered with the help of a great many inventions, tools, both material and conceptual, and instruments, as well as constructs. We certainly do not grasp laws in their virgin purity, we do not even grasp singular facts in themselves, without distortion. The process of scientific discovery is not a mere reflection of facts by way of induction, but arduous work of tentative reconstruction which, while penetrating deeper and deeper into the thing in itself, never attains it entirely. The constructs, hypotheses, called scientific laws, are the variable reconstruction of objective laws on the level of rational thought. If preferred, laws too are the incomplete projections of laws on the conceptual plane. They never entirely overlap the objective laws, as is shown by the historical perfectibility of laws in contrast with the assumed constancy of laws. This partial overlapping, or, better, this incomplete and ambiguous correlation between laws and scientific laws, is not only an instance of the distortion stemming from human frailty or immaturity, but also a consequence of the fact that scientific discovery is a reconstruction rather than a reflection, a process of building models. 25 I of reality rather than that of copying it, as is shown by the fact that science employs a host of abstract entities lacking a factual counterpart, and by the central role played in it by hypotheses. 9 In brief, whereas laws of nature, thought, and society are the structure of reality, the corresponding law statements belong to ideal models of reality, whence they apply, if at all, only approximately, never to any desired degree of accuracy. Now, there are many kinds of scientific law, laws of class inclusion, of composition, and of structure, laws of motion in space, of force, and of conservation, laws of interdependence among qualities, of overall trends, of stochastic connections, and so forth. There are inductive generalizations supported only by the instances they cover, and there are stronger scientific laws, belonging to hypothetical deductive systems, that are supported not only by their instances but by their compatibility with other hypotheses as well. There are laws too stating almost everyday matters of fact and others containing elaborate theoretical concepts, while the indispensable form of others is mathematical, but not necessarily numerical or metrical. There are, in brief, many ways in which laws of nature, thought, and society can be looked upon from a metascientific viewpoint. But at this point we are interested in the problem of scientific law in connection with the question of causal determinacy. And this problem is essentially the following: are there scientific laws that can be termed causal, and others that cannot? At first sight, this is a trivial question. However, the influential positivistic school has claimed, since the days of Kant, that there is a certain opposition between causal explanation and scientific law, the business of science being to dispense altogether with the cause concept as well as with explanation, and to concentrate instead on the search for the so-called phenomenological or descriptive predictive relation. Some antipositivists, like Meyerson, have maintained on the other hand. 252. That scientific laws are nothing but particular cases of the causal principle, and even that entire scientific theories, like analytical mechanics or the atomic theory, are but manifestations of the causal principle, since the chief aim of such theories is to explain phenomena, and explanation, according to an old tradition, is usually assumed to consist in or to be exhausted by causal explanation. That follows is intended to show that scientific research, the chief aim of RIC is certainly the discovery of laws, does not dispense entirely with the cause concept, and that science contains both causal and non-causal laws, as well as laws having a causal range. 10.2. The traditional identification of causality and lawfulness following an ancient tradition recorded by Sextus Empiri Cus 10 lawfulness, that is, agreement with law, is usually identified with causality, as if no other kinds of scientific law were possible than causal laws. First-rate thinkers have conured with this confusion even after the popularization of the discoveries of non-causal laws, such as the so-called phenomenological laws of geometric optics and of thermodynamics, the statistical laws of random populations, the teleological laws of living matter, or the dialectical laws of human history. Thus in Russ' old age Helmholtz recognized that in his famous youthful work on the conservation of energy he had let himself be influenced too strongly by Kant. Only later did he realize that the principle of causality is nothing but the assumption of the lawfulness Gesetzlichkeit J of all natural phenomena. L2 Some years later, Mach stated a similar identity between lawfulness and causality, the business of physical sciences. The Reconstruction Nachbildung, copy rather than reconstruction of facts in thought, or the abstract quantitative expression of facts. The rules which we form for these reconstructions are the laws of nature. In the conviction that such rules are possible lies the law of causality. The law of causality simply asserts that the phenomena of nature are dependent on one another. 13 From this chain of definitions it clearly appears that Mach did not regard laws as immanent in nature but as rules of procedure, as man-made rules devised in order to translate the facts, that is, the primary sense data, into thoughts. A strange paradox. On this view, laws of nature must be contingent relatively to nature, just as in the religious philosophies of nature. L4 The two identifications performed by Mach in the foregoing quotation, that of law with rule of procedure, and that of causality with lawfulness, have been retained by subsequent positivists. Thus Russell once gave the following definition: by a causal law I mean any general proposition in virtue of which it is possible to infer the existence of one thing or event from the existence of another or of a number of others. 15 The cryptic prophet of logical positivism wrote in his characteristic style, if there were a law of causality, it might run, there are natural laws. But that can clearly not be said. It shows itself. 16 The founder of the Vienna Circle 17 regarded laws of nature as Vorschriften, directions, and Verhaltungsregeln, rules of behavior or procedure, of the investigator, which is certainly true, but not the whole truth. See Sector 10. And he also identified causality with lawfulness when he wrote that the inquiry as to whether causality exists can only be interpreted as the inquiry whether a natural law exists. The principle of causality itself is not a law, it only expresses the fact that laws exist. L8 Even antipositivists, like Bergson 19 and Planck 20, have retained the traditional identification of scientific law with causal law, though of course with different aims. Although statistical physics is almost a century old, it is still possible to read sentences stating that there is an irreducible opposition between genuine laws of nature and statistical laws, as if the latter could not be laws of nature and indeed not laws at all, but mere overall regularities, just because they do not enable us to predict individual events with certainty. Even Eddington 21 could not acknowledge the existence of a law of chance, although he was an indeterminist. The very notion of a law of chance conflicted with his Pythagorean rationalism. The same irreducible opposition between natural and statistical laws was held by two eminent empiricists. 22 Presumably on the 18th century thesis that chance is but a name for our ignorance of nature's stern rules of causation, and not an objective mode of being subject to a new type of law. The mere existence of non-causal scientific laws, such as the laws of correlated variatics in organisms, shows that scientific research does not consist exclusively, probably not even mainly, in the search for causal laws. Just a few types of non-causal scientific laws will be mentioned in following sections, with particular emphasis on taxonomic, kinematic, and statistical ones. They might all be forced under the heading of exclusively descriptive laws, but this classification, however widespread, is erroneous, since such laws serve explanatory purposes as well, only, as will be shown below, they do not enable us to formulate causal explanations. 1003 Some non-causal types of scientific law. 10.3 Taxonomical and morphological laws. All law statements involve the class concept, whether explicitly or not, since they all refer to kinds or classes of facts rather than to singular facts, see Sector 2.2. But taxonomical laws are just classifications, that is, statements of class inclusion, and therefore they are the simplest of all types of law statements. Linnaeus's epoch-making Systema Naturae, 1737-1768, was not concerned with change, hence it did not need any category of determination. This work introduced a method of artificial classification, by single characters, of coexisting living forms without any reference to lineage, and set forth a number of taxonomical laws. True, the Linnaean classification was afterward supplemented with systems of phylogenetic classifications founded on aggregates of characters and based on hypotheses of genetic relations and evolution. That is, new arrangements of the available material were made with a predominantly, though not exclusively, descriptive purpose, on the basis of explanatory hypotheses. In other words, new descriptions were grounded on a new explanation. But Linnaeus's systematics was undoubtedly an indispensable preliminary stage in biology, at least in the science of plants, and this is easy to understand, for before knowing that species had been changing, and that genealogy accounted for parentage, it was necessary to know what might have evolved. The replacement of artificial by natural or genealogical systems of classification did not mean, however, a substitution of causal explanation for sheer description, in fact, to the extent to which evolutionary systematics 256 accounts for biological progress, it goes beyond the scope of causality, which excludes higher novelty, see Sector 8.2. Another outstanding member of the class of non-causal and morphological theories is classical crystallography. The crystal types classified by this discipline may in turn be explained by the atomic theory, which does include a causal element. But the discipline concerning crystal forms is a science in its own right, and is moreover indispensable for explaining certain physical phenomena like piezoelectricity, which originates in crystallographic asymmetry. Generally speaking, the morphological branches of science need not contain causal elements, although they may turn out to be explainable in terms of theories containing causal elements. For the explanation of laws in terms of higher-level laws, see seconds 2.2.3. 10.3.2. Kinematical laws. Among kinematical theories, some of the most interesting and far-reaching are Ptolemy's and Copernicus' theories of planetary motion. They assigned no causes to the complex motions of the celestial vagabonds, however, they help to explain and to predict other celestial phenomena, such as eclipses. That is to say, these kinematical theories were not contrary to what is usually held purely phenomenological theories, they were not restricted to describing phenomena without explaining any of them. Thus the aim of Ptolemy's astronomical theory was to explain sensible appearances, notably the apparently irregular motion of the planets, see Fig 26, which was indeed irregular relative to the apparently circular motion of the stars. Is it necessary to show that order and regularity are not absolute but relative? The Almagest, CAD 140, performed this task with the help of the hypothetical epicycles and eccentrics invented by Hipparchus, see Figs 27 and 28, and which were curves to which Ptolemy and most of his followers seem to have assigned no reality. The component motions functioned as reasons rather than as causes. Ptolemy thereby succeeded in explaining the apparent motions of the planets, whose irritating irregularity was one of the most important sources of progress in astronomy. To this extent, his Fig 26. Apparent motion of a planet. As seen from the Earth, the advances, halts, and backward motions are irregular relative to the apparent motion of the fixed stars. 257. Theory was not phenomenological despite the assertion of phenomenalists. 23. What Ptolemy did not explain was why the component motions of planets were such as he assumed and not otherwise. In particular, his theory did not point to the efficient causes of planetary motion. His was a non-causal and predominantly descriptive, but partly also explanatory, theory. Aristotelians could obviously not remain satisfied with such an astronomical system, and precisely because it was not a causal theory, hence not fully explanatory, on the Aristotelian doctrine that explaining is advancing reasons, which are in turn causes, see Sector 9.2. By adopting and elaborating the astronomical ideas of Callippus and of Eudoxus of Cnidos, according to whom celestial bodies were dragged along by homocentric rotating spheres, Aristotle had completed a causal theory of heavenly motions. Every one of the numerous celestial spheres he invented was charged with the task of pushing a group of celestial bodies. The spheres were in turn pushed each by a first mover. Unfortunately for the followers of the philosopher, his astronomical theory did not match the results of observation. This is why Averroes, the commentator, complained that the astronomy of his day did not exist, being a convenient means for computation, without however agreeing with what exists. 259. Many an Aristotelian must have wondered how it was possible for a non-causal theory like Ptolemy's to account for most of the then known celestial phenomena and even to afford an explanation of some of them, notably the awesome eclipses. However, nobody seems to have drawn on the correct conclusion, namely, that a scientific theory need not be causal. As is well known, Newton's theory enabled kinematic laws, such as Kepler's, to be explained. Consequently, these need no longer be regarded as ultimates, though at the price of admitting higher-level ultimates, namely, Newton's second law of motion and the law of gravity, which in turn become derived statements in the wider context of the general theory of relativity. Thereby, astronomical theories have been built, which satisfied the rationalistic demands of Averroes, though not his Aristotelian requirement that reasons correspond to causes. Furthermore, modern dynamics made it possible to show that Kepler's kinematic laws of planetary motion are only approximate, owing essentially to the perturbations exerted by the remaining planets. Besides, it has made it possible to ascertain that the appearances which the geocentric theory took as unshakable starting points were wrong, the correct point of departure being an unperceived but intelligible and objective reality hiding behind the appearances. 24. But the fact that the elementary kinematic laws of planetary motion can be explained by, that is, be deduced from, a higher-level theory containing an important causal element, Newton's theory, does not invalidate the assertion that the former are non-causal laws. For contrary to what Russell 25 and others have maintained, a statement such as planets move in ellipses, essentially Kepler's first law, is not a causal law, for the simple reason that it does not refer to the causes of either motion or ellipticity. 10.3.3. Further non-causal laws, statistical laws, principles of relativity, and quantum prohibitions. Statistical laws are indisputably non-causal, even though some of them may be shown to be partly derivable from laws having a causal component. A typical illustration is afforded by the kinetic theory of heat, which explains thermal phenomena as emerging from lower-level mechanical motions, or, more exactly, as the collective result of a large number of individual mechanical motions. 3 layers of theory and consequently 3 types of scientific law are involved in the statistical mechanical explanation of molar, thermodynamic phenomena. They are, I. Particle dynamics, applying to single molecules; 2. Statistical mechanics, studying the overall and long-run behavior of large collections of similar components; 3. Thermodynamics, treating physical systems as wholes, the emergent properties of which are partially explained in terms of I, and 2.26. The first level, particle dynamics, contains a strong causal component, summarized in the force equation. At the second level, statistical mechanics, the non-causal notion of Random motion, or mutual irrelevance of trajectories, is introduced. That is, while the individual motions are regarded as dynamically determined, every one of them is assumed to be contingent upon the remaining motions. On the next level of theory, thermodynamics, both causation and chance have disappeared almost entirely. They have merged together, producing a theory dealing with concepts, referring to properties and processes, linked together by symmetrical functional relations which cannot be polarized in an unambiguous way into cause-effect links. But we need not resort to statistical physics in order to substantiate our contention that lawfulness is not exhausted by causality. The special theory of relativity, usually, and wrongly, regarded as an altogether causal theory, affords an outstanding example of theoretical structure having non-causal ingredients at its very basis. In fact, the basic axioms of this theory may be considered to be the special principle of relativity, stating the invariance of physical laws relative to the choice of inertial systems of reference, and the principle of the constancy of the velocity of light in a vacuum. It is only occasionally recognized 27 that neither of these principles is a causal law. That this is so can be verified by confronting them with any of the formulations of the causal principle, see Chapter 2. The same conclusion can be reached from a direct examination of the Lorentz transformation formulas, which can be derived exclusively from those axioms with some additions of a mathematical nature. Indeed, the Lorentz formulas, x, vt, x equals, I underscore v2 jc2, ty equals y, z equals z, state a relation between inertial systems, not a genetic one-sided dependence, as the causal bond docs. Consequently, the Lorentz-Fitzgerald contraction, following from these formulas, is uncaused. The realization of the non-causal nature of the Lorentz transformation formulas should alone be enough to discourage inquiries into the cause of the contraction, which inquiries have contributed to clouding the interpretation of relativity, by hiding the relational character of both space and time. 28. Finally, let us mention a rather odd group of law statements seldom, if ever, containing the causation category, namely, the prohibitions or assertions of physical impossibility. The first two laws of thermodynamics may be framed as stating the impossibility of existence of perpetual movers of the first and second kinds respectively. Atomic and nuclear spectroscopy both contain a host of selection rules prohibiting certain transitions, that is, stating the impossibility of the existence of certain spectral lines or decay schemes. A further characteristic forbid is Pauli's exclusion principle. These laws are neither causal nor statistical, but constitute a group of their own. It is interesting to notice that both certain conservation theorems and selection rules which are constants of the behavior of microsystems, and are derived from higher-level laws do not refer to collections of systems but to individual objects, that is, they are supposed to be valid for every single microsystem, and not on the average or for a certain percentage of microsystems taken at random. This is important because it shows that quantum mechanics, in either of its interpretations, is far from being a purely statistical theory. 29. Contrary to what is usually asserted. This will be enough, I hope, to show that scientific laws of nature need not be causal. I now turn to the thornier problem of socio-historic laws. Ida. Causality and lawfulness in the socio-historical sciences are 0-4I. Are sociology and history scientific disciplines? The reduction of lawfulness to causality is a mistake in scientific method and, like other mistakes of this sort, it is liable to have noxious consequences for science and for every general world outlook that claims to be based on science. In fact, such a restriction of the meaning of lawfulness lends itself to the attacks of phenomenalism, indeterminism, irrationalism, and subjectivism upon science. This is only too clear in the case of atomic and nuclear physics. Vera non-causal lawfulness is often looked upon as a sign of indeterminacy, whereas it only shows that causality has a limited range of validity. But the negative results of the restriction of lawfulness to causality are even clearer in the field of the sciences of man, where the exclusive operation of causation is far from obvious. Essentially, two arguments have been invoked in support of the claim that sociology and history are impossible qua-sciences. The first is the uniqueness or unrepeatability of socio-historical facts, the second is the non-causal nature of human affairs. If science were defined as the disclosure of the causes of recurrent, non-unique, events, then it would not be difficult to show that the sciences of society and history are impossible, since no two identical events are to be found in things human, and since non-causal categories of determination, such as statistical, teleological, and dialectical ones, are clearly involved in them. Two ways are open, either to acknowledge that the failure to include history and society in that definition shows only the inadequacy of the definition, or to maintain that the definition is correct but applies only to the natural, not to the cultural, sciences. The latter course has been taken by the humanistic historical school, initiated toward the end of the 9th century by Dilthey, Rickert, Windelband, and other members 30 of the Geisteswissenschaften movement of reaction against the extension of the scientific method to all fields of research or, at least, against its application to problems where it might yield undesirable insights. These writers, particularly Dilthey, denied that the chief object of historical science is both the material conditions of existence and the social, largely impersonal, forces that ultimately mold the spiritual culture. They asserted, on the contrary, that the sole concern of the historian is to trace the exploits of an allegedly free spirit, which they regarded as independent of the material culture. Moreover, they refused to grant that the ultimate aim of historical research is the disclosure of general laws. They held that the aim of the historian should be restricted to the literary description and artistic resurrection of altogether singular and lawless events of a spiritual nature, for which task a mysterious and rarely found inborn intuition, das Verstehen, is indispensable. This supposed ersatz of the scientific method is, of course, alien to general norms enjoying an intersubjective validity. According to this regressive trend, history is, in brief, not a science but an art, or at most a branch of philosophy, in the traditional sense of the word, requiring a special insight. 31 Now, it would be foolish to deny that some insight is needed in order to disentangle orderliness, to solve problems, or to invent fact-fitting hypotheses, whether in history or in any other science. What is disputed is, a. that there is an inborn historical insight, and, b. that insight, whatever psychologists may find out it is the guarantee of truth. Being incapable of providing a test for historical hypotheses, the celebrated method of Verstehen is not a method at all and has no title to replace scientific method. The claim that historical events are the feats of a free spirit need not concern us. Two monstrous world wars and the pending menace of nuclear and bacteriological warfare should suffice to dispose of such nonsense, the sole use of which might be to consecrate acts of rapine and murder as pure, spiritual exploits. What is relevant to our concern is the claim that it is not possible to disclose laws of history, because historical events are both specific, unique, singular, einzeln, and essentially non-causal. Let us start by examining the assertion that historical events are unrepeatable, for if they turned out to be completely unique, if they were singular in all respects, then obviously no general law, whether causal or not, would be found to fit, since law statements do not refer to single objects that are unique in all respects, but to kinds or classes of objects. The presumed non-causal nature of historical events will concern 10.4.2. The uniqueness of historical events. The unique, unrepeatable, specific character of socio-historical events is hardly disputable. The question is whether this uniqueness or Einmaligkeit is peculiar to human affairs or is a trait of all concrete objects, though admittedly to a lesser extent on levels lower than that of society or culture. That such a uniqueness is peculiar to socio-historical facts is easily granted by those who, from Schelling to the contemporary Romantics, are not familiar enough with the natural sciences. Even outstanding methodologists who grant the possibility of building a science of history, and who assert that causal explanations of historical facts are possible, claim that the difference between history, an allegedly particularizing science, and the generalizing sciences, like physics, lies precisely in that it is the particular event that interests them, many students of history and of its methods, and not any so-called universal historical laws. For from our point of view, there can be no historical laws. Those who are interested in laws must turn to the generalizing sciences, for example, to sociology. 32. 2 points in this characteristic statement are relevant to our problem. The first concerns the concept of particular event, the second regards the controvertible identification of historical laws, most of which might consist in overall and long-run trends, with universal historical laws, valid for every type of society and covering every single historical event of a given class. The nature of historical laws will concern us in the next section. As to the first question, let us begin by granting that complete identity in all respects, such as is defined in Logic 33, is a theoretical fiction in connection with socio-historical. 266. Facts. But, then, it is a fiction in all other fields as well, with the single exception of logic and mathematics, which build their own identical objects. This is a matter of fact for every dynamical ontology, from Leibniz to dialectical materialism and Whitehead's philosophy of organism. And it is increasingly being felt by scientists, too. Thus no thoughtful physicist believes now that there are in the real world, in contrast to theoretical schemes, two bits of matter, whether endowed with mass or not, in exactly the same state and interacting with exactly the same fields. No two macroscopic events can be strictly identical, if only because the entropy of molar systems never remains the same. Every physical object, material system, event, or process, is an unicum in at least one respect. Contrary to what Hegel thought, man not nature is the privileged inventor of strict, ideal, identity and recurrence, man is consequently the exclusive proprietor of boredom. Identity of coexistence, and exact repetition of successives, are as ideal as perfect circles, they are found to obtain to within a non-vanishing error only. Total identity of concrete objects is an appearance sooner or later corrected by finer observations and deeper theoretical analyses. Only partial identity will be found at the ontic level. If something is not unique in at least one respect, then it does not belong to the external world. Consequently, no science of the concrete world can aspire to find complete repeatability, that is, repeatability in all respects, the type of identity we build at the level of abstract thought. Hence exception is not an unscientific word, as is usually believed. Exceptions are just the least frequent alternatives in a collection of facts. The idea that exact identity is not a relation among facts of the external world but a construct that is very often approximately true is supported by the examination of the act of measurement. The measurement of the simplest physical attribute, such as length or weight, almost never yields the same result twice, provided sufficiently accurate instruments are employed, see Fig. 29. This is not a result of the limitations of our power of observation, quite the contrary. As the sensitivity of the measuring instrument increases, unrepeatability increases as well. That is, the finer the observation, the more differences are detected. This is due to a deeper penetration in the fine structure of the object concerned, and to changes both in the object under observation and in its environment, in which the experimental setup must be included. In short, the finer the observation, the smaller the chance of finding two things exactly alike. And this is just why finer observations are always desirable, not because they increase uniformity but because they permit the detection of a larger diversity. If such a specificity, uniqueness, or unrepeatability of events in the world of matter does not make physico-chemical sciences impossible, why should it render the social sciences impossible? Granted, socio-historical events are enormously richer than those of the lower levels, and this lends them a higher degree of specificity or individuality. But this does not mean that socio-historical events are einmalig, that is, happen but once, in all respects. To hold complete unrepeatability is as superficial as to 268 the function oj the causal principle in science repeat that history repeats itself, and it amounts to denying the existence of species on the ground that no two individuals are exactly alike, a nominalistic, and nihilistic, position criticized long ago by Kant. 34 Nor does the diversity in question show that socio-historical events are lawless, which would be the sole mark rendering their scientific approach fruitless. If socio-historical events were all essentially different from one another, if no two similar happenings could be found, if uniqueness in detail were inconsistent with essential and partial identity or at least similarity, then nothing in society and in its historical development would be intelligible, and social scientists and historians could aspire to nothing but a more or less artistic chronicling of separate, unintelligible, hence useless facts. Assuming that their mere description were possible, which assumption is far from obvious, since a new set of terms would have to be invented to narrate every event. Presumably no intelligent person would be interested in such a description, even if it were possible. Let us now turn to the question of whether there are historical laws. 10.4.3 The lawfulness of historical processes. It can easily be granted that we know as yet very few universal historical laws, in the sense of patterns common to all periods and to all types of social organization. In the first place, most known historical laws are, as will be argued below, statistical laws, in the sense both that they involve numerous collections of men and that they do not apply in every single case but in a certain percentage of cases. In the second place, each type of social organization exists and evolves according to its own peculiar laws, thus the social life and the historical development of a community facing nature as a more or less integrated whole could not be the same as those of a social group ridden by struggles between antagonistic classes. Historical laws do not tower above men but are just the way in which men get along in time. Notwithstanding, some social laws do remain quite constant through history, and the existence of such cultural invariants, or constant patterns of social behavior, is what entitles the anthropologist to speak of man, and the historian to speak of the history of man. 35 One such invariant is the ultimate or long-run predominance of material, biological and economic, conditions over spiritual culture, condensed in one of the few sayings that have both an individual and a social validity, namely, primum vivere, deinde philosopheri. Another, by now quite obvious, socio-historical law statement is the one according to which deep changes in the mode of production, such as the renewal or reorganization of technical equipment, in the long run elicit the renewal of the social structure or at least render such a readjustment of social relations desirable to a section of society, which accordingly attempts to modify the prevailing social organization. A further universal historical law too is the statement that gathering and hunting precede plant, animal, and human domestication, which in turn precedes civilization, at least in the case of autonomously evolving social communities. Besides a handful of truly universal socio-historical laws, which are grounded on general and nearly constant traits of mankind and are just the ones enabling us to group all men in the species Homo sapiens, there are general laws peculiar to each type of social organization, or culture. That there are such laws is shown by the well-known fact that each type of society reacts in a typical way of its own to any given stimulus, whether external or internal. And is not the typical form of social behavior in the course of time what is meant by an historical law? However, it must be admitted that the social sciences are still characterized by too large a gap between the factual basis and the uppermost level of general principles. This gap between singular facts and higher-level law statements is gradually being filled with law statements, lower-level hypotheses, inferred from particulars though not without the interference, favorable or otherwise, of general principles. To the extent to which this gap in the level of laws is filled, the valuation of both the factual basis and the top will undoubtedly change, different kinds of facts will be regarded as relevant, and new general principles will accordingly be proposed but, now, not as mere hunches based on insufficient data, but as syntheses of whole bundles of particular law statements. With regard to the scientific study of the existing social types, once this stage has been attained, and probably before the newly found general principles bear fully grown fruits, the discovery of new facts and new laws, the time may have come to alter the prevailing social structures, zero-baying such principles, and so sociological knowledge will become historical knowledge. Granted, historical laws are enormously more complex than natural laws. In history we do not find it possible to apply easy schemes like the Hebrew prophet's law of increasing evil, or Spencer's law of unlimited progress, or the inevitable repetition asserted by Buckle and Schopenhauer, or the organismic rule of cyclical growth and decadence imagined by Vico and Spengler. Besides complexity, a further factor tends to obscure historical lawfulness, namely, the usually forgotten fact that single scientific laws, of whatever kind, do not hold for concrete, specific, individual instances. Scientific laws hold only for classes of facts, and classes have a real existence in a limited number of respects alone, whereas concrete individual systems, events, or processes have an unlimited number of sides, so that they may belong to many different classes, their specification therefore requiring a number of laws. In order to make a group of concrete objects, systems, events, processes, fit into a class, we are forced to strip every one of them of peculiar marks that are irrelevant to the class in question. In a sense, by classifying events, and every application of law statements involves a previous classification, we turn concrete objects into abstract ones, but, if the classification is adequate, that is, if the attribute or set of attributes chosen for the grouping is actually possessed by every member of the class, then the universals concerned will have a real counterpart. In this case, the class, a product of intellectual activity, will also have an objective status, but the recognition of such an objectivity, far from being obvious, will demand a varying effort of abstraction. Hence the uniqueness, specificity, individuality of every member in a collection does not render classifications illusory. The elements of the collection will all be the same in certain respects, never in all particulars, that is, if they are concrete objects. This applies, of course, not only to properties at any given instant but to their changes in time as well. Laws, whether of structure or of process, whether of society or of history, are then possible. Thus wars consist of fights among armed people for some reason, usually a material interest. Hence, although no two wars in the past have been exactly alike, they all share certain characteristics, they all fit a few elementary patterns. The existence of laws of war makes it possible and profitable to study strategy and tactics, using information about wars in the past in order to disclose and illustrate laws, the knowledge of which may be useful in future butcheries. As a consequence, historical particularizing is not inconsistent with scientific generalizing, establishment and use of laws, and is moreover performed on two successive levels: first, in the narrative of true histories; second, in the attempt to make these histories fit a comprehensive theoretical framework involving explanatory laws. The point is that the explanation of a unique historical event cannot be attained with the help of a single law statement, that is, it cannot be derived as an instance of a single nomological statement, in conjunction with a set of items of information performing a function analogous to the initial conditions of physics. Concrete, hence unique, objects, such as historical events, may be viewed as intersections of a large, perhaps infinite, number of laws. The following sketch of a logical analysis of the problem of uniqueness versus legality may contribute to clear the issues. Let XL denote any characteristic, property, and let L designate any of the laws connecting XL with other properties, X2, X3. In the simplest case, the law Ln will have the form of a dyadic relation, that is, in this case Ln equals df, 1 Rn, XL Rn Xn. Let us call F the field of the nth roughly, the class of facts for which 272 Ln holds, or, better, the set of elements XL for which the law Ln holds. And let us finally build the intersection of the fields of the laws which the property XL obeys, namely, F equals phi F2 Fn. This will be, by definition, the domain in which all of the laws in question hold in conjunction. Such a field or range may be referred to as the locus Oj, the set of laws Ln. My assumption is that every real fact, event, phenomenon, in which XL is involved can be regarded as the sole element Oj. The locus Oj a certain number of laws I if preferred. Unique facts are those loci of a given set of laws that reduce to a single point. Even better, on this assumption singular facts are described in terms of general laws as the single member loci of a set of laws, thus, 1x, x euro f1 f2. Fn. It is both ignorance of presumably important socio-historical laws and their large number that usually prevent historians from going beyond the level of narrative. In this regard, the situation in the historical sciences is not essentially different from the one that still prevails in medicine, where case histories are indispensable, not only as the raw material for the eventual inference of laws, but also as a substitute for as yet ignored, but presumed, laws. The present relative backwardness of medical theory does not, however, warrant the conclusion that there are no laws of human pathology. Why should not the same apply to history? 10.4 Plus obstacles to disclosure Oj. Historical laws. One of the difficulties besetting the disclosure of laws in any field is the low frequency of observed regularities. Was not the apparent disorder in the phenomenal world one of the pretexts Plato gave for denying the possibility of a science of the material world? Regularities are seldom observed, they are usually inferred or reconstructed, that is, first assumed and then tested, and this, just because regularities pertain not to individual, specific objects, but to classes of objects. In order to find regularities we must make an extensive use of abstraction, which alone can go beyond the maze of appearances into the essence of things. We must, in brief, impoverish the immediately given before we are able to recognize its orderliness. In other 273 words, the establishment of laws requires the framing of theoretical models, and this will not become a habit as long as the descriptive attitude prevails in the sciences of man. 36 Philosophers of social sciences should not dogmatically deny that man is capable of learning some socio-historical laws. At least, man is entitled to seek for laws of cultural development, being moreover vitally interested in finding them, just in order to improve his chances of succeeding in socio-historical business. Philosophers of cultural sciences should also grant that our comparative ignorance of the laws of society and history is due not only to the great complexity of human affairs, but also to the very prejudice that there are no laws of history, a prejudice suspect of being allied to powerful social, or antisocial, interests that are vitally interested in preventing deep insights into the social mechanism. Et pour cause. People who are able to take the social mechanism apart in theory may wish to change it in practice, and what is more dangerous for those who live on the persistence of fossil social forms, such men may even succeed in their attempt. This is essentially why the pragmatic view of science, summarized in the positivistic maxim to know is to foresee is to control, which enjoys such wide acceptance in connection with the sciences of nature, is so often forgotten in the sphere of the social sciences, where it is found more desirable to hold that human society is rationally unknowable, hence unpredictable, hence incurable. To summarize, there are historical laws, 37, both universal and general, the former applying to mankind, the latter to definite types of social organization, but this does not mean that history repeats itself. Nor does the lawfulness of nature exclude novelty, see Sector 8.25. There are general patterns of collective behavior and of its changes, but most of them, being peculiar to the type of social structure, change in turn with every radical social transformation. Finally, as will be argued in the next section, socio-historical laws are not exclusively, perhaps not even predominantly, patterns of causation. RO 4.5. Non-causal features of socio-historical events. Many philosophers, but I believe few historians, would deny that most social processes of historical importance are at the same time strongly self-determined, internally determined by the structure of the social group itself, definitely dialectical, consisting in or brought about by struggles of human groups, partly teleological, striving, though mostly unconsciously, toward the attainment of definite goals, and typically statistical, the collective result of different individual actions largely independent of one another, that socio-historical events are, in short, eminently non-causal. The self-determination of socio-historical events is here understood in the sense that factors external to the human group concerned, natural environment and contacts with neighbor cultures, are effective solely insofar as they succeed in changing the essential inner processes, which proceed in accordance with immanent laws, those of material production, social relations, and spiritual life. These laws are all certainly rooted in the animal basis of man, but they do not therefore reduce to biological laws. Thus, the laws of the production and circulation of commodities in a given society are rooted in the common animal needs of man, but they are economic, not biological, laws. This is why they change considerably in the course of history, even though man has changed but little, biologically speaking, during the last several millennia. The dialectical nature of the socio-historical events having some historical relief is related to that very self-determination, and originates in the lack of social homogeneity and inhomogeneity that exists whether or not the social group concerned is divided into social classes, but that is characteristically intensified, to the point of eliciting destructive antagonisms, wherever the appropriation of material goods is individual. It is, in fact, no longer a secret, although it is still widely held to be a seditious heresy, that the main source of social change is the pacific or warlike clash of material and cultural interests. As to the partially teleological or goal-seeking character of socio-historical processes, it hardly needs to be proved, since it is a truism that men act not only because they are driven by present inward and outward pressures but also in view of the future, sometimes even in view of a non-existent personal future. Human behavior is of course not always conscious, and it is seldom intelligently planned, although it would be foolish to deny that the conscious planning of social life has been steadily increasing since the dawn of civilization. Moreover, human action is too often unsuccessful, which only shows that teleology should not be understood in a fatalistic but in a statistical sense. However, in contrast to processes at the level of inanimate matter, human behavior is largely directed to the satisfaction of future needs and to the future attainment of freedom from want. Nevertheless, this does not happen in every individual instance. Teleological laws obtain only in a large percentage of cases, that is, they are statistical. The statistical nature of social events was recognized, though only in a restricted manner, early in the 17th century by Dutch statesmen and statisticians who realized the usefulness of statistics for governmental affairs. But the rise of this discovery, from a technique for the collection of taxes and estimate of budgets to a principle of the philosophy of the cultural sciences, had to wait till Condorcet's Mathématiques sociales, 1795, Vitellet's Physique sociale, 1836, and Historical Materialism, 1850s. In the statistical determinacy of social events, historical materialism saw a confirmation of its thesis that the laws of society are as objective, and operate as blindly, as the laws of nature. Most economic, social, cultural, and historical laws do not consist in fixed recurrent patterns concerning the totality of a class of individual events. They are, instead, tendencies, that is, overall and long-run trends. They do not apply without exception to every individual event of a certain kind, but in a given percentage, and hold for kinds of large collections of events. They are, in short, collective regularities. The term probability law is often used as a synonym of statistical law. 276. But such a designation is misleading, since probability is a mathematical concept. Only the propositions of the theory of probability should be termed probability laws. Consequently, at the pragmatic level, cultural laws are not infallible precepts but, at their very best, rough maxims that are found successful in a high percentage of cases. The fact that most socio-historical laws have a statistical character does not mean that individual events are lawless. It means only that they cannot be expected to obey single laws, but rather groups of laws operating in conjunction, see Sector 10.4.3. And they are not only governed by socio-historical laws, but by lower-order laws as well, that is, singular facts at the social level are the intersection of a number of laws belonging to both the social and the lower integrative levels. Thus the decisions of the individuals participating in a given historical event are motivated by biological, psychological, intellectual, and other factors, but they will be effective solely provided they fit a social scheme. And the statistical nature of most socio-historical laws does not mean that the social sciences are solely interested in the statistical resultants of many individual deeds without caring for the latter in themselves. Not only the most frequent events are important, hence interesting to the historian, also large deviations from the mean, uninteresting to the statistician, are sometimes eminently interesting to the historian, for they may be associated with deep qualitative changes. An obvious illustration of such infrequent, improbable, events is provided by the profound changes that comparatively small sections of mankind, and even exceptional single individuals, succeed in eliciting from time to time, namely, social and political readjustments. But even such exceptional events, far from being lawless, are the outcome of the laws of social growth. Besides, even if novel in the highest degree, they will share something with similar events in the past, and this partial identity is what renders the study of history useful for both conservatives and reformers. 10+6. Scientific exactness, not exhausted by numerical accuracy. The claim is often heard that sociology cannot apply statistical methods in all of its sections, owing to the existence of social imponderabilia, of allegedly unmeasurable characteristics such as taste, fashion, devotion to a cause, enthusiasm, and so forth. While it is true that the assessment of the weight of every cultural factor is far from easy, experience seems to show that there is no difficulty in principle in making it. The problem reduces essentially to devising the adequate conceptual tool and appropriate technique. The alleged imponderabilia are unmeasured rather than unmeasurable characteristics, and they usually finish by being weighted in some way as soon as it is found that they have an economic importance. No object in the external world is inherently non-quantitative. What is usually non-quantitative, but just classificatory or comparative, is our approach to concrete objects. Besides, the aim and result of the measurement of social features need not always be a set of numbers fitting functions, vectors, tensors, matrices, and so on. Sociology is certainly interested in measuring the intensities of socio-economic factors, the concern of sociometrics, but sociology is also interested in topological or order qualities and relations that can be described with an equivalent accuracy. Thus, the inquiry into the structure of a social group is a socio-topological, not a sociometrical, problem, although it is approached on the basis of definite numerical data such as income distributions. In the case of certain stable societies it requires further, non-quantitative data, such as those regarding the place occupied by the members of the particular group in material production and in the social hierarchy, if any. In short, the metrical or numerical approach to social problems is indispensable, but it must be supplemented with a likewise exact, but comparative or topological, analysis. However, this is not peculiar to the sciences of man. Exactness is not exhausted by numerical accuracy. An exclusively statistical approach to socio-historical facts, and moreover an approach focusing on the measurement of 278 petty details but overlooking the mainstream, may be as misleading as a purely qualitative approach. However, the error does not lie in the method itself, it may lie in the selection of facts, a selection that is always guided, overtly or not, by general principles. Exclusively statistical accounts tend to overlook both the main trends of social development and the inner mechanism bringing about the given statistical results. This micro-sociological approach, so typical of contemporary American sociology, is unable to foresee the major social changes, although it may afford accurate predictions regarding the forthcoming sales of a cigarette brand. But this short-sightedness is not, let me repeat, inherent in the statistical approach. it is usually the result of a superficial selection of facts, and of lack of theoretical models in the service of whose test the data should be gathered. The microsociological approach must be supplemented with the inquiry into the inner mechanism of social evolution. The latter can both make use of and guide microsociological research. At any rate, the intimate mechanism producing the observable statistical results in the social field is not essentially causal, although it is perfectly determinate. 10+7. The defense of the scientific method in the socio-historical sciences. The claim of the Geisteswissenschaft movement, that the study of history cannot be scientific because it has not been possible to find causal historical laws, is justified to the extent that, a. Historical writings are usually less than causal analyses, remaining mostly at the level of chronicling or narrative, b. A strictly causal analysis of historical facts would of necessity overlook an enormous number of facts and connections not fitting any bundle of causal threads, c. The causal approach to historical problems has led to the isolation of causal chains that can easily be destroyed by organismic and functionalist philosophies of history, see Sector 5.2.2. The identification of scientific analysis with causal analysis thus facilitates the view that history cannot be a science, a view that very nicely matches the desire to prevent people from understanding what they are doing and 279. From learning how to participate consciously and effectively in historical events. However, defenders of a scientific approach to human affairs often write that the chief aim of social science is to attain a knowledge of causal connections among social factors. 38. And that the historian's main task is the disclosure of causal bonds among events. 39. I think that such statements should not be taken too literally. What they mean is not always a systematic application of the causal principle, but rather the application of the principle of determinacy, that is, of the lawful genetic connection, see Sector 1 foot 5.3 inches. What most contemporary defenders of causality actually mean is, I believe, that events do not happen capriciously but according to law, and that they do not spring out of nothing but emerge from pre-existing conditions. Hence, where they write causal connections, one should perhaps read some sort of law-dual connection, whether causal or not. In order to decrease the prevailing confusion about historical method and its ontological presuppositions, it is desirable to dispense with the nomenclature attached to an outdated philosophy of science, namely, that asserting the coextensiveness of science and causality. A way of defending the application of the scientific method in sociology and history is to acknowledge the limitations of causality, and to demand the exploration of the whole range of types of determination. Being a particular nexus, causation is defensible as a trait of reality and is even indispensable as an approximate reconstruction of becoming, but it is indefensible as a category of unlimited extension. Lawfulness, on the other hand, is not only the chief result of scientific research but also, in a way, its very presupposition. No scientific approach to reality would be possible if at least research itself were not susceptible of a systematic organization in accordance with rules of its own, and only on a transcendentalist anthropology, that is, only by supposing that man is altogether alien to the reality he studies, might this reality be imagined to be lawless. 10.5. Conclusions. Positivists have demanded that the concept of causation be replaced by that of law. They have required that science forsake what Kant called Laufenrecht der causes, and they have imagined that science has already eliminated the common sense notion of causal influence, substituting the entirely different Denkmittel of law. 40. Some antipositivists, on the other hand, have held that lawfulness is insufficient, a causal connection having to be sought behind every law. An examination of the nature of scientific law has shown us, however, that science has followed neither advice, since it contains both causal and non-causal laws, as well as laws in which various categories of determination concur. The trend of recent science points neither to the decausation preached by positivism in favor of purely descriptive statements of uniformity, or to a return to traditional pancausalism. Present trends show, rather, a diversification of the types of scientific law, alongside of an increasing realization that several categories of determination contribute to the production of every real event. The stage of formulating causal laws is not the last, or even one of the most advanced, of research. It is usually followed by stages in which questions are answered in terms not only of causes, but of several other categories of determination as well. Theoretical physics became firmly established the day Newton rejected the scholastic precept of looking for causal explanations only, and realized instead that the chief, though not the sole, task of scientific theory is the discovery of the laws of phenomena whether or not the causal aspect is prominent in them. But this did not mean the replacement of causality by lawfulness, it meant instead an enrichment of determinism. Causal determinism became sublated in general determinism. Finally, scientific laws afford not only an economical, abridged description of phenomena enabling us to dispense with the repetition of observation or experiment, as Comte and Mach believed. Scientific laws, or law statements, being approximate ideal reconstructions of the immanent forms of structure and process, not only enable us to answer what dash, where dash, when dash, and whence questions, but also provide perfectible answers to whys. They are the chief tools of the scientific explanation of nature, thought, and society. But the problem of explanation will be approached in the next chapter. 11. Causality and scientific explanation. Scientific explanation has traditionally been regarded as causal explanation. The explanation of a fact was not usually deemed to be scientific unless its proximate and ultimate causes were assigned. Positivism reacted against this mistaken identification, which ultimately rested on the assumed identity of reason and cause. However, the reaction of positivism against causal explanation was not grounded on the limited range of causality but on the rejection of every sort of explanation, in favor of description. The thesis to be here defended is, again, neither the traditional nor the positivistic one, but a third position, namely, that answers to why questions need not be causal in order to be scientific, although causal explanation does constitute an important ingredient of scientific explanation in many cases. To this end, a cursory examination will be made of some types of explanation that are actually being used in science. But, before this is attempted, the question whether science should have an explanatory function at all will be treated. I1.1. Is science explanatory? It is worthwhile to recall briefly the story of the movement of reaction against the pain explanatory endeavor of rationalism, especially since that movement is far from simple, and is connected with the attacks on causality from a regressive standpoint. The explanatory function of science has been questioned from two opposite quarters. On the one hand, religious writers have usually held that scientific knowledge is powerless to 282. Causality and scientific explanation attain the primary or ultimate causes of things, whence it is vain. Skeptics, agnostics, and early positivists, on the other hand, have regarded speculations about trans-empirical and ultimate causes as vain either because, as consistent empiricists, they believed the whole reality to be such as it appears to us, or because they deemed the essence of things to be unattainable, or, finally, because, in harmony with the zeitgeist of an industrial era, they held an instrumental conception of science, seeing no profit in the search for ultimates. The positive character of science, as contrasted to the wild, obscure, and largely profitless speculations of medieval schoolmen and ulterior philosophers of nature, from the Renaissance down to our own day, consisted in accurate descriptions and predictions. The search for answers to why questions, regarded as an impossible or at least useless enterprise, was explicitly proscribed by the various kinds of phenomenalism. According to phenomenalism, the task of scientific research is to describe how things appear to us to happen, not why they happen thus and not otherwise. Faithful to this rule, Comte rejected the wave theory of light, an epoch-making scientific invention of his own time, on the bare ground that it provided an explanation of optical phenomena, more exactly, an explanation of the laws of symmetric optics in terms of higher-level laws. There is not a single kind of phenomenalism, or at least not a single intention, that may nourish phenomenalism. Thus Francisco Sanchez was a representative of progressive phenomenalism and agnosticism in the face of scholastic essentialism and dogmatism. On the other hand, Berkeley was a clear instance of regressive phenomenalism associated with dogmatism, and that not in the Renaissance, like Sanchez, but at the beginning of the Enlightenment. In Byrne, the young Kant, and the young Comte, the progressive aim of discrediting supernaturalism and unscientific speculation about matters that were successfully being handled by science was already mingled with the regressive attempt to put a priori limits on the scope of rational inquiry in general, and on scientific research in particular. With their strict adherence to the phenomenalist program that circumscribes the domain of 284. Scientific research to the positive description of what is immediately given, Comte and his followers have earned the name of negativists. By limiting the reach of research, curtailing the function of reason, and refusing to answer the most interesting questions, phenomenalism allied itself willy-nilly with the obscurantist trends. A tacit alliance was signed against the claims of rationalism and realism, the end of the long warfare between theology and science was proclaimed, and a division of the sphere of spiritual culture into non-overlapping domains was established. From the last decades of the 19th century on, in wider and wider circles science began to be looked upon, not as essentially the pursuit of truth and the attainment of understanding, but just as a means of control over nature and over man, as a summary of facts and as a technique for prediction, hence as an aid to action on the basis of sheer, uncommitted description. Science could be tolerated as long as it was assigned solely an instrumental, not a cultural value. A modus vivendi was possible as long as the reply to why questions was declared to be beyond the reach of science. The pragmatic attitude towards scientific research, the irrationalistic devaluation of theoretical knowledge facilitated by the ignorance of the role of hypotheses in science had captivated so many outstanding minds toward the end of the last century, that Mach could declare that only the relation among facts die Beziehung Dathatzi Gleichen is valuable, and this is exhausted by description. Lle Dantek stated that the best language is the one involving the fewest hypotheses and affording the fewest explanations. Tu Duhem, the Catholic positivist, wrote bluntly that the explanatory part of science is parasitic. 3 Petzold, the German follower of Mach, repeated the contention that there is no other explanation than a complete and most simple description. 4 Pearson, the British follower of Mach, went so far as to state that nobody believes now that science explains anything, we all look upon it as shorthand description, as an economy of thought. 5 More recently, Wittgenstein demanded that this attitude be taken by philosophy as well. There must not be anything hypothetical in our considerations. We must do away with all explanation, and description alone must take its place. 6 The partisans of the Princip der Denkokonomie put forward by Occam and reinvented by Mach 7 practiced it to such an extent that they failed to notice that the most economical of all procedures is not to think at all. It was William James who, with his deep insight, realized that an outcome of the pragmatic outlook was the revindication or at least the toleration of religious experience, alongside other kinds of experience. Although rank-and-file followers of positivism still believe that scientific explanation is nothing but unbiased, uninterpreted, hypothesis-free description, the explanatory function of science has become so obvious with the quick development of theoretical science that the most distinguished and open-minded neopositivist philosophers have recently been led to acknowledge that it had been a mistake to uphold a hypertrophied operationism entailing a radically anti-theoretical attitude and looking upon explanation as a metaphysical misfit. 9 But those logical empiricists who now admit the legitimacy of explanation usually restrict the philosophical problem of scientific explanation to that of its logical structure, leaving entirely aside the epistemological and ontological sides which this, like every other philosophical question, has, and to which I now turn. 11.2 Some aspects of the problem of scientific explanation. II.2 Conditions for an explanation to be scientific. The aim of scientific explanation is to render facts intelligible, that is, to rationalize reality, not, of course, in the psychoanalytic sense of rationalization. But obviously not every explanation affording what is loosely called intellectual satisfaction is scientific, Only general, meaningful, and verifiable ideas are involved in genuine scientific explanation. A factual hypothesis, that is, an assumption referring to facts, can be regarded as tested, verified, or confirmed, not proved beyond doubt, but verified to within a vague margin of uncertainty, if it meets at least the following requirements: I. The rational or logical condition of consistency, that is, of compatibility with the remaining propositions of the same theoretical system. Only partial consistency should be required, not consistency with the whole corpus of available knowledge, for the proposition, hypothesis, in question may happen to refer to a discovery invalidating some of the received ideas. Consistency, a mark of rational success, is also a temporary halt in the advancement of knowledge which, as Socrates is said to have discovered long ago, proceeds chiefly through the clash of internally consistent ideas and systems of ideas. 2. The material, factual, or empirical condition of satisfactory, not necessarily nor possibly perfect, adequacy to satisfactorily certified facts, sometimes called scientific facts, or facts under experimental control, in contradistinction to brute facts. Adequacy of factual hypotheses is tested by experiment and observations, but adequacy does not consist in empirical verifiability. Adequacy consists in correspondence, however incomplete, between propositions and facts. The condition of adequacy is to be fulfilled by the particular consequences of the principles, basic hypotheses, not by the principles themselves, which may have an objective counterpart but need not have an causality and scientific explanation empirical counterpart at the time they are formulated and, being general, are not directly verifiable. Both the certification of facts and the adequacy of a hypothesis to a class of facts are of course perfectible and even altogether infirmable, the contradiction between ideas and the facts to which they eventually refer being a further source of scientific progress. At least some of the explanans propositions involved in any scientific explanation must be capable of being submitted to an empirical test, if possible through prediction and, even better, through reproduction. But in order to be honored with the title scientific, a hypothesis need not have been verified already. What is peculiar to scientific hypotheses is neither truth, which some scientific hypotheses are assumed to share with some vulgar assumptions, nor infallibility, which is rather a mark of dogmatism, but logical consistency and empirical verifiability in principle. Verifiability means possibility of verification, and this entails both refutability and perfectibility, improvement of consistency and adequacy, and eventually extension of the domain of validity. The foregoing remarks should suffice, for the time being, as a general description of scientific factual statements. 10. I shall now proceed to a brief characterization of the logical structure and epistemological import of the explanatory statements of science. II.2.2. The logical structure and epistemological meaning of scientific explanation. Etymologically, to explain means to unfold, expose, or develop. The commonly received doctrine on the logical structure of scientific explanation is in agreement with the original meaning of the word. In fact, that doctrine holds that to explain a fact is nothing more than to show that the proposition, stating the fact is or are a particular consequence of one or more propositions of greater generality, eventually in conjunction with some items of specific information about the particular case in question. The concept of cause need not be involved in scientific explanation. Thus consider Leonardo's explanation of the downward direction of the fall of bodies. Every natural action is made in the shortest way. This is why the free descent of the heavy body is made towards the center of the world, because it is the shortest space between the movable thing and the lowest depth of the universe. 11. The explanans proposition is here a minimum principle, known from Hellenistic science, by no means a causal proposition. Now, the general propositions acting as explainers or premises in science, that is, the explanans propositions, are usually of that particular kind of hypotheses named law statements, are laws too. Hence, the scientific explanation of a fact consists, from a logical point of view, in showing that it is an instance of a general law. In turn, the scientific explanation of a uniformity or regularity will, when available, consist in its deduction from a higher level law, that is, in its subsumption under a statement of greater generality. I3 Thus, for example, Kepler's laws of planetary motion were shown by Newton to follow from the conjunction of his own law of motion and the particular law of force known as the inverse square law of gravity, both of which have a range of validity wider than Kepler's laws. Hence, from the standpoint of logic, to explain is to show the existence of an entailment or implication of the particular by the general. The object to be explained is thereby shown to be a member of a certain group, the idea to be accounted for is thereby shown to be somehow included in a previously admitted set of assumptions. Consequently, to the extent to which deduction may be regarded as tautological, explanation will be tautological as well, that is, from a strictly formal logical point of view, explanation produces nothing new. Nothing that was not in some way contained in a previously admitted system of ideas. In brief, the logical aspect of explanation consists in demonstration. Unfortunately or not, logic does not tell the whole story of knowledge. Explanation, like deduction in general, does add to knowledge, because actually the object to be explained was not previously contained in its class, or in its law statement, from the start, it was put by us in it a posteriori. The explanation operation is not a mere drawing of an element out of a given collection. From an epistemological point of view, explanation does not consist in the mere identification of an element of a class that is overtly displaying its characteristics before us. Explanation consists, rather, in the inclusion of the given object, fact or idea, in its class. And this is a constructive, synthetic operation, requiring the previous schematization of the given object, comparison of it with other objects, and so on. Now, at the level of formal logic, change does not enter, hence processes, like the epistemological one involved in explanation, have no place in deductive logic, which dispenses with the time concept and treats the actual processes of thought as laid down in an eternal present just in order to avoid contradictions between successives. In other words, what from an epistemological viewpoint is a real transition from ignorance to knowledge appears in formal logic as a purely analytic relation. Deduction, and in particular explanation, always entails a novelty in knowledge, and this is why we care to perform it. To put aside the non-logical aspects of explanation, by concentrating exclusively on its logical structure as is usual among contemporary empiricists, 14 is, I believe, a token of one-sidedness. Like every other exaggeration of logicism, the reduction of explanation to deduction has strange ontological and epistemological consequences. In philosophy, as in everyday life, to abstain from looking at facts does not eliminate them. Indeed, the view that scientific explanation is nothing but the disclosure of identity in the midst of difference, the discovery of like in unlike, the deduction of the particular from the general, such a view suggests a metaphysics holding the monistic belief that there must be one or at most a few universal essences, ultimate substances, fundamental laws, basic languages, or what not, to which everything must ultimately be reduced, freely trespassing on the boundaries between levels. It also suggests the odd theory that the advancement of knowledge consists in a progressive unification, reducing the apparent multiverse to an extremely impoverished universe depictable by a highly economical unified science. Such views have actually been held not only by traditional metaphysicians but also by modern positivists. To say the least, that is a one-sided view of the matter. The history of science shows that the number of law statements and of categories increases, that the number of fields of research increases as well, that the number of irreducible but eventually connectable concepts increases accordingly. A progressive differentiation, instead of a progressive reduction, is the sign of scientific advancement. But, just as in the case of biological and cultural progress, the very process of differentiation calls for an increasing integration of science, both ontological and methodological. In point of fact, there is evidence of an increasing unity of method, not excluding the increasing diversification of particular techniques and of a ceaseless discovery of new connections among fields that initially looked Separate connections which need not erase qualitative differences. The advancement of knowledge follows Bernard's law of biological progress, namely, plus l'organisme est lev / plus ilya de Verelt dans plus d unital. The increasing integration, or unity, of science should not prevent us from realizing its increasing diversification. In conclusion, the logical structure of scientific explanation consists in deduction from scientific laws in conjunction with particular items of information, or, what amounts to the same thing, the logical kernel of explanation is generalization, the process of showing that the fact in question fits a general pattern. But logic does not exhaust the analysis of scientific knowledge, nor is it the concern of formal logic to perform such an analysis. In order to complete the picture of scientific explanation, we must take a look at its ontological aspect, especially since a peculiar characteristic of scientific explanation is that some of the explanand's propositions in it are law statements that are supposed to have an ontological status, that is, laws too that are assumed to be correlated to laws law. I 1.2.3. The ontological basis of scientific explanation. Explanation of facts and explanation of laws. Usually a scientist does not feel that he has understood a demonstration if he has grasped only the logical mechanism of it, that is, the derivation of the result from the assumption, s. He may, on the other hand, feel that he has understood a derivation even if he has not looked into the detail of the logical chain, that is, even if he has neglected a number of steps in the process, which he often does purposely just to avoid getting lost in the formal net. Moreover, whenever a scientific explanation is summarized, the details of its logical structure are left aside, it is merely taken for granted that they have been taken care of, and what is required is a short presentation of the very stuff of the explanation. This actual procedure of scientists suggests that, in the so-called empirical sciences, explanation raises at least two philosophical problems, I, that of the nature of the materials, explanand's terms, out of which the explanation is built, 2, that of the logical relations among these materials. The reduction of explanation to deduction, or generalization, overlooks the very materials of explanation. The logical analysis of a given scientific explanation is able to ascertain whether it is formally, logically, valid, not whether it is materially plausible. The logical analysis of explanation is incomplete, because the explanand's terms are left unanalyzed in it. These explanand's terms, regarded as primitives at the logical level, constitute the object of an ontological analysis, to which I now turn. The object of scientific explanation may consist of a. Classes of facts, natural, mental, social, or b. Scientific laws themselves. For instance, empirical generalizations may be subsumed under law statements containing elaborate theoretical concepts. In either case, scientific explanation, in contrast to popular explanation, is performed in terms of laws. That this sort of explanation has an ontological aspect should be obvious except to those holding that both facts and laws are constructs. As an illustration of scientific explanation of the first kind, where the explicandum is a class of facts, consider the case of the recoil undergone by guns upon firing. This class of acts can be explained in two different ways, which are at first sight essentially different from one another. On a first level of explanation, we account for the recoil motion of the gun as being an effect of the equal pressure exerted in all directions by the gas generated in the chemical reaction started by the trigger. On a second level of explanation, the recoil is explained as being a mere instance of Newton's law of the equality of action and reaction. The former we are tempted to call a causal explanation, because it invokes an efficient cause, namely, the gas pressure. As to the second explanation, we are on the verge of terming it a rational explanation, as it openly consists in a deduction from a general principle. However, this dichotomy of explanation into causal and rational is like every dichotomy of scientific statements into purely factual and purely rational, or purely synthetic and purely analytic, too simple to be adequate. In fact, our first level explanation was incomplete, since it did not state that the cause, the gas pressure, is in its turn a result of the self-sustained, hence non-causal, chain. 293. Reaction initiated by the trigger in the explosive. Moreover, that explanation made not only a direct, explicit reference to a fact, the gas expansion, but also an indirect or implicit reference to a law immanent in that process, namely, the law of the isotropic distribution of gas pressure, in the absence of external fields. Hence, our first-level explanation was not simply an explanation of one kind of fact in terms of a further sort of fact, but included a reference to a law statement. In short, our first-level explanation is not complete insofar as it is exclusively causal, and it is as rational as the second-level explanation, since its logical structure is that of deduction. As to our second-level explanation, although it did not involve a direct, explicit reference to facts, it did appeal to the wide class of facts covered by Newton's third axiom, which is a physical, not a formal, principle. Our second-level explanation, which is manifestly a deduction, is not an explanation of facts in terms of pure reason, it is, again, an explanation in terms of a scientific law. First-level explanations are psychologically more appealing, hence didactically more effective, than second-level explanations, because their immediate referent is a further fact, but they are misleading as long as the concealed law is not noticed. There is no essential difference between the two kinds of scientific explanation. At both levels reference to facts and laws governing the same or related facts is made. Only, in first-level explanations the reference to facts is explicit, whereas the appeal to laws is implicit, which obscures the role of inference in it. Most explanations of historical facts seem to be first-level explanations in which the reference to law statements is concealed, which accounts partly for the current unawareness of historical lawfulness. 16, and in second-level explanations, the roles of facts and of law statements are reversed relative to the former case, which creates, especially among logicians, the illusion that scientific explanation is a purely logical affair. Let me now turn to the case in which the explicandum itself is a scientific law. Science seldom remains satisfied with the explanation of a class of facts in terms of a given set of laws. Either different explanations are tried or, to the despair of ultimate lovers, scientific laws are explained in terms of further, more general, laws. Moreover, there is no evidence that the process of finding the laws of laws may ever finish with the discovery of fundamental, ultimate laws, even less, with the disclosure of a single universal formula. Empirical generalizations are shown to follow from statements richer in theoretical concepts, as when Galileo's law of falling bodies was deduced from Newton's second axiom in conjunction with a specific assumption regarding the force function, and statements having a certain range of validity are subsumed under statements of greater generality, as when Newtonian mechanics was shown to be a limiting case of relativistic mechanics. Weakly explanatory, that is, mainly, though not exclusively, descriptive, laws are deduced from laws having a stronger explanatory component, as happened with geometric optics, which was deduced from the wave theory of light. Conversely, strongly explanatory laws may be subsumed under weakly explanatory laws, as in the case of the deduction of the laws of motion from a variational principle. The laws characterizing a given integrative level are explained as emerging from lower-level laws, as was the case of the laws of chemical binding, which follow from the laws of quantum mechanics, and so on. Science does not stop asking why laws are as they are. It does not, however, seek explanations behind laws, but in terms of further laws which, if believed to be final at a given moment in a given context, are called principles or axioms, that is, highest-level law statements. Science, then, does not remain contented with the phenomenalist dictum that there is nothing to be further understood about laws, as if laws were contingent, that is, as if they might have been different. Laws are logically contingent, in the sense that there is no logical necessity in them if torn out of the theoretical system to which they belong. A change in the HWS of nature or of society would not be illogical, that is, would not entail logical contradiction. Science is always looking after the sufficient reason of laws. 295. And ficit in still other laws. Nothing warrants the belief in ultimate first principles or absolutely fundamental laws, laws too may be fundamental in a given context or for a while, not absolutely or forever. By subsuming scientific laws under statements of greater generality, by deriving the laws characterizing a given level of reality from laws working at other levels, science tests the ontological hypothesis of the connectedness of reality, just as the variety and heterogeneity of the world is shown by the fact that an increasing number of qualities and systems of qualities, of laws and systems of laws, is continually being discovered. But it is high time to approach the problem of the relevancy of the causal principle to scientific explanation, that is, the question of the extent to which scientific explanation is causal. To this end, the types of scientific explanation may be grouped in the following classes: a. Explanations that may but need not be causal, and b. Those that are characteristically non-causal, in the sense that they do not involve the causation category. Needless to say, no attempt will be made to achieve an impossible completeness. 11.3. Explanations that can be causal. Let us examine some types of explanation in which the notion of causation may enter. An explanation will be scientific and causal if, besides being coherent and adequate in the sense explained in Sector 1 1.2.1, it invokes a causal law. A. I. Inclusion in a sequence of events or of states. Illustrations: A. The present month is September, because the last month was August. The law here invoked is the uniformity of sequence. September comes after August. B. Charlie's voice is now changing because he is entering puberty. The regularity serving as explanans is here the voices of almost all boys entering puberty change. The typical form of this explanation is B is thus and thus because it was preceded by A, and whenever A happens it is known or assumed to be followed by E. No genetic link need. 296. Be asserted in this sort of explanation, which invokes a mere sequence. This is a very rudimentary type of explanation indeed, but it is often sufficient, whether the antecedent can be regarded as a cause or not, that is, whether the explanation is causal or not. From the logical point of view, this kind of explanation often consists in an appeal to a definition, and consequently is tautological. Thus the definition September is the month following August, explanatory premise, entitles us to infer that the first day after August is over will be September I. But we are not interested at this stage in the logical structure of explanation, we are concerned with its ontological aspect, which in this case focuses on the concept of sequence, not necessarily of the causal type, not on the logical concept of definition. A. 2. Tracing of Genesis and evolution. Illustrations: A. A behaves the way he does because of his social origin and of his upbringing. B. Let us then suppose the mind to be, as we say, white paper, void of all characters, without any ideas. How comes it to be furnished? Whence comes it? By that vast store, which the busy and boundless fancy of man has painted on it with an almost endless variety. Whence has it all the materials of reason and knowledge? To this I answer, in one word, from experience, in that all our knowledge is founded, and from that it ultimately derives itself. I7 In this typically, though not exclusively, modern kind of explanation, the present traits of the explicandum are accounted for as a stage in its development. Laws of evolution, or of emergence, play here the role of explainers. In contrast to the previous kind of explanation, consisting in the inclusion of an object in a sequence, a genetic connection is here assumed whereby the raison d'etre of something is accounted for in terms of its production at a given time, and of its later development. As in the former case, however, a why question is reduced to a whence question, and the law to which reference, explicit or implicit, is made may but need not be causal. Illustrations: A. Iron rusts when in contact with air and moisture. B. Electrically charged particles, when approaching our planet, move along a helix owing to the magnetic field of the Earth. In this case, the given fact is connected, not with other facts of the same series, as in the two previous kinds of explanation, but with facts of a different order, and these act as the determinants, or codeterminants, of the change in question. Explanation is here achieved by placing the event concerned in what is assumed to be its actual context, or nearly so, a system of interconnections that had been overlooked before the explanation. This sort of explanation, which Whewell called colligation, is common in the socio-historical sciences, where the assumption of interconnections is instrumental in suggesting the search for events which available evidence has not yet established. Often, this kind of explanation is characteristically causal, since it may invoke agents acting extrinsically and uniquely, but even more often, it revolves around the category of reciprocal action, or reciprocal causation, since it consists in showing the existence of interdependencies, see Chapter 6. A4, Analysis OJ complex into simpler facts OJ same nature illustrations, A. Ampere's explanation of large-scale magnetic fields in terms of molecular currents acting as elementary magnets. B. Explanation of the working of complex mechanisms in terms of the functioning of simple machines. In this case, the given fact is explained as the aggregate or composition of simpler facts, usually on a smaller scale, which are either known or assumed to be known or simply forwarded as an untested conjecture. An essential point is that the explicandum and the facts acting as explainers shall not be radically different from one another. When they are, we get essentially non-causal explanations of types B, 4, and B, 5, below. A conspicuous subclass of this kind of account is that of mechanical explanations, consisting in decomposing complex events into changes of place of mass points, which may but need not be atoms. In contrast to the traditional conception of explanation as reduction of the unknown to the known, of the new to the familiar, the scientific analysis of complex into simpler, not simple, which involves an assumption about ultimacy, facts has sometimes just the opposite character, since it may be performed in terms of unperceivable hypothetical entities, sometimes called theoretical entities. Such was the atomic theory before our own century. Scientific analysis need not reduce the new to the old, the unfamiliar to the familiar, as reductionism requires. What it does is to reduce the complex non-understood to the simpler understood. I 1.4. Non-causal explanations, B, I, recognition, identification, or inclusion in a class illustrations, A, this body sinks in water because it is made of iron, and iron is heavier than water. B, that animal does not sing because it is a dog, and dogs do not sing. The typical form of this explanation is, if a thing is F, it is G, now, A is F, hence A is G. This kind of explanation might be termed taxonomic, for it essentially boils down to a classification, that is, to the inclusion of the class F in the class G, FCG. Causes are definitely absent from this sort of explanation, although further explanations, at other levels, might introduce the causation concept. B. 2. Description illustrations, A. The formation of images in optical instruments is explained by means of the laws of geometric optics. B. The functioning of heat engines is explained with the help of the laws of thermodynamics. By definition, the so-called phenomenological laws do not contain the causation category. Thus geometric optics regards light rays as stationary states rather than as processes, and the principles of conservation and of evolution, which stand at 299. The basis of thermodynamics, definitely do not refer to any causal agent. Despite the traditional opposition of description and explanation, the so-called phenomenological laws do serve explanatory purposes. We saw this in the case of kinematic laws, see Sector 10.3.2. In a sense, description is prior to explanation, in another sense it is a sort of explanation, though admittedly a superficial one. Sooner or later, truthful explanations enable us to frame more complete and more accurate descriptions. They may even suggest the existence of facts overlooked in descriptive statements. Pure description, unhampered by theory, unbiased by interpretation, entirely hypothesis-free, is a myth invented by traditional positivism, intuitionism, and phenomenology. Science ignores wholly uninterpreted facts. The very selection of facts is guided by theoretical principles, such as criteria of relevance, and by hypotheses of an explanatory nature. The interpretation of pointer readings is based on theoretical considerations embodied in the very building of the measuring apparatus. Even the wording of the so-called protocol sentences entails a host of assumptions about the relevancy of the factors usually present in every concrete situation. No scientific statement is meaningful outside a theoretical system. In short, science is both descriptive and explanatory, and description can be distinguished from explanation but not separated from it. b. 3. Explanation in terms of static structure laws. Illustrations. A. The raison d'être of every piece in a metal framework is accounted for by the place it holds in the whole. b. The differences among isomeric molecules are explained by the relative positions of the component atoms. In this sort of explanation, the given object is analyzed into entities which are shown to hold a certain place in a static structure, which place accounts for the peculiarities and functions of the whole. Nothing is here said of changes. 19. Hence, the causation category is not involved in this kind of explanation, which may be regarded as a subclass of a. 4, just that for which the connections are not causal. b. 4. Reference to a lower level. Illustrations. A. Molar properties of matter are explained as emerging from molecular behavior. b. Laws of mental processes are in principle explainable in terms of physiological laws. The object to be explained, the explicandum, is shown to be, or assumed to be, not the mere aggregate or sum of smaller scale facts, as in a. 4, but the outcome of qualitatively different events belonging to a lower level. A genetic but non-causal connection is thereby established among different domains. This sort of explanation is often referred to as a reduction. 20. This designation is misleading insofar as it suggests that the peculiar qualities of a given level are explained away by their connection with the properties of the underlying level. Every explanation is a reduction from a logical point of view, since it consists in the derivation of a particular from a general statement, but it is not always ontologically reductive, not, at least, unless the higher level entities are shown to be mere aggregates of lower level entities, without properties of their own. Genuine reductive explanations were dealt with above, under a. 4. b. 5. Reference to a higher level. Illustrations. A. The measured values of the atomic properties called observables depend not only on the atomic objects themselves but also on their interaction with the macroscopic apparatus with which the measurement is performed. b. The behavior of a member of a collection, molecule in a mass of liquid, limb or gland in an organism, individual in a community, depends strongly on the behavior of the whole. The figures, obtained by Correns, are in the proportion J32, 291, 14, or approximately I2, I. b. Statistical explanation of cross-fertilization. The reproductive cells of the TVO-kinds combine at random, hypothesis of randomness. The theoretical prediction of proportion is accordingly I2, I. This sort of explanation, often called organismic, consists in disclosing the place of the given object in a whole and in showing the reaction of the whole on the part. The synthesis, reconstruction of the whole, results from an analysis of the interdependence of the parts. The part-whole relation, not the causation category, is here at stake. b. 6. Statistical explanations. Illustrations. A. The equation of state of the ideal gas is explained by means of mechanical and statistical hypotheses. b. The distribution of hereditary characteristics in certain populations of living beings is explained by means of Mendel's laws, see Fig. 30. Statistical explanations consist, essentially, in showing that the given object is a member of a statistical population or of a 302 stochastic process. It is a widespread opinion that statistical statements are purely descriptive, that they are in need of being explained, without being entitled to perform an explanatory function. Now, it is certainly desirable to find explanations of statistical laws, but, then, of every other type of law as well. Statistical explanations are satisfactory at their own level, and are peculiar to modern science. To exclude statistical explanations would be as unwise as to declare them to be final. b. 7. Teleological explanations. Illustrations. A. Gastric juice and saliva are secreted by man when he sees a tasty dish or hears a description of it. In the case of a Pavlov dog, when it hears the sound to which it has been conditioned, this secretion takes place as a preparation for possible future digestion. b. Certain wars are consciously planned in order to prevent economic crises or placate social uneasiness. No one seems to have afforded convincing grounds for doubting that human conscious behavior is purposeful or goal-directed. The controversial point is whether unconscious end-seeking functions and activities can be found at the level of life. What is not usually denied is that, in contrast to physico-chemical processes, many plant and animal functions and behaviors are not indifferent to the end result but occur instead as if they were somehow directed by it. They are actually determined by the immediately previous states and by the whole past history of the organism, as well as by its environment. Organs, functions, and behaviors could not be determined by future, still non-existent needs. They are presumably determined by past and present conditions and are adapted beforehand to coming conditions, though not with foresight or conscious planning, but as a result of a long and blind past history of successes and failures. In the case of the conditioned reflex-producing secretion by certain glands, the sound, stimulus or efficient cause, initiates or triggers, but does not produce, the entire process. Moreover, the process anticipates another function, digestion, which, after all, may not take place. Whatever the real nature of the causality and scientific explanation nexus stimulus, cause, response, effect, may be, it certainly is not a direct causal link. And as soon as physiology and psychology attempt to go beyond simple schemes of the stimulus-response type, as soon as they try to explain the whole process between the observable cause and the observable effect, they transcend not only the frontiers of phenomenalism, for example, behaviorism, but also those of causality. The largely non-causal character of biological processes is realized when it is understood that, within a wide, though limited, range, they are independent of the precise environmental conditions, and even of the particular means or methods employed to achieve goals, such as self-preservation, that are comparatively stable. 21 life processes are eminently self-determined and historically pre-adapted. Far from being the passive toy of its environment, the organism seems to select actively the most favorable conditions for the attainment of its ends: preservation, development, propagation. It should however be emphasized that teleological laws are statistical, in the vague sense that organisms do not always succeed in fulfilling their ends. Teleological laws are consequently deprived of the necessity, uniqueness and regularity, claimed by vitalism, and characteristic of causal laws. Whether teleological explanations will be retained in future biology and psychology or not, cannot, or should not, be foretold. The fact is that teleological explanations have not been diminished from these branches of science. What modern science has done in connection with teleology is not to discard it but rather to deprive it of supernaturalistic overtones, to confine it to the higher integrative levels, and to show that even there it is insufficient and, moreover, that teleology is often replaceable by other categories of determination. So far as I know, modern science has not proved that inner finality, or immanent finality, in contrast to transcendent design, is a myth. It may be a mistake to dispense with teleological explanation just because in the past it has been associated with anthropomorphism and theology. The unscientific attitude toward teleology is to regard goal-striving activity as ultimate, unexplainable, or supernaturally directed. The present task of science, in connection with teleology, does not seem to consist in denying it a priori but in trying to explain the laws of goal-adapted organs, functions, and behaviors, in terms of evolutionary laws, feedback processes, and so forth. It consists, in short, in explaining teleological patterns in terms of other laws of nature, thereby extruding the notion of design from biology once and for all. It is even likely that teleological laws will not be replaced but will be explained by other laws, that, for example, they will be shown to have emerged in the course of the evolution of organisms and associations of living beings. Although the individual organism may not as yet have gone through the end state that is coincident with the attainment of the goal, its ancestors have, and this experience may have been preserved for the species by the mechanisms of selection and heredity. Teleological laws will perhaps be explained as a new mode of behavior of material systems, resulting from a long past process of trials and errors in the adventure of adaptation, and stabilized by the mechanisms of heredity. Scientific philosophy does not require the extrusion of teleological explanations in connection with the higher integrative levels, it demands merely the avoidance of the obscurantist interpretations of teleological patterns in terms of immaterial and unintelligible entelechies, such as those imagined in the early days of biological and psychological research. b. 8. Dialectical explanations. Illustrations. A. The composition of atomic nuclei is the result of the conflict of two opposing tendencies, the equalization trend stemming from the conversion of neutrons into protons, and the reduction of the proton number owing to electrical repulsion. b. In the process of demonstration the thinker splits himself into two and seats, he contradicts himself. Causality and scientific explanation, and only after having stood and overcome this inner opposition is he a demonstrator. Point 22. Typically dialectical explanation consists in the disclosure of the inward and outward conflicts that keep certain, not all, processes running, or that bring about the emergence of entities endowed with new qualities. Although dialectical explanations employ several other categories of determination, such as interaction and causation, they have peculiar characteristics that cannot be explained away. 11.5. Conclusions. In order to ascertain whether a given explanation is causal or not, its logical examination, that is, the analysis of its logical framework, is not only insufficient but also irrelevant. An explanation can be called causal provided the causation category lies at the center of it, and this is not a logical but an ontological question, or, more precisely, this can solely be decided upon an examination of the ontological referent of the explanand's proposition, s. Therefore the logical empiricist analyses of causal explanation, restricted as they are, when they acknowledge explanation and causation at all, to the logical aspect of the question, are all insufficient. Insofar as they are correct, they apply to all kinds of scientific explanation, and therefore they do not enable us to discern causal from non-causal explanation. A succinct ontological examination of current types of scientific explanation has shown us that there are many ways of understanding, that is, of answering why questions, the disclosure of causes being but one of such ways, or, rather, a conspicuous but not universal component of scientific explanation. 8 types of scientific explanation based on non-causal laws have been listed in the preceding section, but a closer examination should yield even further types of explanation, in which no reference is made to the causation category. To assume or to require beforehand that every scientific explanation be couched in causal, or in statistical, or in dialectical terms does not seem much wiser than the procedure of the shaman who asks the complex question, which are the evil spirits dwelling in this sick man? As a consequence, it is not possible to retain the identity-causative ratio. Contrary to the traditional teaching, causality is not a sufficient condition for understanding reality, although it is often a component of scientific explanation. Moreover, causal explanation, if scientific, will not be found beyond scientific laws 23 but in the laws themselves, as it is characteristic of scientific explanation in general to be made by means of laws, some of which have a causal component while others lack it. Scientific explanation is, in short, explanation by laws, not necessarily explanation by causes. What lends causal explanation a delusive majority over the remaining types of explanation is that most explanations are framed in a causal language. Thus in English most explanatory statements contain the word because, by cause, they are, indeed, of the form Q because P, save teleological explanations, which usually have the form P in order that Q. To fall into linguistic traps like this one is a sign of naivete, but it is also a mark of philosophical candor to conclude the bankruptcy of causality from the undeniable fact that the statements of particular scientific laws do not usually contain the words cause and effect, which designate philosophical categories. Now a test of scientific hypotheses, whether causal or not, is prediction. Prediction, backward or forward, is, indeed, a touchstone of the factual adequacy of theories, just as theorems are the touchstones of the logical consistency and fruitfulness of axioms. Let us then proceed to inquire into the place of the causal principle in scientific prediction. We shall now examine the nature and function of scientific prediction, in order to ascertain whether successful forecast requires the knowledge of causal laws, as is usually assumed, and whether successful prediction is both the meaning and the criterion of causality, as is often maintained. It will be shown that there are several kinds of prediction, scientific prophecy by means of causal laws being only one of them, whence both the traditional and the positivistic solutions of the problem of the relevance of causality to prediction, and vice versa, are inadequate. 12.1 Nature and functions of scientific prediction. I2. Nature of prediction. According to law, scientific prediction may be defined as the deduction of propositions concerning as yet unknown or unexperienced facts, on the basis of general laws and of items of specific information. It has rightly been pointed out that the logical structure of scientific prediction is the same as that of scientific explanation. In fact, both are consequences of the conjunction of laws and particular pieces of information. A theory can predict to the extent to which it can describe and explain. But the identity in logical structure between prediction and explanation does not entail an identity in nature or kind. Prediction is epistemologically not the same as description and explanation because, as everyone knows, prediction is usually affected by a peculiar uncertainty of its own. Descriptions are 307. 308. Never complete, and explanations are never final, because an unlimited number of variables always escape us. The uncertainty of prediction stems partly from the incompleteness of description and explanation, but in prediction an additional uncertainty appears, namely, the one associated with the unexpected emergence of novelty. The most careful prediction may fail to foresee important novelties that would not remain unnoticed in an accurate description. As the saying goes, it is easy to be wise after the event. In other words, the difference between description and prediction is simply due to the fact that the event that is predicted need not be the same as the fact that is described. To put it even more briefly, there is knowledge but not foreknowledge. True, the uncertainty that characterizes prediction could be removed or decreased if more complete knowledge of the relevant or significant variables, laws, and specific data were at hand. But the fact is that satisfactory descriptions and explanations are often attained with the help of a fixed and even small number of laws and data, which may however be found insufficient for an equally satisfactory prediction. In this sense, every specific problem in description is closed, whereas every prediction problem is open, just because of the provisional closure of description. Prediction is, then, epistemologically quite different from description and explanation, even though the logical structure of prediction is the same as that of explanation. 12.12. Predictive nomological statement, a third level of meaning of law. The consideration of causal laws affords a clear illustration of the difference in kind between scientific explanation and scientific prediction. In point of fact, on the basis of causal laws, or partly causal laws, we can frame causal, or partly causal, explanations but very seldom predictions that are causal to the same extent, for most predictions about the empirical verification of laws, whether causal or not, have a statistical ingredient, such as the statement of the probable error. Moreover, quantitative predictions, such as those of future positions on orbits, are always partly statistical, since the estimate is incomplete unless the probable error is assessed. As a compensation, Statements of laws 2 for purposes of verification, prediction, or application may have a causal component that was absent in the corresponding laws 2. This is the case whenever we are able to control some of the variables related by the law under consideration, provided the relation is unambiguous. The set of variables under experimental control we may call the causative. By changing their values in a prescribed way, a given effect is invariably produced in a unique way, without in turn appreciably influencing the cause. But this will not be enough to warrant that the relation concerned, that is, the law 2, is itself a causal one. To this end, we have to prove that, by choosing the complementary set of variables as parameters under experimental control, that is, by handling the former effect as a cause, a different connection will obtain. If the same connection obtains, it cannot be termed causal, for, being reversible, it lacks the essential unidirectionality of causation. And such a proof will often fail. Most connections are, in fact, symmetrical, hence non-causal, functional dependences, that is, they do not alter if the cause and the effect are interchanged. As Campbell 12 wrote in connection with the process of verification of a functional relation of the type y equals x, the law states a relation which is not that of cause and effect. Although it may be established by observing such a relation, there is a distinction between the meaning of the law and the evidence on which it is asserted. The foregoing considerations suggest rendering explicit a third meaning of the term law, besides the two recorded in Sector 10. Namely, the form taken by law statements, laws 2, when used for predictive and other purposes connected with experience. We thus have three levels of meaning of law: objective pattern, LOL, conceptual reconstructions thereof, laws 2 or theoretical laws, and adaptations of laws 2 to their empirical verification or practical use, LAWSA. Reality, its theories, and the empirical verification of the latter are thereby accounted for, see Fig. 3i. The mere fact that a neat distinction must be drawn between law statements, laws 2, and their adaptations to practical purposes, LAWSA, is, by the way, a strong argument against the pragmatic, or operational, principle according to which the meaning of a proposition is the mode of its verification. The nature of scientific prediction will be further clarified through an analysis of its functions, to which I now turn. I 2.1. 3. Functions of scientific prediction. The function of prediction I twofold. A. It is a forecast of some kind, whether like those of astronomy or the statistical sort, and as such an indispensable aid to successful human action and control. B. It is a test of hypotheses, for by means of prediction we confirm or disconfirm scientific assumptions. Prognosis is a test of both the diagnosis, description, and the causality and scientific prediction. 3.2 Etiology, in the wide sense of explanation, whether causal or not. Prediction is then both practically and theoretically important. Moreover, these two features of the question are mutually dependent. In fact, a forecast will be successful to the extent to which it is made on the basis of sufficiently true law statements and specific information regarding the particular case in question. In turn, as pointed out above, a test of law statements, and of the items of information involved in the framing of the corresponding laws 3, will be the successful prognosis formulated with their help. Hence, although prediction is a very important task of science, the most cursory examination of its functions shows us that it cannot be more important than either description or explanation, on which prediction rests and on which it reacts. Prediction is as important as description and explanation. To assert that prediction is the most important task of science, as positivists and pragmatists have held, shows a strange lack of acquaintance with the life of science. Successful prediction is of course verified, or refuted, by means of observation, experiment, and artificial reproduction. Reproduction, such as is performed in industry on the basis of technology, is the optimum test of prediction, since it requires the control of the most relevant variables. But, of course, reproduction is not always possible. Moreover, it is hard to ascertain when reproduction may be regarded as crucial, that is, as affording a definitive confirmation or refutation of a given set of hypotheses to the extent to which there is anything definitive in empirical matters. Furthermore, the fact that successful reproduction is the best test of prediction does not mean that making entails knowing, that is, it does not mean that, if we know how to produce or reproduce a given thing or phenomenon, we know all there is to know about it. The atom bomb was made with the coarsest nuclear theory. Making is not knowledge and does not entail exhaustive knowledge. Making is a test of knowledge, it is not the sole test and it does not afford the last word, but it is, undoubtedly, the best test. 312. However, our concern is not prediction in general but rather the various kinds of scientific prediction. 12.2. Kinds of prediction. According to a widespread prejudice, a single sort of forecast is entitled to be called scientific, namely, the highly accurate quantitative prediction of future events, such as those based on the laws of classical mechanics or classical electromagnetic theory. 3. This view is outdated. There are many kinds of prediction, actually as many as there are kinds of scientific law, on which scientific prophecy is based. Although the last statement is merely a consequence of the definition of prediction adopted in Sector 12. It will be convenient to insist on this point just in order to show that our definition does cover the actual usage of the word prediction in contemporary science. To this end, let us examine the kinds of forecast afforded by some types of scientific law or, if preferred, the kinds of extrapolation allowed by them. Consider, in the first place, taxonomic rules, the simplest of all from a logical point of view, since they assert mere generalizations. They are of the form every A is A, where A stands for a class and A denotes either an individual or a subclass of A. An elementary illustration of this kind of law is all birds are warm-blooded, that is, the class of birds is included in the class of warm-blooded animals. This inductive statement enables us to predict, with probability near certainty, for that the next bird we catch will be warm-blooded. A more distinguished example of a taxonomic law enabling us to perform scientific predictions is Mendeleev's periodic table of the elements. Taxonomic rules enable us to predict, sometimes with a high probability of success, that every next member of the given class, or every next subclass, that we meet will have the qualities typifying that class. The word next need not refer, in this context, to the objects themselves, that is, to a future state of theirs. It may refer solely to the predictor himself, as is the case with the empirical generalizations of paleontology, archaeology, history, and so on. This kind of forecast does not consist in the accurate prediction of any numerical values referring to future events, but it is nonetheless scientific, since, far from being a blind guessing, it is a grounded and testable inference. Next come structure laws. For example, the existence of some light isotopes was predicted on the basis of the assumed structure of their nuclei. A certain set of hypotheses concerning this structure permits the formulation of the following rules, all of which can be used to predict the formation of isotopes. All stable nuclei up to 016 are obtained by adding a neutron and a proton in succession, in the order NP, and from 016 up to 36 the isotopes are obtained by repeating the sequence NNPP. There are a few exceptions to this rule, such as He5. This shows that something is wrong with the basic hypotheses concerning nuclear structure, but this lack of completeness and certainty is precisely a mark of scientific knowledge, as contrasted with revealed formulas. Here again, prediction is not an inference from present to future, but from known to unknown. Structure hypotheses, as well as taxonomic rules, laws of colligation, and so forth, enable us to forecast the existence, or the absence, of certain things and properties, whether in the future, the present, or the past. In this sense they are much more important than many accurate quantitative predictions. Then come the so-called phenomenological laws, such as those of geometric optics, thermodynamics, and pre-Newtonian astronomy. For example, if the refractive index n of a transparent body is known, either from previous measurement or from other physical characteristics linked to it in a known way, and the angle of incidence I of a light ray is measured, the Snell law sin H/sin R equals n enables us to predict the angle of refraction. 314. R of the ray. Note that time does not play a role in geometric optics, nor does it in the thermodynamic theory of equilibrium states. This shows that, contra to a popular belief, scientific prediction does not require law statements asserting that certain events will follow other events according to prescribed time patterns. Prediction on the basis of this particular kind of law is just a kind of scientific prophecy, not its prototype. Time does, however, enter the phenomenological laws of pre-Newtonian astronomy, such as Kepler's second and third laws. In none of these cases have causal laws been at stake, yet accurate predictions were shown to be possible. Let us now approach prediction on the basis of time patterns, which is usually, and wrongly, believed to be the sole kind of scientific forecast, or at least its paradigm. Laws of development in time, which may have a causal component or not, can sometimes be expressed in a mathematical form. The simplest types are, Jx_jt equals f, t, finite difference equation, dx dt equals f, t, ordinary differential equation, 8u at equals f, x, t, partial differential equation, f, t, equals u, t, 2, f, 2, operator equation. Such formulas are needed in order to predict the precise future, or past, values of a certain variable at a prescribed time. They are, together with knowledge of initial or boundary conditions, necessary for the formulation of this kind of prediction, but they are not sufficient. An additional condition is that the equation concerned actually has solutions for the prescribed time, and this is not obvious but must be demonstrated. 5. 6. For instance, the general solution of the partial differential equation OOAI plus IA equals O is U, X, T, equals len exp, inx plus nt, and this series converges for t dot 0 only, thus rendering retrodictions, but not predictions, possible. However, as should be clear from the previous examination, this sort of prediction is the exception in science rather than the rule, despite which it is practically the sole one dealt with by philosophers of science. 6. The reason why we are able to predict even without the help of law statements containing the time variable is a truism, namely, that in such cases it is our knowledge that undergoes a change in time, whether that knowledge refers to a process or not. Let us now take a look at statistical prediction. 12.3. Statistical prediction. 12.3.1. Insufficiency of prediction of individual events. The fact that certain astronomical predictions have been and are still regarded as the model of scientific prognosis, because of their numerical accuracy, and because they have been the sole reliable ones for millennia, has had two opposite effects. On the one hand, it has fostered research in other sciences, on the other, it has spread an erroneous notion of the nature and function of scientific prediction, and consequently an incorrect idea about what are the disciplines that can be honored with the title of science. Astronomical predictions based on laws of motion should not be regarded as the type of scientific prediction, but rather as a highly exceptional case favored by the extreme mechanical isolation and stability of the solar system, as well as by the large interplanetary distances. These conditions are almost ideal. They are the furthest from the ordinary conditions met with in science, and they account partly for the early development of astronomy. Even so, if we asked the exact position of our planet 1 billion years hence, no astronomer royal would venture to give us an accurate answer, even assuming that no qualitative changes were to occur in the meantime, tidal friction, random perturbations from other celestial bodies, and the very errors. 6. Thus Destouches, 1948, La mécanique ondulatoire, Chapter 7, and Quelques aspects théoriques de la notion de complémentarité, Dialectica 2, 351, 1948, has built a general theory of predictions based exclusively on time patterns of the above-mentioned types. In the estimate of the present values of the Earth's position and velocity, initial conditions would suffice to blur completely the future values. This problem is similar to that of asking about the exact result of a roulette wheel after a sufficiently large number of turns. The answer is that all final positions are equally likely. Moreover, modern astronomy makes extensive use of statistical methods in the exploration and classification of heavenly bodies. It also uses the theory of probability in the study of large collections of stars qua collections, and even in problems connected with individual bodies, such as comets, which are then regarded as members of a potential collection, since the probability concept is a set property. As far back as I-816, Laplace published a study entitled Sur les comfits, in which, by means of probability considerations, he tried to account for the observed frequency of elliptic and hyperbolic comet orbits. This kind of study, based on definite physical and statistical hypotheses, enables us to explain observed facts, such as frequency ratios, and to estimate the probability that the next member of the collection will have such and such characteristics, for instance, that it will move along an elliptic orbit. But the chief use of statistical laws, established either empirically or on the basis of hypothetical models, is not the prediction of the probability of occurrence of individual events. Their chief importance, as far as prediction is concerned, lies in that they help in foreseeing collective properties, that is, properties of large collections of entities that are similar in some respects. Among other things, statistical laws enable us to predict probable frequencies, inferred from probabilities that are handled without any uncertainty, averages, mean deviations from the mean, degree of association, statistical correlation, among causally disconnected entities, the most probable trend of a course of events, and so on, see Fig 32. 12.3.2. The statistical predictions OJ the sciences of man. A popular argument against the scientific character of anthropology, sociology, history, and related disciplines is that socio-historical sciences are seldom capable of predicting. If it is implied that the required prediction be of singular events with precise indication of place and time, then it can easily be granted that such a sort of prediction is rare in the field of the so-called cultural sciences. It is also easy to see why this is so. Most socio-historic laws are statistical, see Sector 10.4.5, and statistical laws are simply not supposed to permit the formulation of precise predictions about singular events. The word statistical, in connection with socio-historical laws, means not only that they cover mass phenomena, but refers also to the uncertain character of the predictions of singular facts attained on the basis of such laws. 318. Thus one of the goals of anthropology, in the large sense of the word, is to predict or indicate the general directions of change likely to be taken by the phenomena under consideration. The proper sphere of anthropology as a science is therefore to strive to secure historical, sociological, and psychological laws that describe overall trends or processes among the peoples of all prehistoric and historic periods. 7 general predictions about overall trends, which are typically statistical, can be and have been made on the basis of socio-historic laws. On the other hand, it is next to impossible to predict particular historical events with accuracy. For instance, Marx's hopes for an early social revolution in England did not come true. On the other hand, he certainly succeeded in predicting some general features of future developments. 8. It is no wonder that he failed in the forecast of singular historical events while he was able to predict some of the main traits of the world we live in: large centralization of the means of production, increasing participation of the whole of society in production, decadence of colonialism, growth of socialism, and so forth. To this end, Marx relied on a few sketchy law statements concerning the economic structure of the capitalist society, which have only a statistical validity, so that they permit the prediction of what is likely to occur in the long run /v wherever certain conditions are met. Likewise, the Mendelian laws of heredity do not enable us to foresee with certainty the appearance of a given hereditary trait in a prescribed offspring of Ps at a prescribed time, and this, just because they do not refer to individual events and because they do not contain the time variable. Scientific prediction cannot transcend the scope of the law statements on which it is based, and it cannot be more precise than the specific information that it uses. This is precisely what essentially distinguishes scientific forecast from popular prophecy. A further difference between prophecies and predictions is that the former are unconditional and can consequently be couched in categorical statements, such as peace will break out. Scientific predictions, on the other hand, are formulated al. hypothetical statements exhibiting the conditions required for the occurrence of the event under consideration, as in peace will break out if such and such conditions are fulfilled. The ground of this logical difference is that whereas prophecies do not rely on laws, scientific predictions do rest on them. In short, scientific prediction is lawful. Consequently, if scientific laws are employed in an incorrect manner for predictive purposes, the user of them and not the laws themselves must be blamed. 12.3.3 Are statistical predictions less complete than others? The complaint is often heard that statistical laws are incomplete, in the sense that they do not allow us to infer with certainty what individual events will happen at a prescribed place and time. Thus, from the birth rate in a given country we cannot derive the birth date of a given individual. That statistical laws are incomplete in this sense, and that they should consequently be supplemented with laws of a different type, is easy to grant. Yet, statistical laws are no more incomplete than other kinds of scientific law, only, their incompleteness is of a different kind, and this is all. In fact, all kinds of law statements, laws 2, permit the framing of predictions, instances of laws 3, that are both qualitatively incomplete and quantitatively inaccurate. The difference between the sort of prediction afforded by the various types of scientific law is a difference in kind rather than in degree of completeness or accuracy. Thus Newton's laws of motion, usually regarded as the paradigm of scientific law, will not tell us much about the overall behavior of a group of, say, 1,000 stars, whereas a statistical mechanical treatment of a star cluster, that is, a model of it in which every star is regarded as if it were a molecule in a mass of gas, may lead to certain accurate prognoses. For example, the disintegration rate of a star cluster may be derived by applying Maxwell's statistical law on the distribution of velocities. Statistical predictions can be, generally speaking, as certain, or uncertain, as every other kind of prediction. They do not refer with certainty to individual events, but as a compensation they refer to collective properties, that is, to overall behavior or long-run characteristics. 320 The function OJ the causal principle in science. The claim that statistical laws, in contrast to other kinds of scientific law, are incomplete, hence provisional, is largely a matter of metascientific inertia. It is a heritage of the 18th and 19th centuries, when it was commonly thought that the progress of science consisted in a close imitation of mechanics and astronomy, the predictions of which were deemed to be the sole decent kind of prophecy that science should afford. In contemporary science and technology, and even in everyday life, we often ask questions that simply cannot be answered on any individual or dynamical laws, questions requiring a statistical approach and analysis. And this is so because they refer to events that occur, to a large extent, no matter what the precise behavior OJ the individual components OJ the collection under consideration is. Thus an insurance company is not interested in the precise date of the death of every one of its clients, for the whole insurance business is based on the knowledge of certain statistical laws with the help of which the premiums are calculated to calculus that amounts to a statistical forecast. Even if complete information is available, statistics is not a dispensable luxury. 9 Statistical laws are patterns of collective behavior, and such behavior is not rendered any the less real and peculiar when the detailed behavior of the parts is known. If we are able to answer questions about statistical populations that individual or dynamical laws cannot answer, why should we continue to describe statistical laws as less complete than other kinds of law, which do not allow us to formulate predictions about overall or long-run behavior? Statements were a faithful reflection of reality, and they never are. They would not be enough to formulate predictions, whether accurate or not. Law statements have to be supplemented with specific information such as initial or boundary values, past history over a stretch of time, constraints, and so on, and the limited precision with which this specific information is known is always a source of error, see Sector 1 2.4.3. Consequently, the causal nature of a scientific law does not warrant the certainty of the predictions attained with its help. On the other hand, certain statistical laws allow us to attain near certainty. Thus, the second law of thermodynamics may be interpreted as stating that it is almost impossible for the entropy of a closed molar system to decrease. And the analysis of so simple a mechanical system as the one consisting of two uncoupled linear oscillators with phases standing in an arbitrary ratio to each other shows that it is likewise almost impossible that a given configuration of the system be repeated, whence it may be concluded that eternal recurrence is nearly impossible for an aggregate with a finite number of independent, or nearly independent, components i.o. even if they constitute a mechanical system, in which no qualitative change can occur. An event of probability unity is almost certain to happen, that is, it will happen almost always, and an event of zero probability will almost never happen, although it is not impossible. In this context, the word almost means that there may be exceptions, and even infinitely many, but such that they do not accumulate and are so rare compared with the alternative events that they have no appreciable quantitative influence. Such exceptions do not affect the stable values of the relative frequencies, although they may give rise to qualitatively new things, a problem that does not concern the theory of probability. In technical language, that is expressed by saying that the exceptions constitute a zero-measure set, because they form a denumerable sequence. This lack of overlapping of the frequency, which may not vanish even if the probability is exactly zero, and the probability is but an illustration of the incompleteness of the correspondence between the world of experience, to which frequencies refer, and its reconstruction in THIRD-WORLDism, a conceptual system in which the concept of probability may take part. In short, in the extreme cases of zero and unity probability, statistical laws lead where causal laws lead only exceptionally, namely, to prediction almost with certainty. 2.4.2. Almost necessary truths of fact. In some cases, the degree of certainty corresponding to zero and unity probability, which are interpreted respectively as near certainty of failure and near certainty of occurrence, can be attained without resorting to either causal or statistical laws. Thus, on the basis of the functional and teleological laws of human physiology, we can predict with almost complete certainty that no child lacking a heart will survive its birth. This prediction is not made on the basis of empirical evidence regarding past cases. If it were, it would be open to the usual objections against inductive generalizations. The empirical knowledge of the zero frequency of children without hearts surviving their birth rather supports a posteriori the prediction. In fact, the prediction is a result of our knowledge of the central role of the heart. It is the understanding of the heart's function, rather than any empirical generalization, that permits us to attain such a certainty. Before Harvey's discovery of the nature of the heart's function, the eventual empirical finding of the zero frequency ratio of surviving children without hearts would not have guaranteed the prediction of the death of every next such baby. We can often ascertain a priori, not so much the necessary outcome of an event, as its being next to impossible, on the ground that its occurrence would violate certain well-established, though still hypothetical, laws of nature. For example, the laws of the strength of materials enable us to predict that no arbitrarily high column can be built, although the height at which collapse would take place would only be estimated to within a certain error. And the physiology of the nervous system allows us to infer, with the same certainty, that nervous, hence psychic, functions cease with bodily death. So, causality and scientific prediction that survival of the soul is out of the question. Do these instances of almost necessary synthetic truths refute the traditional claim of both Platonic idealism and skeptical empiricism, that no certainty can be attained in factual and, particularly, in empirical matters? That is, do these examples refute the thesis that every general proposition having a factual, or an empirical, content is at best a probable hypothesis? No, they do not refute it, but they qualify it considerably, as we shall see presently. Skepticism about the possibility of attaining anything near certainty in empirical affairs was amply justifiable at a time when most reliable scientific knowledge of the external world was little more than a heap of empirical generalizations, that is, general propositions supported solely by their favorable instances. Moreover, such skepticism played a progressive role in the fight against nativism, which claimed that everyone has innate true ideas with factual reference, that is, self-evident truths of act having a necessary character. That time ended in 1687 with Newton's Principia, in which experience and reason were firmly united for the first time, and in such a way that it became possible, so to speak, to calculate facts. From that time on, the ideal type of scientific statement is no longer the empirical generalization but the universal law containing some elaborate theoretical concepts and supported, not only by its instances, but by other laws too as well, so that it stands or falls together with a whole bundle of hypotheses. In fact, hypotheses belonging to theoretical systems are not confirmed or invalidated as if they were isolated statements. The test of them strengthens or weakens entire frameworks of ideas referring to facts. This does not change the fact that all general propositions with a factual content are more or less probable hypotheses, but it introduces the important novelty that universal law statements are not all equally probable. Some of them are almost certainly true and others almost certainly false. Contrary to what Kant held, this certainty, actually, quasi-certainty, in empirical matters is not grounded on a priori principles, whether logical or intuitive, but upon the rational reconstruction of experience. It is theory, including the theory of experiment, rather than either pure speculation or pure. 324 The function OJ, the causal principle in science, empirical generalization, that enables us to set forth some almost necessary truths of fact or, if preferred, some rational truths OJ factae, name that in a way typifies the most advanced sections of modern science, which have gone beyond both rationalism and empiricism. Neither experience by itself nor pure mathematics has led us to attain certainty in factual matters. In this sense, the quest for empirical certainty has come to naught. But the theoretical sciences of nature, and, let us hope, of society as well, are rendering the quest for near certainty meaningful, dispelling the paralyzing ghost of equally probable hypotheses. 12.43 Grounds for the failure of specific predictions. Scientific laws do not enable us to draw completely safe inferences about the future course of physical or cultural events, and this, quite independently of the presence of the causation category in the law statements concerned. The reasons why a scientific prognosis may fail fall rather naturally into three groups. They may be connected with the law statements themselves, or with the complementary specific information, or with the process of inference. In more detail, the sources of uncertainty in prediction are essentially the following: I. Errors in the law statements or in the choice of them. A. The statements of the laws are incomplete or inaccurate, incompleteness or sketchiness referring to qualities, inaccuracy to quantitative precision, that is, our knowledge of the objective laws that are relevant to the fact, under consideration is too sketchy or inaccurate. B. Some of the laws themselves fail, that is, they cease to apply owing to the emergence of qualitatively new features during the process. In other words, unexpected new laws begin to operate. Complete predictability / vold require not only a thorough knowledge of laws, but also a knowledge of the laws of variation of those laws. 2. Errors in specific information. A. The information regarding the nature of the system is neither complete nor accurate enough, which leads to a wrong. It. Predictable. Future. Knowable. Past. Unpredictable. Future. Observer X. Unknowable. Past. Fig 33. Limitation of possibility of information gathering owing to the finite velocity of light messengers. Regions of space-time other than the one controlled by the observer in the figure can be scanned by observers, or observing devices, placed at other positions. Choice of the relevant law statements. In particular, the information may not report that the system under consideration is inadequately isolated, so that unexpected interactions with external systems occur. B. Specific information depending on observation and measurement of quantitative characteristics, such as initial conditions, constants, and so on, is assessed with an excessive error. C. Accessible information is not enough, either because of technical limitations or because the nature of reality is such that it prevents us from gathering all the items of information needed in order to apply the relevant law statements. This may be due, for example, to the finite propagation velocity of physical signals, such as light rays. This limit upon the speed of message carriers confines the knowable past within the backward light cone and the predictable future within the forward light cone of the observer, see Fig 33. 326. 3. Errors in the inference. The logical or mathematical process of inference is faulty, or is correct but entails too many simplifying hypotheses. For example, the eventual calculation contains a mistake, or its order of approximation is too poor. Bearing in mind that all of the operations of scientific predicton involve law statements, specific items of information, and deductions, it is rather marvelous that certain scientific forecasts can be made with a high degree of accuracy and for long stretches of time. We conclude that the degree of certainty attainable in scientific prediction is not as dependent on the kind of law as is frequently believed. In particular, it is untrue that successful predictio depends on causality. The degree of certainty in prediction depends on a host of factors, and it is almost impossible to predict with certainty the conditions that will make one prediction more accurate than another. 12.5. Should causality be defined in terms of predictability? 12.5.1. The positivist criterion of causality. The traditional doctrine that prediction is possible with the help of causal laws alone can be found in the belief that predictability is a symptom of causality, or even that causation can be defined in terms of predictability. A characteristic statement in this connection is the following by Fagel: the clarified, purified, concept of causation is defined in terms of predictability according to a law, or, more adequately, according to a set of laws. Point 1. The definition of causal law as a predictive instrument led Russell 13 to regard generalizations such as dogs bark or lions are fierce as causal laws just because they enable us to make predictions, even though they assert nothing but invariable associations. L4. The following points should be noted in connection with the equation of causality and predictability. First, it involves the identity of scientific law with causal law, an identity which we found outdated, see Chapter 10. Second, contemporary scientists know that the degree of certainty in prediction does not depend solely on the kind of law, but that a host of circumstances determine the completeness and accuracy of prediction, see Sector 1 2.4.3. Inaccurate predictions can be made on the basis of causal laws, while statistical laws sometimes permit the attainment of quasi-certainty, see Sector 12.4. Third, a trait of reality, causation, should not be identified with a criterion, predictability, for the empirical test of scientific hypotheses that may but need not contain the causation category. In other words, predictability is not the meaning of causation but is a criterion of truth of both causal and non-causal hypotheses. Unlike causation, which is an ontological category, predictability is an epistemological category with an obviously historical status. Indeed, what seemed formerly to be unpredictable in principle is now seen to be predictable in some sense, and vice versa. Both the kind and the probability of every prediction depend on our knowledge of general laws and of specific situations. On the other hand, causation is a mode of behavior of things in the real world. Predictability, a variable human ability, does not mirror causation at the level of knowledge. It is grounded in all types of lawful determination, including causation. The equation of causality with predictability is, of course, common among the upholders of the positivistic interpretation of the quantum theory. Thus Heisenberg 15 in a famous paper, held that what prevents modern physics from retaining causality is the physical impossibility of measuring simultaneous exact values of conjugate variables, such as the position and the momentum of a particle, and this, in turn, prevents us from formulating accurate predictions about the future states of the particle. In fact, in the rigorous formulation of the causal law, if we know the present exactly, we may calculate the future, not the inference, but the premise is false. We cannot in principle know the present with every detail. Heisenberg's rigorous formulation of the causal law is at least striking, since it happens to be the formulation of an epistemological consequence of the hypothesis of invariable sequence in time, whether causal or not. It is incorrect to hold that the causal principle assumes the premise we can know the present exactly, because the law of causation is a hypothesis referring to a kind of connection among events as they happen, whether under experimental control or not. It is only in order to test hypotheses concerning connections among phenomena that we have to know the antecedents from which predictable consequence will evolve. To say the least, it is hasty to proclaim the failure of determinism on the bare ground that it is not possible to gather all the information that is needed to test the causal principle in a particular domain, such as atomic physics. Only the erroneous equations determinism equals causality, ontological narrowness, and causality equals predictability, anthropomorphic conceit, can be made the ground of indeterminism. Uncertainty in knowledge is far from being the unequivocal sign of physical indeterminacy or haziness. Moreover, the empirical indeterminacy characterizing the usual interpretation of the quantum theory is a consequence of its idealistic presuppositions regarding the non-existence of autonomous physical objects. 16. The so-called observables of the quantum theory are in general only statistically predictable. More exactly, with the exception of pure cases, it is not possible to predict with certainty what values a given variable will assume upon measurement. This comparative uncertainty in the prediction of the results of measurement is an empirical indeterminacy, an uncertainty, which by no means warrants the validity of indeterminism in an ontological sense. Moreover, it is not an unbound indeterminacy, for definite probability distributions are predictable, that is, the probability of finding every single value is predicted. Furthermore, the uncertainty under consideration is not the reflection of an objective indeterminateness, of a lack of precise connection between the successive states of microphysical systems, since it openly refers to results of measurement, hence to the interactions of the object with its macroscopic environment and not to things in themselves, as they behave in the absence of interactions with macroscopic devices. In other words, the empirical indeterminacy in question refers only to physical variables represented by operators. On the other hand, the so-called hidden parameters, or intrinsic variables, by means of which de Broglie and Bohm have succeeded in setting forth the causal interpretation of quantum mechanics, are not affected by any inherent uncertainty. Those who wish to invoke the quantum theory in favor of some of the fashionable indeterministic reveries must decide to forget, a. that not even the usual formulation and interpretation of quantum mechanics foregoes determinism in general, but questions only causality, see Sector 1.2.5, the universal validity of which had been questioned in philosophy long before the advent of the quantum theory. B. that from 1952 on various consistent and empirically equivalent interpretations of quantum mechanics have been proposed, in which a good deal of causal determinism is reinstated, though not to the exclusion of statistical determinacy. 12.5.3 Uncertainty and indeterminacy. Is ontological determinism inconsistent with epistemological probabilism? Successful prediction enables us to confirm or invalidate scientific law statements, whether causal or not. Prediction and practical application are tests of all the general hypotheses of science and technology, whatever their causal rate may be. The systematic failure to predict by means of a given law with a strong causal component is a strong presumption against the truth of that law statement in the range under investigation, but it does not invalidate the law in every range, and it does not constitute a refutation of the causal principle. The failure of particular causal hypotheses and even the eventual failure of causality in entire fields of research proves only that the causal principle has not a universal validity. In particular, the statistical ingredient in all the statements which we have named laws, such as the statements of laws 2 for predictive purposes, shows that at least one domain, that of the subject-object relation, is not exhausted by causal connections. Causality cannot consequently be defined in terms of predictability according to law, nor is it correct to define chance as inability to predict. Prediction is a human both fallible and perfectible ability. Predictability is an epistemological consequence of the existence and knowledge of laws of any kind, both causal and non-causal. Uncertainty therefore does not entail indeterminacy. Complete determinacy, univocally fixed by the totality of laws, is a necessary but not a sufficient condition for attaining complete predictability. It would not be fair to blame the world for our own shortcomings. Ontological determinism is therefore consistent with epistemological probabilism, the doctrine according to which only probable general propositions can be asserted regarding empirical matters, the degree of confirmation being treated as a probability, though not all equally likely. 12.6. Conclusions. In contrast to divination and guessing, scientific prophecy does not claim to attain complete certainty. Very few facts in the concrete world are predictable with near certainty, and causality and scientific prediction 33.1 none in all detail, because scientific forecast is based on the knowledge of laws and of specific information regarding singular facts, neither of which is ever complete and exact. Still, scientific prediction is often satisfactory. Moreover, it is perfectible, which is to say that it is fallible, since the failure of every prediction calls for the improvement of the formulation of the premises on which it rests. The conviction of scientists that satisfactory prediction is possible whenever the relevant laws and specific information are at hand with a minimum accuracy is a form of the confidence in the lawfulness of reality. But prediction, being together with reproduction the decisive test of law statements, does not exhaust lawfulness and its function. Comte was certainly right when he put forward his famous slogan, "Science dou paralvoyance dou action." But he was wrong in denying the explanatory function of science, which not only satisfies in a rational way the inborn instinct of investigation, but also is instrumental in suggesting new, as yet uncertified facts. What? Where? When? Whence? Why? These essential questions that scientific research tries to answer in an intelligible and verifiable way imply each other. To answer one of them is not more important for science than answering any of the remaining questions, at least in the long run. Causation is not identical with predictability. Hence, successful prediction by means of non-causal laws refutes the belief that causal legality is coextensive with science. Secondly, failures in prediction on the ground of causal laws do not entail the failure of determinism in general. In particular, inability to predict radical, qualitative, novelty, far from confirming indeterminism, only suggests that the law of emergence of the new feature under consideration has not yet been found. Moreover, complete predictability, as contrasted to complete determinacy, is in a sense inconsistent with our recognition of radical novelty. A being who was endowed with the power of predicting every novelty would be unable to recognize it as such when it occurred. He would always have the feeling of déjà vu. In a word, neither causal laws nor laws of evolution in time are indispensable to scientific prediction. Conversely, successful 332. Prediction with the help of a set of laws is not a test of their causal nature. A pragmatic criterion, like predictability, cannot decide about the meaning of laws too or about the nature of law. Slow predictability and artificial reproducibility are empirical criteria for testing the truth of law statements. The attempt to derive all the meaning of law statements from their use and from the procedures of their verification amounts to confusing truth with one of its criteria, semantics with pragmatics. Only a philosophical analysis of scientific laws can decide upon their meaning. The kind of laws needed for prediction will depend on the kind of prediction that is being asked for. Conversely, the kind of prediction that can be obtained will depend on the available laws, and specific information. Any kind of scientific law will, if true enough, allow us to perform scientific predictions of some sort. In contrast to divination, scientific forecast is just foresight grounded on an insight including a knowledge of the objective patterns of being and becoming. In brief, there is no necessary relation between causality and prediction. any more than there is between causality and explanation. 13. The place of the causal principle in modern science. 13.1. Causality, neither myth nor panacea. The problem of causation divides philosophers into roughly three camps: causalists or paneidists, who may be regarded as the conservative party, acausalists or anaidists, who exhibit the nihilistic tendency, and semi-causalists or hemiatists, whom I take pleasure in imagining to be representatives of the progressive or constructive trend. Causalism is the traditional attitude of disowning all non-causal categories of determination, holding dogmatically that every connection in the world is causal. The nihilistic party, on the other hand, declares that the concept of causal nexus is a fetish, Pearson 1, an analogical fiction, Weyinger 2, a superstition, Wittgenstein 3, or a myth, Thalmann 4. This view is usually accompanied by the phenomenalist rejection of every kind of explanation, including of course causal explanation, in favor of description. Needless to say, the denial of the existence of genetic bonds among events is vital for every kind of subjectivism. In the case of laic empiricism, the sole admissible link among events is the experiencing subject, whereas in the case of Neoplatonist, Malebranchian, or Berkeleyan idealism, there can be no other bond than God. In either case a person, human or divine, is assigned the role of glue among facts that would otherwise be disconnected or simply non-existent. The entirely negative attitude taken by indeterminism and by empiricism toward the principle of causation is inconsistent with the very goal of science, which is the search for the objective forms of determination and interconnection. To declare that the sole verifiable relations are those obtaining among sense data, concepts, and judgments, and to hold that it is vain to try to disclose autonomous interconnections and real modes of production, is an anthropomorphic attitude blocking scientific advance. It is a regressive attitude, even if most of its upholders sincerely believe that they are in the van of modern thought, just because they substitute modern dogmas for traditional ones. On the other hand, the recognition that causation is more than a psychological category akin to habit, the acknowledgement that genetic links, among them those of the causal type, do exist in the external world, is an attitude that, far from being anthropomorphic, helps to avoid the pitfalls of subjectivism, whether sensationistic or spiritualistic. Many who wish to resist the phenomenalist and indeterminist attack on rational knowledge have found no better way than to repeat with obstinacy the traditional view according to which no scientific knowledge worth its name is possible apart from causal lawfulness and apart from explanation and prediction on the basis of laws which, like Newton's or Maxwell's, are wrongly supposed to be purely causal laws just because they are not statistical, the truth being that they have a causal component, combined with doses of self-movement and reciprocal action. This conservative attitude, often rooted in a sound desire to preserve the right to understand the world, a right denied by indeterminists, has proved powerless in the face of philosophical criticism and the increasing realization of the importance of other types of determinacy, such as reciprocal causation, self-determination, and random interplay. The course of science has not confirmed the conservative hope that all the non-causal types of determination would finally be seen. The place of the causal principle in modern science. 335 To be reducible to causation. Quite the contrary, a richer variety of types of determination is being recognized. We are not, then, faced with the dilemma indeterminism-causalism. Just as in the problem of moral freedom, in intellectual affairs it is not always a question of choosing among two given alternatives. Sometimes the act of choice is replaced by the creation of a third alternative. The right way of resisting the combined attack of phenomenalism and indeterminism upon rational and objective knowledge is not, I believe, to take refuge in the past by dogmatically disowning all non-causal types of scientific law, explanation, and prediction, regarding them as mere temporary contrivances as is so often done in connection with statistical determinacy. The right and progressive attitude is to face the agreeable fact that science has advanced to such a point that, without dispensing entirely with the causal principle, it has assigned it a place in the broader context of general determinism, a role that is neither the principal nor the meanest, neither that of main pillar of inductive sciences, Mill, nor that of a superstition, Wittgenstein. The causal principle is one of the various valuable guides of scientific research and, like most of them, it enjoys an approximate validity in limited ranges. It is a general hypothesis with a high heuristic value, a fact suggesting that, in certain domains, it does correspond rather closely to reality. 13.2. The domain of causal determinacy. 13.2 Conditions of applicability of causal hypotheses. The statement that the causal principle has a limited range of validity raises at once the following questions: what is the causal range? And when is it permissible to apply causal hypotheses? The first question refers to the objective operation of causation, the second concerns the conditions under which the use of causal ideas is valid. The answer to the first question depends on the answer to the second one, as the scientific way of drawing the strip demarcating, rather vaguely indeed, the domain of causal determinacy is to ascertain the degree of adequacy of our causal ideas about the world, that is, to 336. Ascertain to what extent they are confirmed, a task that is of course performed by science in every particular case. It is a consequence of what has been said in the foregoing chapters, and especially in Part 3, that some of the conditions for the applicability of specific statements fitting the necessary production formula of causation are the following: that the main changes under consideration be produced by external factors, that is, when the system is largely, never entirely, at the mercy of its environment, so that inner processes are not the main sources of the change in question, although external conditions will be efficient solely to the extent to which they succeed in modifying those inner processes. The predominance of external over internal factors finds frequent illustrations in technique and in industry, which, as Bacon would have said, are just concerned with turning the natura libera into a natura vexata. 2. That the process in question can be regarded as isolated, that is, when it is permissible to regard the given process as torn out from its actual interconnections, which are usually numerous, but often irrelevant to the aspect that is being investigated. In other words, when such an isolation does not affect essentially the feature that is being investigated, or, what amounts to it from a pragmatic viewpoint, when the perturbations can be corrected for. This is often possible for limited intervals of time. 3. That interactions can be approximated by agent-patient relations, that is, when reciprocal actions either do not exist or, far from being symmetrical, are such that the action is considerably more important than the reaction. In other words, when reactions either are absent, or are negligible for all practical purposes. It is, again, typical of human production and technology to regard the raw material as a patient on which human work is exerted. 4. That the antecedents and the consequents be uniquely connected to each other, that is, when each effect can be considered as following, not necessarily in time, uniquely from a fixed cause, simple causation, as contrasted to multiple causation. This is particularly the case when the relevant causes are not all equally. The place of the causal principle in modern science. 337 Important in the concerned respect, but may on the contrary be arranged in a hierarchical gradation, chief cause, first-order perturbation, and so on. It should be noticed that all of these conditions concern facts or either than our cognitive grasp, reconstruction, of them. In other words, the conditions for the validity of causal ideas depend primarily on the nature of the object, or on what is assumed to be its nature. All of them seem necessary for causal hypotheses to work, none being sufficient by itself. Probably further clauses would be found on closer inspection, but what is more important to our present concern is that none of these conditions can exactly be fulfilled in real cases. In fact, external conditions are not efficient no matter what the internal ones are, but act always in combination with them and impinge upon the specific characteristics of the object concerned. Consequently, changes are never exclusively produced by extrinsic determiners, as required by I. Besides, there are no perfect enclosures guaranteeing complete isolation even in a given respect, as required by 2. Further, there is nowhere an inert stuff performing the role of perfect patient in the style of the peripatetic materia prima, as demanded in condition 3. Finally, owing to the many-sidedness and changeability of interconnections, as well as to inner lawful spontaneity, real cause-effect connections are never exactly one-to-one, as demanded by 4. In short, the foregoing conditions can sometimes be fulfilled to a sufficient approximation, never exactly. 13.2.2 Range of validity of the causal principle. We can now deal with the question concerning the range of validity of the causal principle. If the previous remarks are accepted, if at least one of the above-mentioned conditions is regarded as necessary, then the answer can be no other than this: strict and pure causation works nowhere and never. Causation works approximately in certain processes limited both in space and time and, even so, only in particular respects. Causal hypotheses are no more, and 338. No less, than rough, approximate, one-sided reconstructions of determination. They are often entirely dispensable, but they are sometimes adequate and indispensable. To put it otherwise, in the external world there is always a wide class of processes, the causal aspect of which is so important in certain respects and within limited contexts that they can be described as causal, although they are never exactly and exclusively causal. A less vague delimitation of the domain of causal determinacy does not seem possible or even desirable. A few general conditions for the adequacy of causal hypotheses have been pointed out, but the decision about the range of every particular causal hypothesis should be the exclusive concern of science. To try to go much beyond the statement of the above-mentioned general conditions, in order to demarcate a priori and unambiguously the domain of causal determinacy in all fields of science, would be to come dangerously close to the traditional subjectivistic procedures. The adequacy of scientific and philosophic hypotheses has to be ascertained a posteriori, even though their probable adequacy can at times be assessed beforehand. The notion of causal range of the laws of nature will next be clarified and illustrated, by analyzing in some detail a typical physical law with which every student of electricity is familiar. The few elementary mathematical symbols that will appear in the next section should not deter the non-mathematical reader, for they will be described in plain words, and are dispensable for a general grasp of the subject. Mathematical signs do not replace physical concepts but ensure their clear, unambiguous, and accurate denotation. 13.3 Delimitation of the causal range of a particular law. 13.3.1 Statement of the problem. Consider the elementary physical system constituted by an electrical circuit fed by a direct current source, such as a battery, see Fig. 34. When the connection is established, an electric current of intensity I is set up, and this current in turn. Electrical properties of the wire are summarized in the constant R, resistance. The overall magnetic properties of the circuit are condensed in the constant L, self-inductance. Notice that this is the simplest electrical circuit possible, for R and L never actually vanish, although in extreme cases either of them, or both, may become exceedingly small. We make the usual assumption that our circuit is isolated enough from other physical systems that the above-mentioned parameters, E, I, R, and L, are the sole relevant ones and are moreover independent of external conditions. That is, we are assuming that condition 2, above, isolation of process, holds. It is hardly necessary to point out that here, as everywhere else in scientific theory, we are concerned with an ideal model of an actual, concrete object. We are, in fact, neglecting a number of internal irregularities and external disturbances, such as small variations in the electromotive force, current losses, variations in the external magnetic field, random temperature fluctuations affecting E and R, and so on. The law that sums up the dynamic interdependence among the essential features of our system, represented by a parameter each, is the following: the sum of the applied electromotive force E and the induced electromotive force Ej, produced by the magnetic field, is equal to the fall of potential. One is tempted at first sight to regard this as a typical causal law, stating that the cause E, applied electromotive force, produces the current I, effect. A closer examination will, however, show that this causal interpretation of law 1 is valid solely in connection with a limited domain, namely, when the current I has attained its final steady value is, given by Ohm's law, which is a particular case of law 1, applicable when the current does not vary. Before the steady state has been attained, and also after it has ceased, the actual connections among the relevant features of our system are not strictly causal, as will be seen presently. 13.3.2 HRST stage of the process, cycle of determinants. In fact, as soon as the battery is switched on, the current increases continuously from 0 till its final steady value is, c. The place of the causal principle in modem science. 34 I cause, applied EMF. I induced EMF. Effect, current. T magnetic flux. Fig. 36. Cycle of determinants in a simple electrical circuit while the current is increasing, stage I. The causal connection obtains when this cycle degenerates into a direct cause-effect bond, stage 2. Fig. 35, I does not attain this value is abruptly, the full effect does not follow immediately upon the cause, simply because in this case the effect I opposes the cause, so that condition, 3, above is violated. Indeed, while the current increases, diff 0, it produces a magnetic field of increasing strength that surrounds the coil and reacts back on the current in it. The variable magnetic flux C/, due to the increasing current, produces in turn an induced EMF, EI equals, dC/F dt equals, diff 0, which in this case opposes the applied EMF. This back EMF induced in the wire by the growing magnetic field is what prevents the current from attaining the final value is without any time lag. This process is an instance of natural, negative feedback with a variable total effect, see Fig. 36. From an ontological point of view, this stage of the process illustrates the cycle of determinants, in which the cause-effect nexus is but a side or a moment of a more complex loop of reciprocal actions. In this first stage of our process, the interaction category is the dominant determinant. 13.3.3 Second stage of the process, causal nexus. The first stage goes over continuously and asymptotically into the second stage, which is definitely causal. In this second case, the action of the cause is no longer counteracted by its effect, the magnetic flux produced by the current is now constant, dC//dt equals 0, so that the effect does not react back on. 342. The cause, EJ equals 0. \VE now have a linear, unidirectional cause-effect bond, summarized in the following law, Ohm's law, which is a particular case of law 1, namely, the applied EMF, the cause, maintains the constant current is, the effect, which is proportional to it. The precise form of this law is, 2, the steady state is, then, the causal domain of the process of electric conduction in metals, or, again, the special law, 2, covers the causal range of the more general law, I. This does not mean, however, that the steady state of electric conduction is an entirely causal process. Quite the contrary, the theory of electronic conduction in solids, that is, the study of the lower level motions giving rise to the macroscopic process covered by Ohm's macroscopic law, 2, shows that several categories of determination come into play. Among them are self-determination, inertia of electrons and fields, interaction, mutual action among electrons, the crystal lattice, and the impurities, statistical determination, collective behavior of the electron gas, and so on. Still, these non-causal categories are finally masked in such a way that the average motion of the electrons obeys such a typically causal law as Ohm's, the causal nature of which is especially manifest in the form given to it by Drude, namely E, R/A, J, which is Aristotelian-like. The self-motion of the electrons again becomes apparent at very low temperatures, where instead of the law of Ohm and Drude we have London's law, E equals A8J/of, which accounts for superconductivity and is of the Newtonian type. Only the net effect is connected in the simple form, 2, to the cause E. When we say that the law, 2, that characterizes electric conduction in metals at ordinary temperatures is causal, we imply that it is causal on its own level, quite aside from its roots in the more complex laws characterizing electron conduction inside a crystal lattice subjected to an externally impressed electric field. Here we are, in short, analyzing the causal range of a definite law belonging to a definite level. We are concerned with the causal component of a given law, rather than with the causal aspects of a given event or string of. The place of the causal principle in modern science. 343 events. As every single phenomenon is the locus of a whole set of laws belonging to various levels, see Sector 10.4.3. 13.3 plus third stage of the process, self-determination. Let us now turn to the third and last stage of our process. When the battery is switched off, E equals 0, the current does not cease immediately but dies gradually, thus falsifying the well-known scholastic maxim causas est ante cessat ej effectus. The associated magnetic field decreases, dCp/dt. This induced EMF is what maintains the current I. It is a typical after effect, for the cause E has now vanished. The pattern of this stage of the process is the following particular case of law, I. LDR. O equals dt plus T. 3. According to Maxwell's field theory, which explains the phenomenological circuit theory, in this last stage the causal component has entirely concentrated in the decreasing magnetic field, which is not, however, an externally acting cause but an intrinsic determinant of the whole system, of which the coil is only a part. But from the point of view of circuit theory, the process of dying out of an electric current has not even a causal component because, unlike stages I and II, in stage 3 the cause, E, has ceased to operate. From an ontological point of view, the stage of the process is consequently dominated by the self-movement category, which characterizes predominantly or exclusively self-determined processes, whose ideal model is inertial motion. To sum up, in the process of growth, maintenance of the steady state, and dying out of an electric current in the simplest possible metallic circuit, 3 stages must be distinguished, each characterized by a peculiar category of determination. These stages are, I, domain of reciprocal action, beginning of current. The effect I has not yet fully developed, and reacts back on the cause E, in 344. The manner of negative feedback. The differential law of this process of reciprocal action is, I, the corresponding integral law is I equals I, E dash, rel, T, I, equals E slash R. As time passes, the effect reacts less and less on the cause, that is, dt decreases, and the corresponding back EMF dies away, until finally the causal stage has fully developed. 2. Domain of causation, steady state. The constant cause E maintains the constant effect is in accordance with Ohm's law. 2. This steady state lasts until, for one reason or another, the battery is switched off and the process goes over into its last stage. 3. Domain of self-determination, dying away of the current. The cause has disappeared, E0, but the effect does not vanish immediately, it dies away gradually, maintained by the decreasing magnetic field. The differential law of this process is, 3, the corresponding integral law is I equals is R, R/L, I. The foregoing example was not meant to illustrate the claim that the range of every law of nature splits unambiguously into non-overlapping domains each dominated by a single category of determination. This contention is definitely untrue, as will be realized by recalling the various types of law discussed in the previous chapters. Some laws have no causal component at all, as is the case with the classificatory, kinematical, and conservation laws, and others have a causal component that is not additively combined with other categories of determination. What the consideration of the electrical circuit discussed is expected to support is the central thesis of this book, namely, that the causation category is indispensable in science but, like every other category of determination, has a limited range and, moreover, works in combination with other determination categories. The analysis is also expected to have shown that the causal any of the laws of nature cannot be determined a priori once and for all types of law, but must on the contrary be the outcome of detailed analyses of specific laws. The place of the causal principle in modern science 345 13.4. Any causality tomorrow? 13 plus I. A verbal trap into which philosophers of verb have fallen. What will the future import of the causal principle be? According to a fashionable view, the domain of causal determinacy will continue to shrink, until nothing will remain of it. All laws of nature and society will ultimately be shown to be statistical, and the concept of causation will be seen to be a myth, a remnant of the prepositive stage of mankind. Russell, among others, prophesied that in a sufficiently advanced science, the word cause will not occur in any statement of invariable laws. 5 Now, this can easily be granted, and there hardly is any need to wait for the future. But it does not follow from it that the concept of cause will finally be extruded from philosophy, however scientific philosophy becomes. The word cause, which denotes a generic concept, need not occur explicitly in any particular scientific statement. The cause concept belongs to ontology, just as do the concepts of quality, change, connection, chance, and so on, which receive specific names in every chapter of science. Every science is concerned with particular qualities, changes, connections, types of chance, and so forth, and some particular changes fit causal patterns even if the word cause does not appear explicitly in the conceptual reconstructions of such patterns. The fact that science employs less and less the word cause, which belongs to the philosophical vocabulary, cannot be regarded as a sign of decrepitude of the causal principle. 6. One should not allow oneself to become an easy prey of language. Likewise, the fact that our philosophical ideas on determination all seem to bear the stamp of causality does not prove the latter's healthiness. Upon closer examination it is seen that in this case, as in so many others, we are not only deluded by the survival of fossil theories into which we try to force every original finding, we are also deluded by the verbal form in which ideas on determination are usually ordinary and in philosophical language, is a reliable sign of the evolution of the status of the causal principle. Since this is factual question, let us take a look at the recent history of science. 13.4.2. How quantum mechanics finally disappointed a causalists. Recent science seems to show neither an enlargement nor a progressive shrinking of the domain of validity of the causal principle. What is apparent is a complex, confused, and unpredictable intellectual process in which some phenomena are deprived of the causal character that had previously been attributed to them, whereas other phenomena are recognized as having a causal aspect. Besides, non-causal types of determination are shown to be somehow linked with causation. The overall trend discernible in recent science in connection with the general problem of determinism is not so much an increasing departure from causality as a progressive diversification of the types of determination, with correlative changes in the meaning and scope of the causal principle. The case of quantum mechanics is highly edifying. Until recently, most scientists and philosophers of science believed that quantum mechanics had given causality the death blow, by showing that quantum phenomena are inherently random. Subject. Phenomenon. Fig. 37. The subject-object relation in the usual interpretation of the quantum theory, the two make up an unanalyzable unit, in the midst of which the phenomenon takes place, provided the experimenter deigns to conjure it up. Hence only statistically predictable. More exactly, the partition of the world into observing and observed system prevents a sharp formulation of the law of cause and effect, as Heisenberg 7 explained. Such a partition is performed in every experiment, and the position of the cut, schnitt, is arbitrary, being dependent upon the decision of the experimenter. Even if causality were assumed to hold on either side of the partition, as has sometimes been done, such a hypothesis could not be confirmed empirically, for what we observe is something lying precisely at the cut, and the behavior of this region is not governed by causal laws but by the laws of the quantum theory, which are, wrongly, supposed to be entirely non-causal. In other words, quantum phenomena are, according to the orthodox interpretation of the theory, located in the intersection of the observer and his observing setups, see Fig 37. In addition, it is the observer who is supposed to play the active part therein. As long as the physical object was thus denied an autonomous existence, as long as laws of nature were not regarded as objective patterns, but their meaning was confounded with the mode of their verification, physical causation could merrily be swept aside. It is therefore not surprising that a few years ago one of the founders of the Theory 8 could prophesy that one should expect further departures from causality in the domain of the so-called elementary particles. Not even the principle of antecedents might be spared in the next move toward indeterminism, according to Heisenberg. And the well-known author of A General Theory of Prediction went on to formulate the bold prophecy that every future quantum mechanical theory would have to be essentially indeterministic and subjectivistic, and the former because of the latter. But prophecies not based on laws are just prophecies, not scientific predictions, see Chapter 12. The above-mentioned prophecies on the progressive shrinkage of the domain of causality did not come true. 1 year after Heisenberg's article, Bohm 9 published his celebrated reinterpretation of elementary quantum mechanics, based on de Broglie's 10-old idea of the pilot wave. In this interpretation, which is so far empirically equivalent to the usual one, the object is conceived as existing autonomously, though as strongly interacting with its macroscopic surroundings, which may include measuring devices, but not the experimenter's mind. The usual quantum mechanical variables, the observables, are assigned to the zone of overlapping of the object and the apparatus, but the behavior of the object itself is described by means of new variables, the so-called hidden parameters, which are not subject to any uncertainty relation, see Fig 38. Heisenberg's uncertainty principle is not regarded as an inherent limitation of precision, but rather as a technical limitation arising from the objective-object apparatus interaction, the amount of which should in principle be computable with the help of a more detailed theory. Moreover, the de Broglie-Bohm interpretation affords a causal explanation of the quantum mechanical fluctuations in the trajectories of atomic scale particles. Classical trajectory. Fig 39. The classical trajectory of a particle is determined by inertia and the externally impressed force. The quantum trajectory is determined, in addition, by an internal force depending on the Lg field. Variations that were formerly regarded as inherently random, hence individually unpredictable in principle. Newton's force equation is reinstated in a generalized form, enabling us in principle to predict accurately the trajectory of the particle. In addition to the ordinary external force, a new, internal force depending on the Lg field occurs in the acceleration formula LL, and this quantum mechanical force accounts for the departures from the classical trajectories, see Fig 39. Who would have expected such a revaluation of the causation category, which seemed to have been excluded forever from the quantum level? Only a few disbelievers in linear progress and complete theories. The moral of this little story, which has produced a deep demoralization and confusion in the acausalist camp, seems to be pretty simple, and even known of old, to wit, beware of prophesying in detail the future course of science along any other path than that of an increasing enrichment in both facts and concepts. The future of the causal principle does not seem more uncertain than that of any other particular principle of determination subsumed under our general principle of determinacy, SEC Secretary I.5.3. All of them seem now to be indispensable and are. The net effect of the nihilistic criticism of causality was to encourage fortuitism and its epistemological partner, namely, irrationalism. On the other hand, the intention of the present book is to show that, just like every other category of determination, causation has a limited range of operation, that the causal principle holds a place in the broader context of general determinism, and that failures of the causal principle in certain domains by no means entail the failure of determinism lato sensu, or the breakdown of rational understanding. The realization of the limited scope of the causal principle supports neither skepticism nor irrationalism. Every failure of causality stricto sensu can be regarded as the victory of a different principle of determination, and it simply marks the breakdown of outdated ontologies that are too narrow to make room for the unlimited richness of reality, as progressively disclosed by the sciences. What in contemporary science has taken the commanding place once held by the causal principle is the broader principle of determinari, or of lawful production. The two components of this principle, under which the general law of causation is subsumed, are the genetic principle, nothing springs out of nothing or goes into nothing, and the principle of lawfulness, nothing unconditional, arbitrary, lawless occurs. The principle of determinacy just states that reality is not a chaotic aggregate of isolated, unconditioned, arbitrary events that pop up here and there without connection with anything else. It states that events are produced and conditioned in definite ways, though not necessarily in a causal manner, and it asserts that things, their properties, and the changes of properties exhibit intrinsic patterns, objective laws, that are invariant in some respects. The principle of determinacy, often mistaken for the law of causation, is the common ground of all forms of scientific determinism, from which fatalism is excluded, since it involves supernaturalistic elements violating the genetic principle. 2. 352. Reduce determinism to causal determinism is to have either a poor opinion of the resources of nature and culture, or too high an opinion of philosophical theories. Those who assign to causality the exclusive appurtenance of characteristics that are actually shared by all kinds of scientific determinism either fail to resist the attacks of indeterminism and irrationalism, or to the extent to which they succeed in the defense inadvertently clothe non-causal types of determination in a causal language. If there is some truth in what has been said in this book, the right policy with regard to the causal problem can be summarized in the following rules: a. To employ the causation category whenever permissible, without fearing to be accused of fetishism, mechanism, or whatnot. B. To recognize the limited character of causal hypotheses. C. To make room for further categories of determination whenever they contribute to affording a truer account of being and becoming. And D. To abstain from terming causal all those categories which, like self-determination, reciprocal action, and so forth, clearly overflow causality and belong instead to general determinism. According to Descartes 12, the perfect science was the precise knowledge of effects by their causes, that is, the deduction or explanation of observed effects from their assumed causes. This peripatetic non may still be regarded as the paradigm of science, but, paradoxically enough, with the following essential qualifications: a. The link between causes and effects need not always be causal, that is, unique, unsymmetrical, constant, external. B. Nothing warrants the presumption that we shall ever attain more than a hypothetical, but improvable, knowledge of causes, effects, and their links, whether causal or not. The causal principle reflects or reconstructs only a few aspects of determination. Reality is much too rich to be compressible once and for all into a framework of categories elaborated during an early stage of rational knowledge, which consequently cannot account for the whole variety of types of determination, the number of which is being increased by scientific research and by philosophical reflection upon it. 12 Descartes, 1644, Principles of Philosophy, Part I, 24. The place of the causal principle in modern science. 353. What has been rejected in this book is not the principle of causation, but its unlimited extrapolation, as asserted by the doctrine of causalism, or causal determinism, a primitive, rough, and one-sided version of what I took the liberty of calling general determinism. To use picture language, we may say that causal determinism is the ray optics approximation of general determinism. Or, if a mathematical metaphor is preferred, determination is a vector in a space of a large, as yet unknown number of dimensions, causal determination being just one of its components or projections. The causal principle is, in short, neither a panacea nor a myth. It is a general hypothesis subsumed under the universal principle of determinacy, and having an approximate validity in its proper domain. 354. The last few decades saw a vigorous resurgence of causal questions, analyses, and theories. Like many another central philosophical problem, the causal problem is actually a whole cluster of problems. It can be divided into two parts: 1. The ontological problem of causation, i.e., what is causation, what are the relata of the causal relation, things, properties, states, events, mental objects, what are the characteristics of the causal nexus, to what extent is the nexus real, are there causal laws, how do causation and randomness intertwine, etc. 2. The methodological problem of causality, i.e., what are the indicators and criteria of causation, how do we recognize a causal link and how do we test for a causal hypothesis. Every one of these subsystems is chock full of problems, some old and some new. Just think of the difficult problem of unraveling causal relations beneath statistical correlation, and of the no less difficult problem of determining the causal range of a law statement. Moreover, the membership of every one of the above subclusters of problems keeps changing in the course of time. But somehow none of them seems to become depleted, even though once in a while a hasty philosopher will proclaim the NAL solution to the causal problem, perhaps without having bothered to propose a careful formulation of the causal principle. This is not surprising in philosophy. At some time or other matter, property, space, time, law, determination, chance, and many other metaphysical categories have been decreed dead until it was eventually discovered that they refused to lie down. Philosophical fashion seems to be as erratic as dress fashion, and in any case it is not a good indicator of the intrinsic worth of a problem or of a theory. This review focuses on the ontological problem of causation but is not limited to the philosophical literature. It also attempts to uncover certain trends in recent science. One state of the causal problem in mid-century: a perusal of the philosophical literature shows that the causal problem failed to attract the attention of philosophers during the 30s, 40s, and 50s. Surely a few books and articles on the subject did see the light during that period. However, most of them were written by non-philosophers, and they dealt either with the alleged death of causality in the hands of quantum mechanics, or with ways of inferring causal connections from statistical correlations. The general ontological problem of causation was usually neglected, as were in fact ontological questions in general. Causality had been a victim of two profound intellectual revolutions in the 1920s, namely the quantum theory and logical positivism. These were not mutually independent events. In fact, the quantum theory had been interpreted in the light of logical positivism, namely in terms of measurement operations, and this philosophy was the heir to Hume's empiricism, which involved a denial of causation as an objective connection beyond constant conjunction or regular succession. Besides, the quantum theory was basically probabilistic. No wonder then that causality seemed scientifically and philosophically dead. Nor were such developments isolated. For one thing, the exact sciences are hardly interested in relations between whole events. Instead, they are centrally interested in relations among properties represented by functions, variables. And functional relations among mathematical representations of properties are neither causal nor non-causal by themselves. For another, chance began to be recognized as an ontological category, not just a cloak of ignorance. Think not only of quantum jumps and of the random scattering of elementary particles by atomic nuclei. Think also of genomes, which are the product of random processes such as the random shoving of genes occurring in recombination, and of the random mutations undergone by the nucleic acids in the cell. Nor were the quantum theory and genetics the only fields where basic probabilistic laws occurred. Probability had started to invade mathematical psychology, in particular learning theory, and mathematical sociology, in particular the theory of social mobility. The whole of contemporary science was shot through with the concept of randomness. So, by mid-century, scientists and philosophers had come to realize that chance is not just a name for our ignorance of causes, that chance is a mode of being and becoming. So, any theory of change that ignores chance and causalism does just that, has to be false. Cournot and Peirce had known this all along. Causalism, or the doctrine that all relations among events except for the purely spatio-temporal ones are causal, was then defunct at mid-century as a result of scientific developments as well as of the emergence of logical positivism. Any attempt to resume the discussion of causal questions seemed then quixotic and doomed to failure. But, as we know from the history of philosophy, certain problems are die-hard. This proved to be the case of causality. To the resurgence of causality, while philosophers rejoiced in the disappearance of one more troublesome problem, men of action and professionals continued to think unashamedly in causal terms. In particular, engineers cannot help doing so because it is their job to design systems whereby man can cause changes in the environment. Likewise, physicians cannot help study the etiology of disease, they too are believers in causality. Nor do lawyers doubt it, for it behooves them to investigate the effects of certain human actions, or inactions. Unfortunately, the philosophy of technology and the philosophy of medicine were hardly in existence at mid-century, so philosophers took not notice of the discrepancy between the practice of engineers and physicians, on the one hand, and the philosophy of causation on the other. But the philosophy of law was very much alive, and it did produce a major work on our subject, namely Causation and the Law by Hart and Honor 1. The authors of this important and influential work show convincingly that causal questions occur often in every branch of jurisprudence, and moreover that there is a large variety of causal concepts, some of them unsuspected by philosophers. Hart and Honor characterize these concepts clearly, though not exactly, and illustrate them with a great many legal cases. The result of their study is the great number of different causes that different legal experts may impute to one and the same human action. Take the case of murder with a gun. What or who caused the death of the victim? The coroner may declare that the cause of death was the shot wound, the public prosecutor, that it was the defendant's pulling the trigger of a gun, and the counsel for the defense, that it was the victim's harsh treatment of the defendant, or the climate of violence in which the latter had been brought up, or what have you. Even if all the experts agree on the facts and act in good faith, every one of them is likely to select one member of the causal cluster or one link of the causal chain as the main or most relevant cause of the event, which is just as well as long as neither denies that every one of them may have been a contributory cause. From an ontological point of view, perhaps the most interesting causal questions arising in the law are not those concerning wrongdoing but the cases of negligence or omission, i.e. the failure to do something when action was called for either morally or legally. Although omissions do not qualify as causes in ontology, they do so in ethics and in the law. Thus the employee who fails to lock a door and thus makes a burglary possible or easier is a contributory cause of the crime and as such liable to retribution. That a non-event, such as an omission, should count as a cause sounds absurd in ontology, not in ethics or in the law, and is therefore a good focus for investigating the difference between natural law and moral, or common, law. Another peculiarity of legal and ethical thought that distinguishes it from ontology is that it involves the notion of responsibility, absent from natural laws and typical of human sociality, and perhaps of the sociality of mammals in general. Thus it matters to both morals and the law who is morally responsible for a crime, example as an instigator, not only who committed it, i.e., caused the wrong outcome. Ivan Karamazov is morally responsible for Smerdyakhov's murder and is therefore as guilty as he. Not surprisingly, the notion of responsibility and its relation to that of causation plays a central role in the treatise of Hart and Honor. The same year saw the publication of the reviewer's own book Causality, The Place of the Causal Principle in Modern Science too. This work seems to have appeared at the right moment, for it was reviewed many times and translated into 6 languages. It criticized a number of doctrines, among them the total denial of causation, its equation with uniform succession or with constant conjunction, and the view according to which causation is the sole mode of determination. Moreover, it defended the following theses: 1. The causal relation is a relation among events, not among properties, or states, let alone among ideas. Strictly speaking, causation is not even a relation among things, i.e., there are no material causes. When we say that thing A caused thing B to do C, we mean that a certain event, or set of events, in A generated a change C in the state of B. 2. Unlike other relations among events, the causal relation is not external to them, as are the relations of conjunction, or coincidence, and succession. Every effect is somehow produced, generated, by its causer, s. In other words, causation is a mode of event generation or, if preferred, of energy transfer. 3. The causal generation of events is lawful rather than capricious. That is, there are causal laws or, at least, laws with a causal range. And such objective regularities must be distinguished from law statements, such as differential equations. 4. Causes can modify propensities, in particular probabilities, but they are not propensities. In the expression event X causes event Y with probability P, or the probability that X causes Y equals P, the terms causes and probability are not intered and able. Moreover, strict causality is non-stochastic. 5. The world is not strictly causal although it is determinate. Not all interconnected events are causally related and not all regularities are causal. Causation is just one mode of determination. Hence determinism need not be conceived narrowly as causal determinism. Science is deterministic in a lax sense, it requires only lawfulness, of any kind, and non-magic. A spate of articles and books on causality followed the publication of 1 and 2, the subject was no longer taboo. Thus Lerner III collected a number of lectures given during the 1960-61 academic year by distinguished authors such as Ernest Nagel, Ernst Mayr, Talcott Parsons, and Paul Samuelson. The Encyclopedia of Philosophy devoted a long article by Taylor Ford to the problem. Supps published 2 works 5, 6 expounding a probabilistic theory of causality. Svechnikov 7 approached the problem of physical causation from the point of view of dialectical materialism. Von Wright 8 treated the matter of causation in human action from the point of view of hermeneutic philosophy. Wallace 9, 10 produced a scholarly historico-philosophical treatise on causality. Mackey 11 re-examined Hume's doctrine and analyzed several notions of causation occurring in ordinary knowledge. Hare and Madden 12 launched a vigorous attack against Hume and his successors, and attributed all things causal powers, i.e., powers to produce or generate something. Hence they characterized the causal relation as one whereby powerful particulars produce or generate changes in other particulars. Finally Puterman III, influenced by Polish and Soviet authors, studied the problem of physical causation regarded as a special form of determination. All in all, the last 2 decades have seen a vigorous revival of philosophical studies of causation. However, we still lack a comprehensive work dealing with causal thinking in all fields, from the natural sciences to the social sciences to the various sectors of rational human action. 3. Causality in physics. Half a century ago causality seemed to have gone from physics, and this for 2 reasons. Firstly, because quantum mechanics and quantum electrodynamics, the 2 most fundamental theories of physics, are basically stochastic, their fundamental law statements are probabilistic. Secondly, because, according to the usual interpretation of these theories called the Copenhagen interpretation, every quantum event is the outcome of some human operation or other, so that there are no subject-free causal chains. Moreover, quantum events are said to be conjured up at will by the experimenter. Both arguments against causality have lost much of their force in recent years. For one thing, the Copenhagen interpretation of quantum mechanics is no longer accepted without quali-cations. More and more physicists are becoming dissatisfied with its subjectivistic aspects. C.e.g. Bunge 14 and Lévy-Leblanc 15. For another, it is being realized that stochasticity does not eliminate causation but modifies the causal relation. For example, when a physicist calculates or measures the probability that an atom will scatter an incoming electron within a given solid angle, he treats this event as the atom's yield causing a certain event, the electron scattering through the given angle, with the given probability. Thus he determines the propensity of a given event, the 2 entities coming close, causing another event, the scattering. Thus causality, initially forced underground by the quantum revolution, is now back though in a modified form. For one thing, all of the quantum theories retain the concept of force which quantitates that of causation, although they dene it differently from the way it is denet in classical physics. For another, they contain not only probabilities of spontaneous, uncaused, events, such as radioactive decays and radiative transitions of atoms in a void, but also probabilities of events induced by external agents such as ELDs. Only, the cause-effect relation is in such cases probabilistic rather than deterministic in the narrow sense. Finally, the causal aspects of the quantum theories are increasingly being regarded as representing causal aspects of the world. What holds for physics holds a fortiori for astronomy and cosmology, as well as for chemistry and the earth sciences. In particular, although in principle theoretical chemistry is based on quantum physics, organic chemistry and biochemistry deal mostly with large molecules and are therefore more receptive to causality than microphysics. Thus the biochemist and the molecular biologist have few occasions to remember quantum randomness in their daily work. They reason not so much in terms of transition and scattering probabilities as in terms of chemical bonds and activation energies. Moreover, when dealing with large-scale chemical reactions, chemists use chemical kinetics, the equations of which contain only concentrations and their rates, RST order derivatives. Because these equations are of the RST order, they make no room for inertia. That is, chemical reactions lack the component of self-movement so obvious in other processes. In molar chemistry, then, the Aristotelian principle causa ante cessat effecta seems to hold. Cf. Bunge 16. Another eld where this principle holds is automata theory and its applications, to e.g. computer science. Indeed, a deterministic automaton stays in a given state unless it receives a stimulus, and jumps to another state just in case it accepts an input. It lacks spontaneity, hence it cannot possibly mimic the human brain. To put it formally, the next state function M, characteristic of each automaton type, maps the set of ordered pairs, state, input, into the set of states, in such a way that M, S, O, equals S, where S is an arbitrary state and O the null input. Incidentally, the M function constitutes a possible formalization of the causal relation. Note that the concepts of space and time, essential to Hume's conception of causation, are absent from the above. For causality in biology, causal thinking is always at work in biology, but it has been particularly active during our period, especially in the following problem areas: evolution, goal-directed behavior, downward causation, and morphogenesis. Let us take up evolution RST. Molecular biologists have a tendency to believe that, since genic recombination and mutation are random, randomness is overriding on the bio-level, and moreover that all biological novelty emerges by chance. Cf. Mono 17. However, whole organism biologists know that this is only half of the story, that the environment selects phenotypes not genotypes, and that such selection is random only in part. Indeed, those organisms that are unt are eliminated and so leave no offspring. A monster has no chance to start a new lineage. For this reason it has been said that the environment is the anti-chance or causal aspect of evolution, Dobbs-Hansky 18. As for NAL causation, laughed away by Rabelais, Bacon, and Spinoza, it is now back in biology under the name of teleonomy, cf. Mayer 19, Mono 17, Ayala 20. Indeed, it is often claimed that the essential difference between the simplest of bacteria and a non-living thing is that the former is goal-directed, or has a teleonomic project built into it. And, just as the teleologists of old saw in adaptation proof of design and goal, so do the present-day teleologists, or teleonomists. Thus Ayala, the features of organisms that can be said to be teleological are those that can be identi-ed as adaptations, 21, p. 498. But this identi-cation of adaptedness with goal-directedness renders the theory of evolution by natural selection useless, for the gist of this theory is that adaptation, far from being the outcome of a goal-seeking process, is the, partially chancy, result of genic variation and environmental selection. Every organism behaved teleologically, then it would be perfectly well adapted, and so environmental catastrophes would be the only evolutionary factors. The idea of downward causation is this. While some geneticists claim that animal behavior is determined by the genetic blueprint, upward causation, some students of behavioral evolution point out that society enhances the genotype by selecting the individuals that are best adapted to both the natural and the social environments, downward causation. Finally, others claim that both upward and downward causation are at work, example Campbell 22. Actually, the term causation is being misused in this context, for what is at stake is a multilevel system, such as a social animal, and two views of it. One is the upward view, according to which the higher level properties and laws of the system are determined by, hence reducible to, the properties and laws of its components, in particular its nucleic acid molecules. The rival view is the downward one, according to which things are the other way around, i.e. the behavior of the system on its higher levels, e.g. the social one, determines the behavior of its components. Thus, by selecting whole organisms, the environment, in particular the social environment, selects indirectly the genetic makeup, i.e. the RNA and DNA composition. While the truth seems to lie in a synthesis of the upward and the downward views, neither of these should be formulated in terms of causation, because levels, being sets, cannot act upon one another. See Bunge 23. What we do have here is not causal relations but functional relations among properties and laws at different levels. Finally, morphogenesis has made two contributions to causal thinking. One is the set of models of cell clumping and other morphogenetic processes in strictly physical or chemical terms, such as the diffusion of the products of chemical reactions and the attraction of cells of the same kind. A second contribution comes from catastrophe theory, which purports to deal with the emergence of novel forms in all realms, from hydrodynamics to biology to sociology. Its creator, the eminent topologist René Thorn 24, has unearthed Plato's forms acting by themselves of extrinsico upon inert matter. He identifies forms with shapes and endows them with a formative capacity as well as with autonomous existence. While this is nothing but Platonism in mathematical disguise, it has created an extraordinary stir among mathematicians who, like Thorn, could not care less for the mechanisms of processes, in particular quantum mechanical, molecular, example hormonal, and selective. Predictably, catastrophe theory has been subjected to scathing criticism, cf. Zoller and Sussman 25. In conclusion, causal questions have been intensely debated by biologists and biophilosophers during our period, in contrast to previous years, when the emphasis was on description and taxonomy. However, the resurrection of NAL and formal causes suggests that the level of sophistication of causal thinking with references to life is rather modest. 5. Causality in psychology. Behaviorism was the golden age of causality in psychology and social science. Indeed, the environmentalist or stimulus response schema and the unconditioned re-X do have the properties of the causal link, in particular the tacit pretense that the inner states of the organism do not matter for its response. In fact, assuming that the animal is in any of a set of normal states, that it has no memory, and that a single stimulus operates at any given time, every SR relationship should be constant. Thus a prick in the hand will always produce the withdrawal of the hand unless of course the animal has been anesthetized. The reason for the response constancy is that the excitation is transmitted by a direct pathway, or through route, in the nervous system, without intervention of the higher centers. However, any departure from normality in the state of the nervous system will distort the SR relationship. Thus a curare or strychnine injection may put the pathway out of work, so that the stimulus will fail to elicit the usual response. This shows that SR relations have a limited causal range. More to the point, it shows that the state of the system is involved, only it may not matter precisely which state the input acts on as long as we do not care to discriminate among the possible responses. In other words, the animal is not a black box but is at the very least a gray box, such as an automaton. As we go higher up in the nervous system, or in the phylogenetic tree, we nd that the SR relationships acquire a narrower or even nil causal range. Indeed, eventually we meet the ideational processes that can delay or distort the responses, or even inhibit them altogether, or produce novel responses. Thus we can occasionally control sneezing and armor ourselves against pain. Even more to the point, some of these ideational processes are self-started rather than evoked by sensory stimuli. They are not totally uncaused, though, but may be explained as the outcome of the activities of neural systems, or of the interactions among these and other bodily subsystems. Because of its increasing concern with internal states, psychology has moved away from behaviorism, hence from causalism. Another factor in this trend has been the work in stochastic models of learning and in random neural networks. Even though most of the former have been behaviorist or at most neo-behaviorist, they have centered on the probability of correct performance upon a given trial, and so have been stochastic rather than strictly causal. Yet they have retained the externality typical of causality. The above-mentioned movement away from causality in psychology, particularly in physiological psychology and learning theory, has had no profound influence on the philosophy of mind. In particular, the psychophysical dualists of the interactionist variety have continued to hold that brain processes can cause mental processes and conversely, though the brain and the mind are separate entities. C.e.g. Popper and Ecclesiastes 26. But of course the concept of efficient cause occurring here is the vulgar one, not the one employed in science, where causation is a relation between changes occurring in concrete entities and moreover describable, at least in principle, in exact terms, not just in ordinary language. To a physiological psychologist there can be no action of the brain on an immaterial mind, or conversely, he will admit only actions, some of them causal, of some subsystem of the neuroendocrine system upon another. For example, in some yoga experiences the cerebral cortex can act on the autonomic system much as it can order a limb to move. To the scientist these are biological processes that can be explained, or ought to be explained, without resorting to an immaterial mind or self. Bunge 16:27. Action theory too is rife with causal thinking. A landmark of our period is von Wright's explanation and understanding 8, a study of the relations between human intentions, actions, and their results and consequences. Von Wright relies heavily on the non-Humean concept of causation as event generation or production, and he draws a neat distinction between the result and the consequence of a human action, which are generally lumped into the category of effect. However, the foil for his analysis of causation and causal explanation is the night-state probabilistic automaton, which he does not call by this name. This model might have served his purpose to some extent, for each state of the automaton, or node of its Moore graph, can be made to represent a state of affairs, or possible world, that can be influenced by human action. However, all this gives is a fan of possible states. It does not tell us anything about the presumptive causal mechanism responsible for the unfolding of states, unless of course one adds the postulate that man is the only causal agent in the universe. In any case, von Wright makes little use of the stochastic model of the world in discussing what interests him most, namely the causal relation between human actions and their consequences. Likewise Tumla, in his lengthy book 28 on the same subject, adopts a causalist viewpoint and more particularly makes NAL or purposive causation the pivot of his theory, presumably on the dubious assumption that all human action is purposeful. Finally, let us go back to psychology proper to mention some recent studies on the psychology of causality in the wake of Piaget's classical investigations of the 20s. There are some interesting new results in this field, among them those of Schultz 29 on whether children between 2 and 13 years of age think of the causal relation as a mere conjunction, or as a succession, of contiguous events, or in terms of energy transmission, i.e. of production of events. Experiment points to the latter. Children are not natural Humeans. The matter of understanding change in terms of causal mechanisms is of course quite different. For example, Piaget 30 NDS that children under 11 years of age, i.e. before they grasp formal operations, are unable to explain the sound emitted by a tuning fork excited by the vibrations of another tuning fork nearby. Unfortunately, most psychologists have failed to analyze the notion of causation and thus tend to lump the question of the perception of causation with the problems of conceiving of the world as lawful, of explanation, and of inference. The moral is clear, namely that one must read carefully their experiments rather than their conclusions. 6. Causality in the social sciences. Chance is ever present in human affairs. Were it not for it, we might be able to predict accurately the state of our economies, our polities, and even our cultures. However, causation is no less a factor to be reckoned with. Every person counts on certain causal links when, intent on causing someone else to do something, or on preventing somebody from causing him to behave in a given manner. What holds for individual actions holds also for social action, or rather concerted individual actions. Surely, like in the cases of physics, biology, and psychology, often only the probabilities of certain causal links can be modified. For example, social mobilities, which are probabilities, can be enhanced or weakened. But this may suffice for practical purposes and, in any case, it shows that the social sciences cannot ignore causation. Yet this is exactly what they tried to do during the long period of positivist social science which historians date back to Ranke. Our period saw the beginning of the end of the night of narrative, or objective, historiography in English-speaking countries. The search for causal connections had been on the way long before, particularly among the French social and economic historians Fiémond Braudel and Marc Bloch. However, the work of these outstanding scholars was practically unknown in English-speaking countries until a few years ago. The English Manifesto of Analytic, or Interpretative, History was Carr's What is History? 31. This book, which devoted an entire chapter to the matter of causation, proclaimed the slogan "The study of history is a study of causes," p. 113. The historian, writes Carr, will commonly assign several causes to a given event and will rank them either in order of importance or in temporal order. Machiavelli nods. Accidents, or chance events, in Aristotle's sense of the word, such as Antony's infatuation with Cleopatra, are not external to causal chains but members of causal chains interfering with the one the historian happens to be interested in. Carr criticizes Sir Karl Popper for claiming that almost anything is possible in human affairs, and for failing to realize the causal networks underlying historical processes. And he criticizes Sir Isaiah Berlin for holding that historical determinism is morally objectionable because, by attempting to explain human actions in causal terms, it denies free will and encourages historians to evade their primary responsibility, which would be to condemn the Napoleons and Stalins of history. Rightly enough, Carr reminds us that the function of the historian is to uncover and explain facts, not to moralize. The American historian Lawrence Stone concurs and, just as Carr works on the Russian Revolution, Stone investigates the Great Rebellion 32, trying to uncover what he calls the preconditions, precipitants, and triggers of that complex process. Although he contrasts the approaches of the narrative and the analytic historians, Stone believes that the main difference between them is that the former works within a framework of models and assumptions of which he is not always fully conscious, while the latter is aware of what he is doing, and says so explicitly, p. 11. A similar movement away from descriptivism and towards the search for causal links occurred at about the same time in anthropology and archaeology. The description of artifacts divorced from their social setting was replaced by the tentative explanation of their function or use. And the description of customs was supplemented by the conjecturing of social structures and economic determinants. Social anthropology became RMLY established and the need for some theoretical guidance began to be felt as ELD workers started to use their brains in addition to spades and tape recorders. The landmark of the period is Harris's brilliant and eloquent Rise of Anthropological Theory 33, a searching criticism of the anti-theoretical bias as well as of cultural idealism. Harris defends instead cultural materialism, which is really a variant of economic determinism. He also espouses operationalism and, like most workers, in the social sciences, calls theories what are for the most part hypotheses. He indicts the search for mere statistical correlations, which can be entrusted to computers and contribute little to our understanding of social reality, and asserts that causality is alive and living everywhere, p. 260. Economists are divided as to the importance of causal hypotheses as well as to their nature. Thus Samuelson 34 adopts the regular succession in time view of causation and, as a consequence, regards difference equations and differential equations with time as the independent variable, as causal laws. However, there need be nothing causal about a regular sequence of events and, unless the equations describing it are enriched with semantic assumptions pointing to causal factors, the equations are neither causal nor non-causal. See 2. Besides, no matter how unconcerned about causes the theoretical economist may pretend to be, the applied economist, for example the Minister of Finances, must know, in order to forecast and plan, which are the effects of printing more money in a given situation, which those of closing or opening up the customs, and so on. The econometrician Wold 35 emphasizes the importance of the search for causal links and discusses some of the paradoxes that can result from a neglect of identifying causes and effects. For example, it is possible to have, for a given pair of variables x and y, e.g. demand and price, two linear regression equations such as y equals x plus b and x equals psi plus d, such that the system they form is not compatible. But these are really different hypotheses, so they should not be treated jointly. In the RST y is causally enhanced by x, whereas in the second the converse causal relation is assumed. The problem, then, cannot be solved unless one commits himself to either hypothesis. Finally, sociologists have continued to work on the methodological problem of inferring, or rather conjecturing, causal networks from statistical correlations. Two particularly distinguished workers in this area are Blaylock 36 and Budden 37. The philosopher will be surprised to see that these and other investigators take properties, variables, such as age and sex, to be possible causes or effects. He may wish to interpret relative differences in the values of such variables as causes or effects, because the latter are always changes in properties, hence states. So much for a review of causal thinking in the sciences. Let us now return to the explicit philosophy of causation found in the recent literature. 7. Ordinary language analysis of causation. Most philosophers either do not analyze the notion of causal relation or examine it within the context of common sense, or ordinary language, adding occasionally a pinch of logic. The latter serves often as a carpet under which the conceptual muddles of common sense are swept. An example of this kind of work is the much-quoted paper by Davidson 38. This article purports to investigate the logical form of singular causal statements such as the hood caused the famine, as well as of causal laws, no example of which is given. However, the very heart of the matter, namely the expression C causes E, is not analyzed other than linguistically. Nor is any attempt made to check whether there are any genuine law statements that the analysis that is being offered. Which illustrates the dogmatism to which the cult of common sense can lead. In another often quoted paper, Scriven 39 asserts that a cause or an effect may be, at least, a state, an event, a relation, a congruation, a process, a thing, a possibility, a thought, or the absence of any of these, p. 50. The reason for such permissiveness is that Scriven, like Davidson 38, Wendler 40 and others, is interested mainly in ordinary language expressions, among which we and the likes of Susan was taken sick because she did not eat, suggesting that a non-event had causal efficacy. But of course expressions like this one are just handy abbreviations of long conjunctions of propositions concerning human metabolism under a variety of food inputs. It is these propositions, not their ordinary language summary, that should be investigated if one wishes to dig up causal connections and thus out what kind of objects can be related by such connections. Ordinary language is something to be analyzed, read, or even discarded, rather than being kept unkempt. In any case, it won't help us perform a causal analysis of scientific theories, a fortiori, it is incapable of identifying causal law statements, let alone the causal range of law statements. Mackey 11 points out that there are a number of causal concepts and pleads for tolerance with regard to the invention of new ones. We can speak, if we like, he asserts, not only of necessary and subsient causes but also of causes that are only necessary or only subsient. And he claims that in all cases of causal statements we presuppose contrary to fact, counterfactual, conditionals. One might rejoin that the latter may be useful heuristic clues for inferring or suspecting causal links, as in surely if A did not act then B would have happened, but not for formulating causal hypotheses. Besides, we know what it means for one proposition to presuppose another, but not what it is for one proposition to presuppose a counterfactual sentence, which is not a proposition. 370 Some philosophers believe that the notion of causal relation can be formalized within the propositional calculus, namely thus: C equals E, subsiency, E equals C, necessity, or CE, necessity and subsiency, where C and E may in turn be analyzed into conjunctions or disjunctions. But this is plainly insufficient, for after all the causal connection is a relation, and so calls for at least the predicate calculus. Thus the common maxim every event has a cause can be formalized as x equals y, cyx. However, even this analysis is insufficient because it does not analyze the predicates C and E, it does not even tell us what sorts of objects they can apply to. So, the elementary analyses of the causal relation, which is the most we get from ordinary language philosophers, are insufficient. Deeper approaches must be tried. 8. The probabilistic approach. It has occurred to a number of thinkers that causation is just a particular case of propensity. Thus consider a thing B at place P with two possibilities of motion or some other change, to the left or to the right. Moreover, suppose that B, when at P, can move to the left with probability P, or to the right with probability 1, P. If P is neither zero nor unity, either of the two changes will occur. But if P equals 0, then B will move to the right, while if P equals 1, B will move to the left. The generalization seems straightforward: determinacy is a limiting case of probability. The above hint has been exploited systematically by subs 5, 6. A cause, in his view, is anything that probability is. More precisely, if at is an event at time t and bt loda an event at a later time t loda t, then at is said to be a prima facie cause of bt iota, just in case the conditional probability of bt given at is greater than the absolute probability of bt iota, i.e. p, bt iota at, p, bt iota. A subsient or determinate cause is dnet as a cause that produced its effect with probability 1. And a spurious cause is a prima facie cause that has no influence on the outcome. The whole theory consists in a careful exploitation of these definitions with the help of the probability calculus. The only, tacit, hypothesis is what physicists misleadingly call the causality condition, i.e., the assumption that influences precede their effects. There is no other assumption, not even as Subs himself emphasizes the hypothesis that every event has some cause. The book expounds then a non-causal theory of causation. More precisely, it is an exact modern version of Hume's view of causation as constant conjunction or succession. This analysis of causation is inadequate for the following reasons. For further criticism, see Bunge 40. Firstly, it consecrates the post hoc ergo propter hoc fallacy. Indeed, consider the events. At equals the barometer is falling, here, at time t bt equals it rains, here, at time t loda t. Since the probability of rainfall at a certain place, given that the barometer has been falling, is greater than the absolute probability of rainfall, we are asked to regard the falling of the barometer as a cause of rain. Second, by the same token, the Hume subs analysis fails to distinguish between sustained, but perhaps accidental, positive correlation, and causation. Third, subs adopts uncritically the vague notion of an event used in probability theory, where an event is just an element of the ELD of sets constituting the domain of definition of the probability measure. Consequently he cannot distinguish events proper, i.e. changes in the states of things, from properties and states, or even from purely conceptual objects. Thus he is led to speaking of negative events, such as not catching a cold, and therefore also of logical events, such as catching a cold or not catching a cold, which is all right as long as the probabilistic construal of event is kept, but is of no help to the scientist and the philosopher, to whom there are only positive events and, affirmative or negative, propositions about events. In conclusion, the probabilistic approach to the causal problem fails to come to grips with the very concept of causation as a mode of event generation. An alternative approach, equally exact but more profound, must therefore be tried. The one to be discussed presently seems to be the most promising. 9. The state-space approach. In the sciences both causes and effects are events, i.e. changes of state of concrete things, be they elds, organisms, or communi. Tis. Things, their properties, and states, do not qualify as either causes or effects but rather as conditions, outcomes, or what have you. But to say that the causal relation is a relation among events is insufficient. Nor does it suffice to add that the causal relation is irrexive, asymmetric, and transitive, if only because there are innately many relations with these formal properties. We must specify, though not so much that the desired generality gets lost. The way to deal with things and their changes in general, without presupposing any particular laws, is to adopt the state-space approach. For a system of ontology conceived this way, and details on what follows, see Bunge 41. Consider any concrete thing, whether particle or eld, atom or chemical system, cell or organism, ecosystem or society. We may assume that everything is, at each instant, in some state or other relative to a given reference frame, and that no thing remains forever in the same state. One way of describing states and changes of state is as follows. Draw the list of all, known, properties of the thing concerned, and represent each property by some, mathematical, function. Such a list, or n-tuple, is the state function of the thing, call it f. The changeability of the thing is reacted in the time dependence of f. As time goes by, the value of f at the instant t, i.e. f, t, moves in an abstract space. This space is called the state space of the thing x, or s, x, for short. Any event or change occurring in x can be represented by an ordered pair of points in s, x, and visualized as an arrow joining those points. The collection of all such pairs of states in the event space of x, or e, x. The set of all really possible, i.e. lawful, not just conceivable, events in, or changes of, thing x, i.e. x, is a subset of the Cartesian product of s, x, by itself. The statement that event e happens in or to thing x is abbreviated, e set membership symbol e, x. A process in thing x is representable as a sequence, or list, of states of x, or else as a list of events in x. A convenient representation of the set of all changes occurring in a thing x during a given period of time is obtained by forming all the ordered pairs, t, f, t, of instants of time and the corresponding states of the thing concerned. Such a set, or h, x, equals, t, f, t, t set membership symbol t, can be called the history of x during the period t. Consider now two different things, or parts of a thing. Call them x and y, and call h, x, and h, y, their respective histories over a certain time interval. Moreover, call h, y, x, the history of y when x acts on y. Then we can say that x acts on y if and only if h, y, is not equal to h, y, x, i.e. if x induces changes in the states of y. The total action, or effect, of x on y is d net as the difference between the forced trajectory of y, i.e. h, y, x, and its free trajectory h, y, in the total state space, I.e. a, x, y, equals h, y, x, mathematical intersection symbol h, y, where h, y, is the complement of h, y, in the given space. Likewise for the reaction of y upon x. And the interaction between things x and y is of course the set theoretic union of a, x, y, and a, y, x. Finally consider an event E in a thing x at time t, and another event E iota in a thing y is not equal to x at time t lota. The events and the times are taken relative to one and the same reference frame. Then we can say that E is a cause of E iota just in case, a, t precedes t iota, i.e. t lota, and, b, E iota is in, belongs to, the total action a, x, y, of x upon y. In this case E iota is called an effect of E. Having dened the notions of cause and effect, we may now state the strict principle of causality. A possible formulation of it is this. Every event is caused by some other event. More precisely, let x be a thing with event space E, x, relative to some reference frame. Then, for every E set membership symbol E, x, there is another thing y is not equal to x, with event space E, y, relative to the same reference frame, such that E iota set membership symbol E, y, causes E. It is a thesis of 2 that the principle of causality is never strictly true because it neglects 2 ever-present features of becoming, spontaneity, or self-movement, and chance. The matters of space-time contiguity, continuity, etc., can be handled with the help of the above notions together with some theory of space and time. See Bunge 16. It would be interesting to formulate all possible, causal doctrines within the state-space framework. This would facilitate their mutual comparison as well as their confrontation with the most general principles of science. This is just one among the many open problems in the ontology of science. 10 Conclusion 50 years ago the causal problem was generally believed to be buried once and for all. Now it is as lively as any philosophical problem can be. Philosophers have come back to it, some of them armed with new, more powerful analytic tools, and scientists speak unabashedly of causal factors, effects, and causal networks. To be sure, few believe in the universality of the causal principle. We have curtailed it in view of the ubiquity of both chance and spontaneity, or self-determination. However, we do continue to think of causes and of effects as well as of both causal and non-causal relations among them. In particular, we can often compute or measure the probability that a given event will have a certain effect, but we do not usually mistake probabilities for causal links. We have abandoned extreme causalism, but, far from becoming indeterminists, we have enriched determinism with new, non-causal, determination categories. And we are still on the job of characterizing our basic concepts and hypotheses concerning causation. Appendix, a reply to criticisms. Professors Schlegel S.L. and Morgan Besser S.2 thorough reviews of my book Causality offer me an opportunity to clarify several points. The first 10 sections of this paper were prompted by Schlegel's remarks, the remainder by Morgan Besser's. Should determinism be equated with lawfulness? Although such an equation Fs often suggested, it is not commendable. Because there is no equivalence between lawfulness and determination if the latter is defined as way of becoming. Something might conceivably emerge out of nothing in a lawful way, or, conversely, it might be produced by something else but erratically and not in accordance with law. This is why in causality the thesis of general determinism, or neodeterminism, is stated as the conjunction of the genetic principle, nothing can arise out of nothing or pass into nothing, and the principle of lawfulness, nothing happens in a lawless, arbitrary manner. The principle of lawfulness is presupposed by the search for laws of any type, and the genetic principle is both a generalization of available knowledge about modes of becoming, and a deterrent of magic. By the way, the cosmological hypothesis of the continuous creation of matter out of nothing should not be invoked against the genetic principle. If we wish to build a scientific ontology, we should not employ ad hoc conjectures conflicting with well-established laws of conservation. 2. Is any assumption of lawfulness extraneous to the quantum theory? The core of the quantum theory is, like that of any other factual theory, a set of law statements, such as wave equations and commutation relations. Of course, these are not purely or even predominantly causal laws. But this, again, is not peculiar to the quantum. 1 Richard Schlegel, Mario Bunge on Causality, Philosophy OJ Science, 28, 1961, pages 72 to 82. 2 Sidney Morgan Besser, Review of Causality, in Scientific American, 204, No. 2, 196 R, pages R75 to 8. 378 Appendix A Theory. There are few strictly causal laws in science 3 and, as causality tries to show, rather than pure causal laws there are causal ranges, or domains in which certain laws can be said to be predominantly causal. 3. What is the causal range of a scientific law? Let us apply the analysis of causation proposed in Causality to the study of behavior. The program of the causal theory of behavior might be phrased thus. Given a class of organisms, example white rats, and a set of external stimuli or agents, example sounds, the responses of every member of the class of organisms, or patients, will be uniquely determined by the external stimuli according to a set of laws. Consequently, the knowledge of such laws, conjoined with information about the relevant circumstances, kind and strength of stimuli, and initial state and previous history of the concerned organisms, will enable us to predict every single act of each member of the given class of organisms. Now, one such law expressing the causal stimulus-response nexus is the well-known psychophysical relation which, for the case of sound, is I, R equals K, so point 3. We know, however, that this law is incomplete, it covers only overt responses, and it does not account for internal stimuli, which may be assumed to give rise to spontaneous responses, i.e., to responses that are random relative to the distribution of external stimuli. Suppose a neo-determinist pointed out this non-causal aspect of behavior and wished to correct EQ I, by including in it a spontaneous response term U, independent of the external stimulus S. This generalization can be done in either of the following ways: a. Phenomenological, y. by regarding U as a random variable, without inquiring into the source of its variations, and b. representationally, by regarding U as dependent on some lower level, physiological variables. The former approach will be regarded as a temporary expedient by our determinist of the Nouvelle Vague, who will prefer the deeper theories to phenomenological summaries. Suppose he calls collectively X these sub-behavioral, hidden parameters, which are not open to behavioral observation but are assumed to be scrutable by physiological, example neurological, means. In the spirit of determinism, a conceivable enlargement of EQ I, to cover internal stimuli, but not covered responses, is the following: 4. R equals K. So point 3 plus U, X. EQ 1, which is a special case of EQ 2, may be called the causal approximation of EQ 2, if preferred, the causal range of EQ 2, is the region for which VR. The qualification must be made that neither EQ I, nor EQ 2, cover the non-causal range below the absolute threshold. Below this threshold there is no response, hence no causal relation between stimulus and response. The deliberate neglect of this non-causal range is taken care of by the definition of S, which does not designate an arbitrary stimulus but the strength of stimuli above the absolute threshold. Let us finally notice that EQ 2 is deterministic in the sense explicated in section I but not strictly causal. 4. Is the relation between the micro-level and the macro/evil causal? The hidden variables lumped in X are occult from a macroscopic or behavioral point of view, but they may be investigated by the physiologist. He will probably imagine more or less fantastic models, will then express them mathematically, that is, he will hypothesize diverse functions v, x, and will finally test such models. This he can do by investigating behavior in the absence of external stimuli, le, for S equals 0, or, better, in the presence of an approximately constant background of external stimuli, by means of Pavlov OBS or vat ion cages, and trying to control internal stimuli in an indirect way, example by food deprivation. The possibility of setting up a reasonable function VEX will depend on the state of physiology, and the possibility of testing it will depend on the state of experimental techniques. In any case, the hypothesizing of new levels and of relations among different levels has usually paid off. The relation between the microscopic or physiological variables X and the macroscopic or behavioral variable U would be described as a reduction by some, as causal by others. Yet both interpretations seem to be wrong. Reduction suggests explaining away by eliminating the macro level as ontologically and methodologically dispensable, and causation does not apply to interlevel relations because it designates an unsymmetrical connection between an agent and for another conceivable generalization of EQ. I is, of course, R equals K dot so 0.3 I plus U, X. A patient. A relation such as U equals U, X, connects two levels of one and the same system, an organism in the above example, each of them characterized by peculiar, irreducible, but explainable, properties. A distinguished representative of this kind of border zone laws is Boltzmann-Planck's law, S equals K log J11, relating the number W of microscopic configurations to the entropy S characterizing a state of a closed system. Likewise, the imagined relation U equals U, X, is a functional interlevel law. Moreover, the responses U are spontaneous in the sense that they are not, immediately, elicited by external agents, but, since they are linked to definite inner, physiological, processes, they are perfectly determined. 5. What is wrong with theories OJ hidden variables? Bohm, De Broglie, Halbwachs, Schiller, Vigier, Wiesel, Yevik, and others have been speculating during the last decade on the possibility of deriving the quantum mechanical laws from assumptions regarding a substratum or subquantum mechanical fluid or field, much in the same way as a psychologist would like to derive part of the overt behavior from physiological processes, see Sector 3. In trying to explain the seen by the unseen, and to split the latter into distinct but connected levels, these physicists are following an old tradition launched by the Greek atomists and embraced by modern science. Even though we may object to some of their speculations, 6 we should stimulate their attempts. Science is the work of bold imagination no less than of patient work, and nobody can predict whence is the new light to come. As the mathematician Isaac Schoenberg used to say, scientists need be given moral credit for their fantasies as much as they need financial credits. Let us only be clear that these new theories, contrary to their own authors' claims, do not reinforce causality, they do support general determinism and realism, in the sense that they reject the anthropocentric view that whatever happens in the universe, example the sun's flares, is the result of an act of observation, and assert on the other hand the objective existence of microsystems. The hidden variables occurring in these theories are supposed to describe objective properties of the microsystems or of the background fluids or fields that are supposed to explain the former's properties. On the other hand, the usual quantum mechanical observables, which are observable in a Pickwickian way, may be interpreted as describing objective system apparatus or, better, system macroscopic surrounding interaction. See Fig 38. p. 349, of this book. This basic realistic epistemological viewpoint is common to most attempts at deriving the quantum mechanical laws from more basic equations, thus it is openly proclaimed by one who opposes both what he calls the Copenhagen doublethink and Bohm's pseudo-causality. 6. Has the hidden variables revolt been sterile? First of all, the various heterodox generalizations and reinterpretations of quantum mechanics have not been found false, even though some of them are incomplete, particularly those which do not account for the process of measurement. The only pertinent question is whether they add to our knowledge, do they provide a conceptual enrichment, and do they account for hitherto unexplained facts? The hidden variables approach has, so far as I can see, two main aims: a. The epistemological cleansing of the quantum theory, its purification from subjectivistic, Anthropocentric assumptions. B. The enlargement of the quantum theory with a view to encompassing experimental results such as those regarding the possible structure and mutual relations of the 30-odd fundamental particles. Of course, the practical utility of the new approach will be measured by its ability to account, say, for the Nishijima-Gell-Mann scheme of elementary particles. Victories on this frontier are being reported. 8. But quite apart from such possible positive results, a new look at certain problems may be worth trying, if only because it constitutes an exciting intellectual adventure, or at least because it enables us to evaluate the old view better. As Sing 9 says, the lust for calculation must be tempered by periods of inaction, in which the mechanism is completely unscrewed and then put together again. It is the decarbonization of the mind. Of course, such critical work and tentative speculation may not find room in the physical review and may not count for academic promotion, but they are the salt of science and they should command the respect of those who prefer the safe highway to the trail in the jungle. But even if the new look were finally found insufficiently fruitful, its practical failure would not support the orthodox theory, just as eventual modifications of the relativity theory will not revive the hypothesis of absolute time. In formal science we are often faced with the decision between two contradictory propositions, one of which is supposed to be altogether true. But in factual science, more often than not, competing hypotheses and theories are not contradictory but contrary or incompatible, and each of them contains an element of truth. In such cases, tertium datur. Furthermore, the criticism from apparent sterility presupposes that the subjectivist, or positivist, or operationalist, interpretation of the quantum theory has been fruitful, and this is at least controvertible, because the theory was first built and then made philosophically palatable. Heisenberg's operationalist requirement that only observables, measurable quantities, should enter physical theory was attached to it a posteriori, in his famous 1927 paper, as was recognized by Bridgman-Ello with his characteristic frankness. I have always wondered, however, whether perhaps this requirement of Heisenberg was not formulated after the event as a sort of philosophical justification for its success, rather than having played an indispensable part in the formulation of the theory. To sum up this section, the criticism of the orthodox view has been epistemologically fruitful, and it has stimulated creative imagination. Progress along realistic and neo-deterministic lines is being made, and some new look was needed anyhow to cope with the flood of new facts, as well as with old difficulties. 7. Is the present quantum theory perfect? Although computing physicists and dogmatizing philosophers are entirely satisfied with the present state of the quantum theory, the more open-minded and imaginative scientists believe that much could be improved both as regards the formalism and the interpretation. Do we know for certain what a coordinate and a velocity are at the quantum level? Or, if preferred, are we sure we have correctly identified the position and velocity operators in the theories of spinning particles? Are we sure cutoffs and renormalizations are not ad hoc assumptions designed to save theories rather than phenomena? Are we to remain satisfied with the black box approach, S-matrix, dispersion relations, and other phenomenological theories, instead of looking for deeper theories that may tell us what goes on inside the box? Shall we continue thinking that the elementary particles are actually elementary, simple, undecomposable, no matter what the interaction energy? Shall we continue regarding them as point masses and yet go on attributing to them more and more properties? These and others are questions open-minded and seriously aimed scientists and meta-scientists ask despite the veto of the powerful yet declining Conservative Party. 8. Does causality advocate a narrow kind of causal determinism at the level of elementary particle processes? What causality does maintain is that the quantum theory is not indeterministic, in the sense of surrendering both the genetic principle and the principle of lawfulness, see section I, even though it does set important restrictions on causal determinism. More specifically, the following points are made in this book. A. Quantum mechanics, whether in its orthodox interpretation or in any of the numerous tenable heterodox versions, is not only lawful but, moreover, respects the genetic principle. For instance, the theory does not maintain that light comes out of nothing in a lawless way, but assumes that light is emitted by microsystems, example atoms, in accordance with definite non-mechanical mechanisms, example quantum jumps, and definite laws, mostly of a statistical character. b. In all of its interpretations, quantum mechanics restricts causality without eliminating it entirely, in the sense that it does not sweep out causes and effects, but rather the rigid causal nexus among them. 12. c. The subjectivist, positivist, operationalist interpretation is neither deterministic nor indeterministic in an ontological sense, as was made clear by Philip Frank long ago. How could it be, if positivism does not postulate the existence of an autonomous external world? What this school asserts, in connection with the quantum level, is what in causality is called an empirical indeterminacy. It declares that there is no direct autonomous, objective, connection between any two successive states of a microsystem, and it asserts that only connections among observations among results of acts of observing subjects are dealt with. A detailed discussion of the philosophy of quantum mechanics and electrodynamics will be found in my M.A. to Scientific Queries. 13, cd, in heterodox interpretations of quantum mechanics, notably in the one advanced by Bohm in 1952-14. Newtonian determinism, with its causal ingredient, is partially restored. 15. Notice that it is not maintained that this is a causal interpretation, but an interpretation with a causal ingredient. The terminology of causality differs considerably from that of Bohm and co-workers. In short, causality does not advocate causal determinism at any level. It does try to show that causal determinism is not as dead as had been supposed, and that it is sublated under a far richer determinism. 9. Are the differences between the various meanings of law secondary? Consider, a. the objective pattern of free fall in a void, b. the approximate reconstruction of the foregoing pattern by the law statement. If a body falls freely in a void, its acceleration is constant, and c. one of the latter's possible translations for test purposes, namely, if a body is dropped in a void, it is found to within expert mental error that its acceleration is constant. In my terminology, a. is an instance of a law, b. of a law 2, and c. of a law 1. There is even a fourth meaning of law, that of metanomological statement, or law-like statement about laws too, which need not concern us here. The acceptance of the existence of laws, or objective patterns, is peculiar to deterministic realists, but the need for a special term, such as law, for the mere discussion of realist and non-realist doctrines of scientific law, should be granted. How else can we explain the meaning of belief statements such as there were laws before their discovery and its contradictory? The further distinction, between law 2 or nomological statement, and law 3 or nomopragmatic statement, is needed as well. The latter contains pragmatic terms, which careful statements of laws 2 avoid. The terms is dropped, is found, and experimental error, italicized in sentence, c. above, are relevant to the study of free fall. They arise in the test of its laws too, but such terms are never regarded as a part of laws 2 themselves. For a further examination I must refer to my M.A. to Scientific Queries. 10. Is causality in our minds alone? It is a presupposition of causality that a discussion of causal determination relevant to modern science should take into account the two basic traditions of Aristotle and Hume, but should depart from them in the sense that it held hinge on the concept of law, which is the heart of modern science. If there is causation in the world, it is because there are causal laws or, at least, laws with a causal range, see Sector 3. Hence the whole question of the nature and objectivity of causation cannot be discussed in connection with complex everyday phenomena, such as slipping on a banana peel, in which it is next to impossible to unravel the logical net. It must be shifted to the question of the nature and objectivity of scientific laws. If we maintain that causation is objective, it is because we think that causal laws are constructs, laws too, that to some extent reconstruct, with conceptual units, corresponding objective patterns, law slow. If the opposite belief is held, then the following puzzles must be solved. A. Why do we never seem to hit upon ultimately correct law statements? B. Why are law statements not only corrigible but eventually corrected, even though we normally presuppose the constancy of objective patterns, loss law? And C. Why do we care for the test of those hypotheses we call laws too instead of adopting them as convenient summaries of available information? On the other hand, to say that causation is objective at least to some extent, is like saying that electrons are real. In either case our mental picture is at best approximately true, and the attribution, X is a causal law, X is an electron, is a mental act. So that, in a sense, causation is in our minds but not in our minds alone. The same is true of our judgments about the capabilities of other people, or shall we deny them? Unless they wish to look philosophically sophisticated, scientists adopt a realistic epistemology including the hypothesis of the objective reality of loss law, much for the same reason that we admit a certain humanoid pink patch as corresponding to a flesh and bone woman, and also because they have stated the great heuristic value of realism. Whereas subjectivism leads to the steedal speculation of an Eddington, realism impels us to enrich experience and criticize theories. Scientists place such a high value on the assumption of the objectivity and immanence of laws, that they have made it part of physical theories. Two distinguished specimens of such metanomo logical statements recognizing the objectivity of laws vis-a-vis of the cognitive subject 17 are: the laws of nature are invariant with respect to the conditions of observation, or with respect to the state of motion of the observer, and transition probabilities are independent of the choice of representation, or do not depend on the mode of observation. II. Do all terms occurring in scientific laws name objective entities or properties? While a naive realist would answer yes, a critical realist would reply no, and would add that scientific theories introduce certain concepts which have no factual correlates, such as the components of vector quantities, Lagrangians, and the average American. The fact that any physically significant function of the space and time coordinates can be Fourier analyzed does not mean that the infinite ensuing components represent each a real wave. The fact that certain partial differential equations are separable does not mean that each of the resulting equations portrays a bit of reality. While a law statement as a whole is supposed to have a real referent, the way of building up such a whole depends not only on the world but also, perhaps mainly, on the available conceptual tools. It might even be argued that only whole bundles of law statements have a real referent. This is all a realist would claim, and all causality, ch. ij, and metascientific queries, chs 4, 5, and 10, maintain. To claim more would be unrealistic. T2. Is Ohm 1's law causal? The law E equals Ri, the electromotive force is proportional to the electric current, is causal at IT8 ohm, macroscopic level, on condition that the customary interpretation of the electromotive force as the cause, and of the current as its effect, be retained, and on condition that the magnetic field does not react on the current, which is true in the case of the stationary state. Certainly, Ohm's law asserts an interdependence among certain variables, but so does every other functional law statement. When studying scientific laws from an ontological point of view, we are little interested in their mathematical form, if any. Thus, one and the same integral equation may be used to describe a physical phenomenon of hysteresis and a biological or psychological heredity or memory effect. The fact that not only the electromotive force E and the intensity I, but also the resistance R appear in Ohm's law, does not show that two agents are at work instead of one, so that no simple causation operates. Resistance, like permeability or solubility, is a disposition, so that there is no ambiguity in saying E causes pound when a given circuit, characterized by a given value of R, is referred to. The causal nature of Ohm's law is better seen upon recalling the meaning of E in field theory. Translated into the language of field theory, our law takes the form E equals L/U, J, where E denotes the electric field strength, which is a specific force, and J the electric current. density, and U the conductivity of the material. Since U is constant for every conductor in a given state, we may introduce the concept of specific current density, designating it by, whence the last law statement would read E equals, a form which facilitates the causal interpretation. But it is no less interesting to discover the limitations of this causal interpretation of Ohm's law. Thus, example, both E and R statistical averages rather than irreducible quantities. Such limitations suggest the inadequacy of the theory of efficient causation and the need to conceive a neo-deterministic theory containing a broad spectrum of determination categories. 13. Is every ordered time sequence causal? Laws which state changes of state without pointing to causes producing unambiguously and ab extrinsico such changes are non-causal according to the terminology of causality. Of course, if state is misconstrued as event, then every regular non-branching sequence of states will be called causal. The trouble is that a state is not an event but a cluster of J properties, what is elsewhere 18 called a poistem of a system. Thus, example, the thermodynamic state of a gas contained in an insulating enclosure with a given volume will be defined, as physicists usually say, by the internal pressure and the temperature of the gas. An event is a change of J state, such as a gas expansion, or a particle collision. An affair can be a cause, a state of affairs cannot. And if scientists occasionally, when philosophizing, construe states as events, the meta-scientist has to notice the semantic shift. Now, if only events E.g., changes of properties can be physically efficient, whether in causal or in non-causal ways, then it is clear that relations among states such as those specified by state equations, like the law of ideal gases or the wave equations of the quantum theory, cannot be causal. A necessary condition for a causal nexus to obtain is that some change be involved. Yet this condition is not sufficient. Consider the elementary equation of state of the perfect gas at a constant temperature, namely PV equals const. We may rephrase it in search for a causal interpretation. Thus, we may differentiate, obtaining PdV plus VdP equals 0, whence dV/V equals dP/P. This equation may be read thus: the relative decrease in volume, dV/V, equals the relative increase in pressure, dP/P, accompanying the compression. This is not a causal statement, it expresses a symmetrical, reversible, relation between compression and increase of internal pressure. A purely formal transformation did not and could not have the virtue of infusing causation into our formula. But causal statements will be obtained if we enlarge the context, by including in it references to the surroundings of the gas. For example, we may establish an interaction between the gas and its environment and, in the treatment of this reciprocal action, we may neglect the reaction of the gas on the environment, since we are still interested in the gas rather than in the world as a whole. We now may add, for instance, that the previously considered compression was caused by an external force and that, in turn, the decrease in volume caused an increase of the internal pressure. In short, changes of state, but not states themselves, can be produced, and sometimes linked, in a causal way. Consequently, not every pattern of succession in time is causal, it may simply be a self-unfolding sequence of states. 14. Are contiguity and antecedence essential to causality? That action at a distance violates causality has been maintained by many. That this contention is mistaken is shown historically by the fact that causality was accepted during the reign of Newtonian physics, roughly 1700 to 1850, which was field-free and admitted actions at a distance. Contiguity, or nearby action, is like antecedence consistent with causality but logically external to it. In fact, the principle of nearby action and the principle of antecedence can be formulated independently from one another and from the principle of causality. Quite general possible formulations of the former are as follows. 3. E, x, x. C, x. dx, nearby action. E, t, equals foot k2, t, tf. C, t. dt, antecedence, co. where C designates the cause, input, or stimulus, impinging on the concerned system at the place x different from, and at a time t earlier than, the place x and the time t at which the effect, output, or response E occurs, or is calculated. Point 19. It is logically possible to build theories respecting nearby action but violating antecedents. Thus, by superposing retarded and advanced electromagnetic waves, we obtain fictitious fields which propagate instantaneously. Incidentally, it is a mistake to suppose that some theories admit an influence of the future upon the present. All scientific theories, even the overtly non-causal quantum theories, admit or presuppose the principle of antecedents, which is often called causality condition. Likewise, it is logically possible to build theories respecting antecedents but violating nearby action. However, this would be pointless, because retardation is precisely explained in terms of traveling along a distance. In short, contrary to what Hume and his followers have supposed, nearby action and antecedents are logically independent from one another and from causality. The occurrence of the term C and E in equations 3 and 4 is not enough to ensure that they designate causally related events. Those formulations of nearby action and antecedents do not involve specific mechanisms, they are consistent with both phenomenological and causal theories. On the other hand, there is no general mathematical formulation of the causal principle, of the kind of equations 3 and 4, 15. IJ strict and pure assation works never and nowhere. How is it possible to confirm causal hypotheses? Is this a contradiction, or does it point to an ambiguous use of cause? Neither the one nor the other. If we say that the Galileo-Newton equations of ballistics have been verified many times, we do not thereby mean that the phenomena they partially and approximately describe are entirely mechanical. We know that a part of the bullet's kinetic energy is transferred to the air in the form of heat, that electric charges are generated by fridation, that the Earth's magnetic field has an influence, and so on. Every law, whether of physics or of sociology, is valid exactly only with respect to the corresponding theoretical model, which disregards canalplications. The confirmation of an empirical hypothesis by means of a set of observations does not enable us to equate our model with its real referent. There is and there will always be a residue. Thus, example, if we state the causal hypothesis flames burn the skin, we make a statement which, on a first level of analysis, can be termed causal. But a deeper analysis will show that the phenomenon itself is not strictly causal. Further categories will be needed to account for it, such as interaction, example the deformation of the flame by the very process of tissue burning, teleological determination, example the action of cicatrice ants in the burn zone, chance, at the molecular level, and so on. Strict and pure causation is as ideal yet as useful as any model can be. Have almost as many meanings as there are philosophical schools. In such cases it is better to attempt to elucidate the term by clarifying, expanding, or building a theory. In causality, the theory of efficient causation is chosen for this purpose, because of its richness and long-standing, even though it is concluded once and again that this theory is, strictly speaking, false. Much in the same way, a physicist who wishes to elucidate the term force will refer, example, to Newton's mechanics, even knowing that the theory contains blatantly false assumptions. Divergences with usage will of course in this way, but the aim of a monograph on causality could hardly be the recording of the ways people use the term cause. This is a task for dictionaries. One such remarkable deviation of the philosophic from the scientific usage of causality occurs in recent physics, where the phrase causality condition occurs frequently to designate the hypothesis that the cause is never posterior to the effect. This same condition is called hypothesis of antecedents in causality, where it is shown that antecedents and causality are logically independent principles. See Sector 14. After all, usage can be wrong, and the job of philosophers is not to perpetuate but to straighten wrongs, even if by so doing they may look quixotic. From Aristotle we have inherited not only the most influential theory of causation but also the definitionist mania, consisting in the belief that all key terms should be defined. Since production is such a term in causality, the definitionist expects its definition much as the beginning student of mathematics asks for an explicit definition of number. Yet logicians have taught us long ago that primitives must be accepted in every context unless one is prepared to run in circles. The meaning of such primitives can, of course, be explained extra systematically, example by way of examples. Thus we will say ionizing radiation produces tissue damage, and not CERN-ply tissue damage is followed by or conjoined with ionizing radiation. With the exception of Hume and his followers, everyone knows the difference between a relation of production, on the one hand, and the various non-genetic relations, such as functional interdependence, statistical correlation, and accidental coincidence, on the other. The interesting probability is to distinguish the causal from the non-causal patterns, and this is attempted in causality, where a variety of determinants and kinds of law are distinguished. In conclusion, I am glad that Professors Schlegel and Morgan Besser have perceived the need for a revaluation of causality in the present age, and I am grateful to them for having elicited the above compliments and illustrations.